the state of AI. Well, the growing technology has major implications.
Generative AI, the most important technological arms race.
Are you about to reveal something about AI?
That was GPT-4o.
So ChatGPT, this is what I ended up with. How does this look?
It looks perfect. You've solved it.
In a recent development, Meta has achieved a breakthrough by introducing Voice Box. It is the most versatile AI for voice generation.
OpenAI's ChatGPT has become a global phenomenon. Amazon has now jumped on the bandwagon as well.
The AI market is all set to explode. This industry is likely to become a $1.3 trillion industry.
What we just witnessed recently is nothing short of a revolution in the world of artificial intelligence. Tools like OpenAI's ChatGPT, Google BART, and other generative AI tools are now helping people not only write essays or code, but also compose music, create art, and even assist doctors in diagnosing diseases. In fact, in a recent discovery, a generative AI system helped researchers design a brand new protein that could lead to groundbreaking medical treatments. Isn't that amazing? But have you ever wondered how these AI systems can understand human language, predict what comes next, or even generate creative content that feels so real? Let me tell you, it's all data. Generative AI is trained on vast amounts of data from the internet. It could be text, images, audio, videos, which then use complex models to find patterns, learn, and create. This is why AI is growing at lightning speed. According to Bloomberg Intelligence, the generative AI market is set to grow massively to approximately $1.3 trillion over the next 10 years from a market size of just $40 billion in 2022. But what's driving this growth? Well, businesses across industries, healthcare, entertainment, education, and even retail are using Gen AI to transform the way they work and save tons of time. That's why industries are under complete restructuring. Employees are getting laid off, some job roles are vanishing from the face of this planet, and new AI-related jobs are shaping up within the industries. According to the research by the World Economic Forum, AI is expected to remove 85 million jobs while creating the need for new 97 million jobs. Even on the LinkedIn job board, there are over 136,000 job openings in AI-related roles worldwide, and this number will keep climbing every day. That's why if your goal is to become future-proof, you need to learn the skill of generative AI now. To exactly help you with that, we at Intellipaat have prepared this comprehensive Generative AI Foundation course. This Gen AI course is designed to help you take your first step into this fascinating field. Whether you're curious about how AI models work or what are the fundamental blocks used to develop these tools, then this course is a great starting point. Let me take you through the agenda that we are going to cover through this extensive course. We'll start by exploring embeddings and deep learning, diving into how these techniques have evolved and why they're essential to generative AI. Next, we'll briefly touch on recurrent neural networks, RNNs, to understand the foundational concept of processing sequences. Moving on, we'll introduce the game changer in generative AI, the transformers. We'll discuss their decoder and encoder architecture and how they revolutionized sequence processing. From there, we'll look at sequence-to-sequence models and context vector and tokenization. Next, we'll dive into self-attention and multi-head attention, two critical mechanisms that help transformers understand the relationships between words or tokens in a sequence. We'll also look at position encoding, which helps models capture the order of words in a sequence. After understanding the mechanics, we'll introduce BERT and its various types. We'll also have a hands-on implementation on BERT, where you'll see how it works in practice. Finally, we'll wrap up with optimizing the program, learning how to fine-tune generative AI models for better performance. So now that we're clear with the agenda, let's look at the very first topic on our list.
So before we start with the journey of LSTM, just want to go through basic concepts first. So you guys are aware of what is neural network or artificial neural network. So there are neurons, and then there are hidden states, and there is a final output. So this is your input, this is your hidden state, and this is your output. This you are aware of. Right? Then, in order to make it better, there is something called as a dropout. You are aware of dropout. So in the dropout is used, dropout is used when you are building a neural network which goes deep. You want to reduce the overfitting. So what you do, you randomly drop a couple of internal nodes so that the pattern and doesn't go overfitting. Okay, that is the purpose of dropout. Randomly switching off couple of nodes. So the node will take the input but will not pass it. So if it is a deep neural network, some of the nodes will get switched off. Which brings to the question, dropouts is fine. Activation function. Yes, this introduce non-linearity. Yeah. So there are different type of activation functions. There can be a sigmoid, there can be a tanh, there can be a ReLU, there can be a leaky ReLU, exponential, and all that. Okay. So you are aware of dropout, you are aware of activation function. Next concept is, are you aware of this concept as well? That is back propagation. Okay. So what happens in back propagation? It just weights and biases. To decrease error. Okay. So how is back propagation different from gradient descent? If you want to adjust weights and bias and decrease error, they both come under the concept of optimization. So GD is also optimization. If this is my input nodes, so I'm going here to get my output. Now, if I go back and start training the nodes, that's the difference. GD optimizes based on learning rate. And how does back propagation optimizes? Okay. So let's take an example. A person is at point A and he has to reach point T. So a person has to take a train and reach point X1. At X1, a person has three options. A person can again take a train, can go by road, go by air, go by taxi. Okay, it will reach some other place. That will be X21, X22, X23, X24. And from here, it will reach to this place. Okay. Now, let's say we extend it even further. That means from reaching A to point T, I'm just expanding it. I can reach to X1. From X1, it can reach to X21, X22, X23. From here, it will reach to X3 to 1, X3 to 2. From here, it will reach to X3 to 3. Here, it will reach X3 to 4. From here again, some nodes will happen. And finally, it will reach to T. Now, when the person, let's say Shiva, is taking these many options and reaching over here, so let's say a Shiva takes this route. It cannot take all the routes. Shiva takes this route. But Shiva is not reaching on time. Shiva is 20 minutes late. Shiva is 20 minutes late. Is all the junctions where the traffic was, let's say these all are the junctions, key areas, toll booth or whatever, should all be optimized by 444 minutes or 555 minutes? Or is every individual will have a different? Okay, so there are 4 nodes. 1, 2, 3, 4. I'll write it in yellow color. These are, let's say, the 4 junctions for you to reach your office. Okay, imagine you have to reach, all of you have to reach your office. You are an individual, you have to reach your office. While going to office, there are junctions or there are stops, which takes time. Let's say you have to pick a person or there is a traffic stop. So anywhere there is a junction and you are 20 minutes late. Are you going to distribute this 20-minute late to all the junctions by 5 minutes? That is case 1. Or case 2 is I will find out which junction requires more time. There is a possibility junction 1 requires 10 minutes of optimization and junction 4 requires only 1 minute of optimization. So which case is more likely? Case 2. How would I know what exactly is the impact of each case? Case 1 is your gradient descent. You understand the error. 20 minutes is your error. You go back, you update the input. That 20 minutes is the error, adjust whatever you want to do. But if you want to hit every single attribute at a different level, what do you need? You want to know the impact of every individual. Yes or no? So if I am at point A, I want to go to point B, and I want to know the impact of going from point A to point B. What do I do? If I know to know what is an impact, impact is implemented using dy by dx, rate of change. Okay, but if dy by dx is something like that, we write, correct? So if x is a function of y is a function of z, I want to find the relation of dz by dx. I cannot directly find the derivative. So what I'll do here is I'll say d dou of z with dou of y times dou of y over dou of x. This is your chain rule. This is your called as partial derivative. So I basically want to know how individual hidden node is impacting. And when you do this, you actually create the learning. Actual learning happens using this. So now if you are going forward, you have to come same way backward to update. At an individual level. This is the core idea of deep learning. Good. So if you are aware of backpropagation, if you are aware of gradient descent, if you are aware of dropouts, so the next topic comes is after we do ANN, we have different approaches by which we can solve the problem. One is we use convolution. Okay. Convolution means I take two functions, T1, T2. If I convolute them, I'll get T3. Now, T3 is going to give me a derivative of this function in such a way that I can understand what exactly it is talking. Or means I can understand the features of my T1. Okay. So this is where the convolution comes. Again, it's a different mathematical formula. The second part is if I don't have a data which is, or if I have a data which is in sequence. This is in general. But this is the data if it's primarily based on a sequence. When I say sequence, what does it mean? It means at time t, I have value as 2. At t plus 1, whatever is my value, it makes an impact. My value will be either 2 plus minus 1. Example, what it can be the example for this? Since the World Cup is on, so can we say T20 can be an example of sequential data? So the interesting part of that sequential data is completely different in behavior. So you have over 1 till over 20. You have made 5 runs now, then you are making 6, 7, 6, 5, like this every over till over 7. Then from 7 to 15, you start making 8, 9, 8, 9, 8, 9 like this. From 15 to 20, if last 5 overs are there, it doesn't mean that whatever you have made, you will just take an average and make run out of it. You can suddenly start making 10 plus runs over here. Right? So you rely basically on the latest information that you have rather than what was happening in the first part. So the recent information carries more weight than what the starting point was. Now, this kind of behavior does not exist everywhere. You remember this. This behavior does not exist everywhere. Primary example I'll give you. All of you have done graduation, right? Semester 1 to semester 8. Whatever score you score in semester 1, it is very difficult to do if you are scoring 50% in semester 1, it is not possible you start scoring 80% aggregate in semester 8. Not possible. Simply not possible. So understand, sequential data doesn't mean that everything which is happening in sequence is a sequence. I mean, it is a sequential data, but it is not that like a T20. This is a different variety of a sequential data. This is a different variety of a sequential data. Okay. So domain matters. Third example is COVID cases. So if you take a 100-day scenario from 1 to 100, for first 50 days, you might have 100 cases every day, and suddenly you start peaking like this, usually referred as wave 2 in India. Okay. But if you would have observed the news, they were also following moving average. Okay. Stock market. So stock market also is an indicator, is a data which comes in a time series. What else is in time series? Or what else is something which is a function of time? May I have a cup of What is X? If I write the same sentence, may I have a class of, what is X? Water, wine, right? What is the difference between scenario 1 and scenario 2? So that means if I have to analyze X, what is happening at, let's say this is Tn, this is Tn minus 1, this is Tn, this is Tn minus 1. So if I want to know X, I should be knowing what is Tn minus 1. So is this a sequential data? It is a sequential data. So text analytics can also be considered as a sequential data problem, which gave rise to a beautiful concept called as RNN. Now, what is a journey? My journey is I was doing very happily my machine learning. Then there was a concept called as a neural network. So I took neural network to solve my machine learning problem. So I created deep learning. In deep learning, I solved my first problem with ANN, artificial neural network. What does artificial neural network was doing? It was basically trying to solve a classification / regression problem. Then this got evolved and we started learning CNN. That means convolutional neural network. Okay. Now convolutional neural network can solve both image problem and text problem. Okay. What it says here is your input needs to be convoluted with the random weights, and whatever you get is your transformed data. This can be used for analysis. That's it. Okay. DL is an evolution of ML. Okay. In deep learning, we start till machine learning, you only have gradient descent. It is deep learning which gives you the gradient descent and back propagation. It is a back propagation that is a game changer. It is a back propagation which enabled a neural network to behave like a deep learning model, because you would have learned something called as perceptron. Maternal uncle of Megatron. Heard of this term, perceptron? Single cell. Single neuron. What does it do? Was doing exactly what machine learning was doing. Because learning was not there. You can add a activation function to it. Does not ensure self-learning. So the self-learning comes from back propagation. That's why we emphasize so much on back propagation. Now ANN gave rise to CNN, and from CNN, we wanted to solve a very niche problem, and that problem was sequential data. And that sequential data was solved by using RNN. Recurrent is the term here. In English, recurrent means something which keeps happening again, and again. Okay. So CNN took a different path, and it took the path of building mega CNNs like AlexNet, VGG, ResNet, etc., etc., etc. RNN went ahead and starts building the recurrent neural network, where a neural network which is specialized to solve a sequential data problem. Okay. These are the algorithms that you can use inside CNN. And at some stage, something magical happened here. And what was that? Transfer learning. So this is a complete different path. Whereas this path was different. You were handling the recurrent neural network. Then we realized there is a problem. I will discuss that problem and we move to LSTM, long short term memory. Okay. So LSTM is a RNN on steroids. LSTM later gave rise to transformers. Okay. But there was a journey. What was the journey? So when we were building the LSTM, there is something else which was happening parallelly in the world. And that is called as embeddings. So which brings to the next question. Are you aware of what is embedding? You're not aware of embedding. So, like I said, we had multiple problems happening here. We were in the middle of a lot of problems when we were walking through this journey. So there were always two types of problem statements that we were trying to solve. What were those? Structured data, unstructured data. Yes or no? What is the example of structured data? Excel sheet. Everything is in a tabular format. You will predict target variable, right? What is unstructured data? Value in key value pair. That means I'm inserting all the books into my database. And when I insert all the books, what I want to do here is I want to classify my books belong to maths, my book belong to physics, my book belongs to machine learning. Probably I am trying to solve a library management case. Okay. So now library management is, so now I'm making a library management system, but key to value is how my unstructured data is. Now I want to build a classification system. So how do I classify which book belongs to which category? So I have a library management system and I have 100 books. I want to find out which category the book belongs. Now, if a human has to do, how does a human will perform this job? Human will read. Human will identify the words. If a book has words like maths, linear algebra, matrix, or solving X and Y, the tendency is this is going to be a maths page or book, right? If you are talking about thermodynamics, if you're talking about entropy, if you're talking about nuclear science, if you're talking about metal, non-metal, mostly I'm talking about physics. It's a very different story that all of them has a mix and match when it comes to machine learning. So I'm going to make a lot of mistakes when I'm predicting machine learning based on these words. What are these words? These words are basically my vocabulary. In English, it is vocabulary. For a machine learning engineer, it is features. So I'm going to analyze which feature is coming where in order to decide which is the book I'm talking about. So if I have a book which has these features as well as these features, I will see where the frequency is high. If the frequency is high with the maths feature, I will call it a maths book. If the frequency is high with the physics book, I will call it as a physics book. So this is called as embedding. So how did I solve this? I used the bag of word approach. And I gave priority to the frequency. Have you heard these two in together ever? Bag of words, frequency. Then I learned that bag of word will not work in all the cases. I need to have TF-IDF. What is my TF-IDF? TF-IDF is term frequency inverse DF. Inverse data frequency, something like that. That means if I always give priority to the frequency, what will happen to the rare words? So if you analyze, let's say you are going to analyze Apple stock from Twitter. What will you do? Oh, sorry, I'm old generation guy. You call it X, right? I still call it Twitter. You guys know what is Twitter X, right? Okay. So what will you do? You are going to say @APPL and then you analyze, right? This is what you will do. So you are going to get all the tweets. Yes. So in bag of word like is will not hold good significance if you are removing the stop words. Okay. But that is controversial. Which stop word to remove, which not to remove. When you are doing an academic exercise, you remove all stop words. That is okay. But think about it that, if you have to remove all the words like is, you, new. So then what happens here is if you remove the new, then the thank you loses the you. The New York loses the new. So I cannot easily remove the stop words. That is another problem with stop words. So what I do here is in my bag of word approach, whatever is my word, every word gets similar weightage. I capture all the words. So @Apple, your product sucks. @Apple, your product is the best. @Apple, you guys need to have better customer care. @Apple, please get more hardware shops open. Something like that is there. But @Apple is everywhere present. If I add one thing to every single use case, there is no point. Example, if you have company of 10 people, if I add 100 rupee to each and every one, will they feel that they have got hike? One is more important, one is less important, right? We don't have. So whenever a word is added everywhere and is present everywhere, the mathematical impact of that word is not significant, right? So in that cases we realized the bag of words approach, that is the approach where we are going to look word at a frequency level, is not going to work. Because if I have built my feature metrics for every single tweet I make, so @Apple is always having a frequency. It is as good as saying the standard deviation of this feature is equal to 0. If the standard deviation of any feature is 0, mathematically it is of no significance. Yes or no? Emotionally no significance, mathematically no significance. So can I remove such words? The answer was in TF-IDF. So TF-IDF says all such words which are present in most of the places, should not be part of it. So what it gave rise to rare word scenarios. Okay, rare words also got importance. That means the words with less frequency also got significance. Now, this were the two methods which you would have probably done in your NLP courses on using Python on any text classification. Right? So you did text classification using TF-IDF, you did text classification using bag of word. Difference between TF-IDF bag of word was rarity of the features. Okay. Now, my artificial neural network, other things were going on, but in the case of an NLP, we started with bag of words, then we moved to TF-IDF, and from TF-IDF, we said, let's build complex embedding to find the same thing. So basically, what does bag of word and TF-IDF does is, they give you the unique representation of a word. Yes or no? This is what is happening. What we call it as a DTM, document term matrix. It is basically unique representation. If anyone is not able to understand what is a unique representation, so example would be, let's say I have a corpus as C. And my corpus says these are the words which are important. The, love, hate, beauty, and kill. And I have a document 1. These are present 2 times, these are present 4 times, this is present 0 times, this is present 1 time, this is present 3 times. This is my document 2. It also has some representation. Now, what is my document 1? My document is a vector with this coordinates. What is my document 2? My document is a vector with these coordinates. Now, can I perform mathematical operation and these two vectors identify they are similar, not similar, wherever they are? So, in our machine learning, we have features and we have values. Right? These are the values we have. So we were using this and identify my target variable. Maths, physics, ML. Now I am saying in my NLP, in order to identify maths, physics, and ML, I need to create this matrix. How do I create this matrix? My first step is identify x1 to xn. What is my x1 to xn? Vocabulary. How do I identify what are the 100 words which I should pick to identify? I have to find 100 words from all the books, which are so good that if I can understand the frequency of these 100 words, I can identify which book it belongs to. If you are confused with this one, look at this. This is what I'm talking again. I have to find 100 words. In such a way, I can identify maths and physics. Yes or no? Now, this 100 words will come from which place? I can either use bag of words or I can use TF-IDF. They will help me identify these 100 words. Once I have identified these 100 words, I can recreate this matrix. Now, this process is called, now in this case, it was record 1. In NLP, it will be book 1. So I am going to represent book 1 with the vector. What is that vector? 1, 2, 10, 4. If it was a 2 by 2, you would have understood very fast. So what is my book 1? My book 1 is 1, 2. This is my vector representation of book 1 vector. What is book 2? 2, 3. This is my book to vector. Similarly, can I do this for 4-dimensional, 8-dimensional, 10-dimensional? This is called vectorization. I am going to represent my single object as a vector. If this is understood, this process of vectorization of word is called as creating embedding. Now, again taking this example that I have in NLP, I have what? I have to identify books. In order to identify books, I have to identify x1 to xn. In order to find out the top n words, the approaches that are given to me are bag of words or TF-IDF. Right? But they both are based on words and the frequency. Then someone in the year 2004 at Google introduced, why don't we build a single layer neural network which creates this embedding, and we called it as word to vec. Okay, what do we do? If I have a sentence, may I have a cup of water? Now let's say this one needs to be predicted. Okay, there are two things. One, I can predict X if I have the context. Okay. If this is given to me, I can predict this. Or case 2 is, if I have cup given to me, I will say what are the neighbors of cup. So either I can predict next word or I can predict neighbors. So these are the two type of word embedding that we had. So this is what my frequency based, and this is what my probability based. What are these two? Continuous bag of words, and second is skipgram. This is word to vec, each word as a vector. So when I want to get my all the neighbors, I'll say skipgram. If I want to predict a word, I'll say continuous bag of words. So word to vec is something which is a inbuilt library using GenSim, but it is a very detailed concept. If somebody is interested, you can research, you can do a lot of study on this one. So we have two types of embedding. One is frequency based, where it comes back of words, TF-IDF. And second one is probability based, which is primarily word to vec, and then it is continuous bag of words and skipgram. Also called as SG. Continuous bag of words. The reason I'm taking through your journey here is because when we go to the next topic, that is transformers, the evolution is important because you will not understand why it is there in the first place. Okay. So word to vec was there and bag of word TF-IDF was there. Then we have the next set of embedding that came was glove. Ever heard of this term, glove? The glove is an embedding which is based on co-occurrence. Okay, embedding is heart of text analytics. If you do not understand embedding, you will never able to understand what is happening in text analytics. That's why I'm emphasizing a lot on embedding. So what happened in Glove was Stanford said, okay, you are building a neural based embedding. It has its own issues. The length, the context that you have given, all those things. So what it says that if I use the word ice, ice has a different meaning in sentence S1 and ice has a different meaning in sentence 2. If I'm using ice with cream, it is a desert. If I'm using ice with land, it becomes a country. Yes or no? So if you think of word to vec, ice will have one representation. Correct? Ice has one representation. Based on whatever I have done analysis, ice has one representation, ice has one representation. Everywhere ice can be represented with one vector identity, whatever is my ice. Okay. But co-occurrence glove says ice will have a different representation depending upon what is followed by ice. Now this is tricky. This gave us importance of where in the sentence ice is coming. For example, if I say I live to eat, this is my sentence 1. My sentence 2 is I eat to live. If I see from a word to vec perspective, the neighbor of live is eat, the neighbor of live is eat. S1 is same as S2, right? This creates confusion in text analytics because I am not giving or value to the order or the sequence. This is not there. So this problem got solved using glove. Glove said live is coming before or after. Are you able to understand the evolution so far till glove? Okay. So glove was from Stanford. So if you want to use glove as an embedding, you will have different flavors of glove. You have 60 dimensional, you have, that means you have 60 million dimensional, you have 300 dimension, you have 200 dimension, the size increases. Now, if you take a heavy dimensional embedding, you will always get a better representation of a word. Okay, so it depends upon your corpus, depending upon. So what these were the pre-trained embeddings. And this is also pre-trained embeddings. You can train them, you can create your own embeddings based on it, but mostly people were using pre-trained. Now, first was my frequency based. So I did frequency based bag of words, TF, IDF. Then I went to my probability based, or that was word to vec. And in that I did bag of words and skip gram. Then we did our glove. And then a lot of people started training their and creating their own embedding for open source. Okay. So AWS came and AWS said, why will people use Google embedding? I will also create my own embedding. Microsoft said, I will create my own embedding. Similarly, other big organization came and they created their own embeddings. Okay. So there was a race on creating embeddings in around 2012 to 2016 or 18 around. This was something which was fashionable event. Then what happened? In this time, we started creating another set of embedding, which became which was Elmo. And from Elmo, we did UNFIT. I believe that I have to check. So here, once we reach to this part, so this part is where this is where deep learning neural network came. This was all co-occurrence. Now we started using deep learning or advanced neural network in order to build the embeddings. And that ULMO, I have to check this term. I'll check this one. Elmo you can consider so far. So these were deep learning based embedding, and this is where the transfer learning started happening. So now in order to give a parallel backdrop, we were going from machine learning, evolution was happening. At the same time, in between, neural network evolution happened, which gives rise to ANN. ANN gave rise to CNN, and CNN started following its set of algorithms, and there came transfer learning. Then in somewhere, we started solving text problem. Now, text problem was also parallelly going on, and this was a path where we reached till TF-IDF bag of words. But we were not able to solve transfer learning problem. And when this came, we took this text problem and started word to vec. At this stage, we started probably glove. And then finally, when we reached to the advances of LSTM, parallelly, we had already created Elmo. So almost these things were happening in parallel. They are not individual concepts. If you see them in together as a whole map of technology advancement, you will realize every concept required a push. So it is a cyclic event which has happened. So once your deep learning became advanced, your embedding also became advanced from word to vec to glove to Elmo. Okay. So at ULM fit at Elmo onwards, Elmo is built top of probably LSTM. So at ULM fit, transfer learning was part of it. But how did this came with the help of LSTM is what we are going to study today. So now coming back to our previous journey, that was what was happening in this world. When the embeddings were getting advanced, we were working parallelly to upskill our deep learning models. So in the deep learning journey, we had the CNNs, and for text analytics, which was sequential in nature, we started with RNN, a recurrent neural network. A recurrent neural network had a shortcoming, so we started LSTM. LSTM also had a shortcoming. We started with bidirectional LSTM. Bidirectional LSTM also had a shortcoming. We added attention. It is when we added the attention, the self-attention, the LSTM became very powerful. And after this, transformer came. This was probably around 2019 when this became very evident. Till 2019, this is what most of the people were doing. The paper for transformer came, I think, around 2017, but it was Hugging Face who, when created transformer library, revolutionized the entire journey. So if I have to use any deep learning model, I need to have embeddings. So everyone understands what is embedding. Everyone understands what is deep learning. Everyone understands what is a journey of deep learning and what is a journey of embedding. Embedding gives me the unique representation to represent the word. Deep learning uses that representation of word in order to analyze what would be the specific outcome. Now let's come to RNNs. So the module one is LSTM. LSTM is built on the concept of RNNs. So to understand LSTM, let's first try to understand what is RNN. So to understand RNN, we should evaluate how we read a sentence in NLP, which I have already explained to you. So a simple RNN unit is we have an input which depends upon the time h at time t, and it also depends upon what ht gives input to its own RNN unit for different frame of time. It can be slightly confusing at this stage that what exactly means by giving input to its own time. So basically what we are saying here is, if I have a sentence, and let me just actually go and show you first. What are we saying here is, if this is the input sentence that I have and I have to make any sense out of it. So whatever is what creating an impact, this should also become part of my next input. So if this is my RNN single unit, I am passing what goes here, and this again comes here, goes into the second one. Here I'm passing is, I'm having my old value of what. So at this stage, I have two values, what and is as well. What is coming from here, is coming from here. Then I am generating the third one. So what and is passing through it, and I am passing your also. So whatever I generate now, this output X will have information which will be having what is and your. Now, if I have to represent this everything, I can say there is one RNN unit which takes input, gives me the output, but whatever it is generating as a hidden state, it will hit it back again to this RNN. So at iteration 1, I will pass what? This value will be 0. So my iteration 1, I will have what? At iteration 2, I will have input as it is plus what is my hidden state at iteration 1. What is the hidden state of iteration 1? It is what? So at iteration 2, my final output will be what and is. Okay. At iteration 3, I will have iteration 3 input. And what is that? It is your. But I will also capture the hidden state. Now, every time hidden state is 3 minus 1. So this is also called as t minus 1. If at this time my t is 3, so this hidden state will become h2. So these are the notations. So at time t, I can have input at t, and I have hidden state t minus 1. So when you look at it, initially you might find it, oh, wow, what a complicated terminology it is. But if you start understanding and analyzing it, it might not look that dangerous. So what we are doing here is, I have my input. My input goes, I bring my hidden layer. My hidden layer gets added. I get my input layer. And if you see here, this is what my concept of deep learning ANN is. So somewhere I do this calculation. It's not that I don't do this calculation. This calculation exists, but the beauty here is the input is always changing. It is not a fixed input that you have seen in ANN. My input is all about getting my hidden layer, and whatever I generate here will become my input for next one, and it goes in a cyclic way. So at the beginning, this is my input. Okay, my hidden state is 0. So at iteration 1, I will pass my input at 1, input at t. Let's say this is t equal to 1. input at t and hidden state at t minus 1. What is hidden state at t minus 1? It is 0. What is input at t? It is what? Okay, so what is my output? At iteration 2, my t is equal to 2. What is going to be my output? My output is input at t plus hidden state at t minus 1. What is input at t? Is. What is hidden state at t minus 1? What? So at this stage, sorry. So at this stage, whatever is my final answer will actually become my hidden state for this one, or the output will become. So that is why if you see there is an output which is going here, that is what, and there is an output which goes inside it. So the what will get here, and then what and is will get here, and finally what is your and name will get. Now comes the part which we are learning for long. What is it? Embedding. You remember embedding? What is embedding? When you vectorize a word. What is your activation function? When you pass a value 10 into ReLU, you get the value as 1. Some function happened, or if you want to do a, if the value is 1.2 and you apply sigmoid, the value might become 0.6. Yes or no? These two functions, you know. So what will happen here is what will be first converted into a embedding. Let's say this is the value of what? Okay, let's say this is a vector that represents what? This value will get into a, let's say, sigmoid function. And it will generate one value. Let's say the value is V1. So at this stage, what is getting embedded? Embedding will pass into a sigmoid function and it will generate a value V1. It's a numerical value. This new value will get over here. I already have this value. I have is will get converted into an embedding. Embedding will pass into a sigmoid function. Sigmoid function will have embedding value, whatever is the value for is as well as value of this, and will perform some operation. It will generate one value, V2. That value V2 is basically value V1 plus is. But I am not taking is, I am taking embedding value of is, and then I'm applying some mathematical operation on top of it. This is going to give me V2. V2 will be passed over here as a mathematical value. I am going to pass here, and finally, whatever the value comes is my V3. Now, this V3 is a mathematical value. I have to find out what is an equivalent of this V3, right? In terms of whatever is my use case. So again, I will be converting my numerical value into a meaningful label or a meaningful number or any meaningful word. Now you can connect the dots why embedding and other things were important. Now there can two things can happen. Okay. I may need to predict what is this letter, or I may need to predict what is your name is what? Is it a positive sentiment? Is it a negative sentiment? Is it whatever? It can be a, my output can be a label, means classification problem. My output can also be a word which I need to generate. Both the use cases are possible. So the process of both differs. But I will first give you an example of what does it mean. Generate means, let's say my representation of word is what is like this. I pass this value, I generate some value V1. So that finally I am generating the output here as V4. Let's say my final value of V4 here, I want. So I create a representation. Now what I do here is, this is the embedding, okay? Or I can use another function to identify what. So let's say this is the embedding I got. I'm just giving a rough example. Don't think it is a literally how it happens. It's only for understanding. If what is represented as 0 0.1, 0 0.2, 0 0.3. If I can get the value of what from here, I can also find out wherever this value is matching, what is the equivalent value of it. Can I do that also then? So this is what I will do at this step. If I want to generate, the family of generation is different. The family of classification is different. But I am giving an intuition of how, yeah, it's like decoding the value. Correct. It's like using a decoder to understand what my final output is. But if I have this kind of a model where, at the end of the day, I want to pass the value and understand whether it is a classification based positive sentiment and negative, it would be a slightly different thing. I will be using a softmax function. Softmax function will give me a probability score. So that probability score based on 0 to 1 will identify with the threshold whether I'm in one category, I'm in 0 category, or whichever category I am, or it is a three-way split. Then softmax is even more effective. If it is a two-way split, I can also use a sigmoid also. So depending upon whatever is my classification, if it is more than 2, I will use softmax. If it is only 2, I will use sigmoid. I will get the value. I can use that value to identify and classify. Makes sense? Right? So if somebody gives you, okay, so if this is going to be my value of sigmoid in my, like I explained you, so I am passing my hidden nodes. I am passing my input value, I am passing my bias, and I am generating my output. This output is the hidden state output for RNN. So what this RO will be? Let's say this is my hidden layer value. So I need this hidden layer value, I need this input value, and I need this bias value. So how will I calculate this H0O? So H0O is basically getting the sigmoid function between X0 and hidden layer. So I am getting a sigmoid function between hidden layer and input. Then I am adding bias to it. This is what I am getting output, right? Let me expand it even more. So what I was saying here is, at a first step, I have sigmoid function of hidden layer and input, and then I'm adding a bias. My input is not just input. If my input is X naught, it also gets multiplied by the weights which I'm assigning it in the first group. And these are the weights which gets always updated using gradient descent and backpropagation. So my input is always X naught times W naught. My hidden layer is H, which can be expanded like this. That's not a problem. And then I can have sigmoid, and then I will have beta. And the value will go on and on and on. So this value will be generated as H naught. Then I will have another word. So let's say I have a sentence, and my sentence is, let's say, like this. If sigmoid is not helping, why not use ReLU? Let's say this is a sentence. That means I have an RNN here, 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 6, 7, 8, 9. I will have R 9 RNN units. If I have R RNN units, that means I will go 9 steps, learn, come back 9 steps. You want to add that, add punctuation also. That's not a bigger concern. My concern here is I have to carry forward go 9 steps and come back 9 steps. And I am also making an assumption that whatever is a value of impact of if, it actually is captured somewhere when you are reading the last word value. And whatever is the impact which has happened over here, let's say the error is showing you E1. Now that error has to get populated for all the words which are impacting here using dou of y by dou of z or whatever, dou of e by dou of w y1. So point here is when it comes back, since you are using a sigmoid function saturates fast. All of you know that? Do you guys know that sigmoid function saturates fast? When I say saturate fast is, if you see this line, this is saturation, this is saturation. The only game you can play here is between this. So if you take very small values, all small values will be here, all large values will be here. So the change happens very small. Now the small change when goes over here, it makes no impact if the sentence is long. So as the length increases, the impact decreases. So what we are saying here is, this is my calculation part. And second thing I'm saying is, if I increase the length slightly as well, sigmoid saturates fast and length is large. So the learning is very small, which almost makes it insignificant. So what is happening here is that the impact of making a wrong choice does not carry forward till the end. The gradient vanishes very fast. So that problem is called as vanishing gradient. So someone here can ask, if sigmoid is problematic because it saturates, why not use ReLU? The problem with the ReLU is it's exploding gradient problem. That means it explodes so fast that a small error will also make impact on everything. So my RNN, if I change my activation function, I can use sigmoid, I can use tanh, I can use ReLU. Whichever way I go, either I will go with a vanishing gradient problem or I will go with the exploding gradient problem. Because length makes a hell lot of a difference. Because I need to capture the impact of if sigmoid is not, then I have to decide whether it is important or not. Irrespective of whether if makes an impact on sigmoid or sigmoid is making impact on is and is making impact or not, I am not checking the impact of individual word. I'm saying everything needs to be captured and then I have to make a decision. So length is a huge problem when I try to handle RNN. Make sense? So what is the solution? Why LSTM? Okay, let's dig little more deep. So when I was saying the impact is reducing, why I'm saying here is because if sigma becomes small, okay, what happens to dy by dx for small values? What is dy by dx of a constant? 0. if dy by dx is 0, it's not about word. See, the word sigmoid, or if it doesn't matter what is the length, it will first go through a embedding matrix. It will get one embedding vector. This will also go through embedding matrix. It will become a vector. Now, if this vector passes through sigmoid and gets a value v1, v hat 1, and this gets v hat 2. This value, when I'm going back from my gradient descent, if the value is small, the dy by dx will become 0. See, if you increase the weight also over here, at the end of the day, you are going to pass the sigmoid value. Read this as a hidden state. Read this as a hidden state. So when you are passing the sigma value on everything, over the period of time, if this value is small, if this itself is small, no matter whatever this value is, this will not make an impact because overall this value becomes small because of sigmoid. Now, when you take a derivative of a small value, it becomes, or a constant, it becomes 0. So this entire thing will become 0, irrespective of whatever the high value of wi or bias I can use, because this value is small. Why this is small? Because we are using sigmoid. Now, whatever the why it will become small? Because we are using sigmoid. Why sigmoid will make it small? Because I will have some value over here at sigmoid, then value will keep on decreasing, 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 decreasing. By the time I'll reach here, the value will become 0. So it will say no impact over here to here, or very weak impact from here onwards, because I'm applying all sigmoids till this part. So it will slowly reduce. Yes or no? Why it reduce? Mathematically, this is the reason. Now it says something LSTM will solve it. How does LSTM solve this problem? This is how LSTM is built. Watching it looks so beautiful, right? Lot of sigmas, as if the life was not complicated with H and X. Now you have C also present. We are having fun. So we have different values to it. So the first one here is I have an input. Okay. So this is going to be my input. This is hidden state. Okay. This is your cell state. Now what it is saying here is just ignore this block. You are passing hidden state, you are passing input state, you are passing cell state, and what you are generating here is again a hidden state and a cell state. So somewhere they are saying there is another box of LSTM which captures this information. This and this is an hidden state from the previous box, previous LSTM box, and this will get into the next LSTM box. So if you have 3 LSTMs put together, hidden state is getting like this. Cell state is also going like this. And inputs are going like this. First, understand this part. So now we have to see each block one by one. Okay. So we are aware of how RNN works. We are aware of RNN has any lot of problem. Now what we want to do here is we want to see how the LSTM helps us solving this problem. Okay. Now LSTM use gates. Okay. So there are gates which are used in order to solve the problem. So the different gates are used here. For example, a forget gate is used, then input gate is used, then output gate is used. So one by one, we will see all the gates. So this is my cell state. This is my hidden state. This is my input state, and this is what I'm generating the output. At this stage, this information is sufficient. Now we go to the next one. What is the cell structure? The cell structure here is I have input gate. Input gate will control the flow of information of the current input with the hidden state from the previous cell. Then you have forget gate. It helps you understand which information to keep, which one to forget. Then we have memory cell and we have output gate. One by one, we have to see all of them. So let me go through the flow. Okay. So let's keep it as it is and start. First, let's try to draw this one. Can we draw it? Because drawing helps in understanding what it is. So I am saying I am passing cell state, whatever it is, doesn't matter. And I am passing hidden state into a block. Okay. And I am passing an input xt. Now, this is what my hidden state is. My hidden state and my input state are matching over here. And then I go and do a sigmoid. My sigmoid then goes here and my cell state continues and I do a cross operation over here. So what I'm saying here is at this stage, I am saying sigmoid of xt w plus ht. Right? Something like this I'm saying. Shalom. Adding this also. This is something I'm saying. I add bias. I apply weight to the input and I take the hidden value. Okay. Now my hidden node also will have some weight. So can I rewrite this whole equation in a slightly different way? So can I rewrite this into I am applying sigma on hidden state, which is ht minus 1 and xt. So let's say this is t minus 1 and let's say both of them hidden state t and x has some weights. So this is what is happening over here. I will get some value at this stage. That is my value 1. Can I say this value is 1 over here? I should not say 1, I should say v1. Otherwise, you might think it is actually v1. What would be the range of v1? 0 to 1? Now, what I'm doing over here is I am passing this information forward. So at this stage, I am saying v1 cross function cell state. Correct? This is my cell value now. Now, if my value is 0, entire v1 will become 0 and entire cell value will become 0. So hidden state and input combined together with sigmoid can give me value as 0 or give me value as 1. If it gives me the value of 0, it says whatever information you're passing, it's very insignificant, forget it. If it is 1, it means, oh, it's very important, remember it. 0 means forget. 1 means remember. Make sense mathematically? I call this as forget gate. I keep it here so that you understand. So this is your forget gate. This part is clear till this part. I use this information to analyze. Still long journey to go. Now what is happening over here? I am saying, okay, take this input and also pass into my another sigmoid function and tan h function. Yes, some information is going to forget, some is going to remain there. And these two I am going to operation. Right? I'm taking input sigma, then tan h, and then I am making this operation. I'm just implementing this part. Now, what I'm saying here is, whatever is this my new information, I am passing my new information through sigma. And then I am going through the hidden state. And then I am applying this function. So this area can be represented as 2. How can I write it? I'll say, let me represent it as I of t. So I am saying sigma times W of I hidden state of t minus 1 times x of t is the input plus bias of I. This is going to be my IT. Then I have another function which is this one, C of t. C of t is nothing but doing a tan h rather than sigmoid. Now, this is what the math says. But what exactly we are trying to do? We are in this block using it as a input gate. This was my forget gate. Forget gate tells me whether I should remember information or not. Input gate signifies, is my new information important? And how do I decide that? Using these two operations. So what I do here is I use IT and CT and do a mathematical operation and then combine it with the cell state with a plus. Just look at it again, it will be a plus. Forget gate is clear. In input gate, we are applying 2 operations. So input gate is a flood gate which holds the information, whether the new information with the new word which we are passing is of significant value or not. Okay. So I apply sigmoid. Sigmoid is the function which tells us which value we update. Then we have tan h function. This creates a additional layer of vectors which we called as a new candidate value, is a term for it, CT, that can be added to the state. What we are trying to say here is, step 1 is I have a cell state which is coming from my previous state. Step 2 here is I take hidden state and I take input. I decide whether previous value is significant or not. Then I check whether my input value is significant or not. This is done using forget gate. This is done using input gate. So if I have a sentence, I need 2 things. One, whatever I have learned so far, is it important? Point 1. Second, what the new information has come, is it important? That is also there. So there is a possibility previous information is important. This is very important. And this is not important. It may also happen that this is not very much important, but this is very much important. Or it may happen both are not important. Anything is possible at this stage. But these are the information that I need to know. So what is happening here is I had previous cell state. I did a function over here with the forget gate. I got my value of this of forget gate times previous cell state. And then I have an additional function which analyzes my input gate plus forget gate times previous cell state. Now we are applying third function over here. What is that third function? That function is this one, sigma and tan h. Okay. So this is our third gate, which is basically my output gate. It controls the flow of information from the memory cell to the current state and memory cell. So I'll come to the output gate in a while. I'm just going through the slide so that you will get a revision kind of a thing so that before we proceed, you follow the flow. Clear? So first thing, what is it? We should know what there is a cell state, there is a hidden state, there is an input. Three things are there. Okay. Next is cell state. This is the power state, passes the previous cell information. The cell state is responsible for storing the long-term information over the sequence. You make sense out of it now? It is storing the information of my entire sequence. Then what is the first step? I will take the forget gate. What is my forget gate? F of t. What happens when I take my forget gate? So I take my forget gate, input gate, and output gate. So first I start with my forget gate. What is happening in forget gate? I take input, I take hidden value, I get my sigmoid, I get my output. So what are the points? Take the previous hidden state, output the value between 0 and 1, decide how much to forget from the previous state, how to erase or remember the information. This is what is happening in this one. This part is clear. Next is input gate. What happens in the input gate? An input gate, we again take the previous hidden states and the current input, and we decide how much current input is important. And how do I do it? I evaluate my I of t, I evaluate of C of t. What is my I of t? My I of t is sigmoid of input and hidden. What is my candidate t? It is of tan h of input and hidden. Then I multiply both of them and I add it with my previous cell value, which I have already understood using forget gate. Focus on the last line. How selective addition and deletion information to the cell state. This operation takes care of that part. So mathematically, this can do that, achieve that. Now is my output gate. Output gate is whatever information I have got so far. I have got my information till this part. So at this stage, I have my importance of cell state, importance of input, and importance of previous value. So these two I have. Previous state is important, previous value is important, and at this stage, I know that how much previous value was important, how much new input is important, and now I need to do the third step. Based on these two, how much should I pass to the next step? So it may happen that if we are building the block, and let's take a case where this value becomes 0. So this value becomes 0. Then what is the value at this stage? CT times IT. Only input is given value. It may also happen that this value is 0. So whatever this value is, it is all about forget gate. or it is combination of forget gate and input gate. All three cases are there. Case 1, only forget gate. Case 2, input gate. Third is forget gate plus input gate. Are you guys clear with three cases possibility? Now, whatever is my possibility, I want to know how much should I pass to the next step. I don't want to pass everything. So let's say I represent my OT as output state. So how do I represent it? I represent my output state as sigma times weight of, what are the inputs I'm passing? Hidden state -1 x of t plus bias, and then I have a function. This line, can you see this line? What is the value of this line? This line is next hidden state. So my next hidden state is what? Whatever is my output weight times tan h of cell state, right? So this becomes my hidden state. Whatever value I was passing through will become my cell state. So again, I am generating a hidden state out of it, cell state out of it. I'll pass this value with the input into the next LSTM. So mathematically, this is how it happens. To understand how the image is. Otherwise, it is okay. Okay, we'll repeat the flow. So what is happening here is, let's assume I have a data, one block here and one block here. Okay. Now this block is passing the information of my cell state CT. This is passing the hidden state HT. This is T-1, this is T-1. Now this information is going like this and into a LSTM box. This will pass this information here as CT. This will pass this information as HT. Now I have an input. I had an input of xt-1 for this. I had an input of xt over here. I have an input of xt plus 1 over here. Now when I pass my value of x of t, what I do here is I do a sigmoid. What will it do here is it will take the value of this. It will take the value of this. It will give me a function out there. I call that as an f of t. F of t is my forget gate. What I do here is I do a multiply over here. I pass this value. I multiply it with my previous CT-1 and I generate my output. Okay. If you are passing the value xt we converted into an embedding. This embedding will get finally will be converted with weights into embedding of your input under the sigmoid function with ht-1 into the weights, and then you will get the final sigmoid function. That's a detailed math. At this stage, we are just saying we are passing the forget gate into with the cell state and we are getting our final value. What is the value? This value is nothing but ft times ct-1. Forget gate tells me talks about previous value. Now I want to know what is my current value. So what I'll do here is I will again pass it to a sigmoid function. Okay. And I call it as input gate IT function. I also pass this value through a tan h function. This I'm calling as a CT. So what I do here is I do a multiplication of IT and CT. And then I pass that information with an addition function to my equation 1. This is my equation 2. What is the purpose of equation 2? Significance of input value. Now input value is sorted, previous value is sorted. What we are doing here is we are doing the third one. What is the third one? Output gate. What is the output gate? It says again pass this information. Okay. Now when you are passing this information, pass it through a sigmoid function. Once you are passing through the sigmoid function, you call it as an output gate. Take that output gate value. I'm just extending, let's say this is. So I'm taking the output value at a sigmoid, only at a sigmoid, and the hidden state, whatever I had over here. But this time I am doing a multiplication with a tanh of my cell state, whatever it is. Okay. And this will generate my new hidden state. This will generate my new hidden state. Cell state is anyways continued to come over here. So my new hidden state is what is important now based on whatever we have got from my input value and tanh function. My cell state input significance is coming from here. My forget gate will tell me. So this is my power line of CT, which will continue. Okay. So this line is which will finally give me cell state. And this line will give me hidden state. Two things I'm getting out of it. If I come over here and try to analyze, this is what I'm getting. I'm getting a cell hidden state. I'm getting a cell state. My cell state is output of my input gate and output forget gate. My hidden state is all about my output gate. My hidden state is all about my output gate. This state is all about my input and forget gate. This is where it helps us in fighting the long RNN's issue of vanishing gradient, because if you see mathematically, if someone is interested, this plus sign makes a difference. For example, all this value becomes 0. You still have some value coming from input. This value will exist. So if you have 2x plus 3, even if this value becomes 0, this value will exist. It will give at least some output. So the value does not diminishes because there is a plus sign. So when you take a derivative also, the constant will come out. Now, does it really look that horrible, or is it just okay? I mean, you can make it work. See, there are, for every LSTM block, what do I need? I need cell state and I need hidden state. And then there is an input, right? If I have to go to the next LSTM block, what do I need? I need cell state and I need hidden state and I need input at this stage. Okay, this is cell state, this is hidden state. C stands for cell, S stands for hidden. So cell state is carrying my all the information that I have, right? So let me repeat again the entire thing, just in case anyone is confused. I'll keep this diagram here open. Let's understand from here. So what is the first step? Forget gate. What happens in the forget gate? We will decide which bits of the cell state, that is the long-term memory of the network. This holds the memory of my previous information that I have, are useful for both the previous hidden state and the new data. So basically, in the first step, I am trying to understand which part of the memory is important. Once it is done, I have hidden state also used along with this. I try to capture what is important from the new input. I have analyzed my previous information. This I have analyzed how much it is important. Then I analyze how is my current information. Once I have analyzed my current information, then I want to know, based on my current and previous information, what part of this should be passed as an output. This output will become a hidden state. Cell state will continue as the memory of my entire thing, which has got affected due to the input. But still there will be something out because there is a plus sign, right? So there are multiple cases that can happen. My cell state was something. I passed this information, everything became 0. What will be my cell state now? Whatever is my input gate will become my cell state. Okay. So my first case was CT, this is 0. Whatever is coming over here, it will be my output. My okay, second case is, this is important. This is 1. 1 times CT is the entire cell state is important. The input state might not be important. So this is 0. So my current cell state, my cell state for my next cell is basically what was the previous plus the whatever was the previous. Okay, because this is just a value 1 or 0. So FT will only say multiply by 0.1 or multiply by 1 or multiply by 0.2, nothing else. So what portion of CT minus 1 should go will decide by this filter. So CT1 depends upon forget gate. Also depends upon what is the significance of input value. Whereas my HT depends upon my output gate. So clearly you understand the difference between hidden state and current cell state. Okay. So if I have all these values with me, what happens here is I have this is my LSTM block. This is also my LSTM block, and this is also my LSTM block. So each block will get a cell value, each will get a hidden value, and each will get a different XT. So whatever is my cell value depends upon my forget gate and input value. Whatever is my hidden state depends upon my output gate. And same value I'll forward, new input will come, cell value will get importance, hidden value will get go through the sigmoid function, and I'll generate new values. So the working is explained here. We have already finished it. I'll just go through again. This is my forget gate. Forget gate will apply this operation. It will give us the information, how much information is important. Then in step 2, we have CT and we have IT. So the next step is to decide what new information we are doing store in the cell state. This has 2 parts. First is sigmoid layer called as the input gate layer, which decides which value we will update. Next is tanh layer, which creates a vector of new candidate value that could be added to the state. Basically, in simple terms, IT into CT gives me a vector representation of input. IT into CT, IT times CT gives me the vector representation of my input. I am not directly using my input, I am vectorizing it. Okay. Step 3 is my output gate. What is happening in my output gate? I take my output gate is here, but what is happening meanwhile? I'm multiplying my forget gate with my CT minus 1. If forget gate is 0, everything will come 0, but still I will get IT into CT. So my cell state is getting, new cell state is getting captured here. How? My new vector representation of input plus how much is forget gate allowing me to pass my previous cell information. That becomes my new cell state. Right? Next is I am creating my output gate. This output gate becomes my hidden state. So I have got my cell state, which maintains the memory of the entire sequence. I have a hidden state, which implies the significance of my previous data, or what should I use it for my next input. So this is where my LSTM theory ends. LSTM is not great that it will solve all the problems. LSTM also have a lot of problems which get solved with the different architecture design. Okay.
Just a quick info guys, Intellipaat offers generative AI and prompt engineering course which will help you gain proficiency in creating generative AI chatbots and other Gen AI tools, along with mastering the latest tools and techniques with hands-on projects and real-world case studies. And the best part, this course will be taught to you by IIT faculty and the top 1% industry experts. What's more, you'll be getting your generative AI and prompt engineering certification from Microsoft. With this course, we have already helped thousands of professionals in successful career transitions. You can check out their testimonials on our Achievers channel, whose link is given in the description down below. Without a doubt, this course can set your careers to new heights. So visit the course page link given down in the description below and take your first step towards your journey as a Gen AI engineer.
Okay. So if you want to change, first is we will set the name. Now the name will get it as for 24. Now, if you want to connect, you can connect from here. But if you want to change the settings, if you want to use a different CPU, how do you do that? Are you aware of the notebook settings? In this, we can select the runtime, Python 3 or R. We can select our P4 or CPU or TPU version 2, whichever is available. We can use that. These are all for the paid versions. We are not using it. So in our case, we can use T4 GPU. It's okay. We don't have any GPU case, but still we can keep it running. So you can see connect to T4. If you have to build a basic classification system, how will you construct that classification system? The first step here is we load data set. So this is how my data set looks like. This is iris data set. Okay. Now, in order to build a classifier, I have to first create my X and Y, split the data, encode the values, and I can scale the data, right? So I will just identify my X and Y. So next step is I identify my X and Y. So this is how I'm identifying X and Y. I am also, yeah, this is how I identify my X and Y. After that, I don't actually need this thing, this step. This is an optional step because we don't need to label and code by Y as it makes okay. This is where we are doing the splitting, and this is where we are doing the standardization of our X. Once it is done, how do I build my classifier? I train the model. If I have to follow the ML techniques, what I'll do, I'll train the model. So let's say I'm using random forest from sklearn.ensemble import random forest classifier. Then I initiate my random forest classifier. Okay. So this step is I initiate my random forest classifier. Here I train my random forest classifier. Okay. So I am training the model here. My model is trained. What will I do? I will predict on my X test. And I save this value in my Y thread. Next thing is I have to see how good I am performing, right? So I can directly say RFC dot score. I will pass my so I'm mostly performing with 100% accuracy. If I have to do the same thing in Keras, how will I do it? So if I have to train the same thing in as an ANN, artificial neural network, how will I train this? I need to import first Keras models, sequential, dense is required in order to create layers. So how do I build it? And when I build it, do you understand the flow of construction for it? So the first step is I'll build with I will identify the critical values. What are my critical values? These are my critical values. Number of features are 4 in my data. 1, 2, 3, and 4. Yes? Oh. Target variable is 1, and categories of target variable are iris setosa, iris versicolor, iris virginica. Now, if I have to build my model, does this information create a role? Does this information play a role? Right? So what is the role does it play? Does it help me identify what should be the input side, what should be my output side, number of input nodes? So what is the first step here is I will initiate my model. How do I initiate my model? I'm calling model.sequential. Step 2 is I will add first row record. Okay. So basically I am adding a layer to it, not a row, I will say layer to it. Right? So how do I do it? I will directly use the term add. And when I'm doing add, I use the syntax of dense. In that, I have to define my, okay, everything came automatically. I don't need to, I'll just use it and I'll make changes to it. I have to write my input dimensions. I have to write my activation function, and there are other things which I can mention. So when I'm writing it, I am using 10 nodes, but I am saying I have to define my input shape as well. So what I'm doing here is I'm defining my first layer of model, that is input nodes will be 4. Hidden nodes will be then activation function will be if I want, I can use a different activation function also. Yes. So what we are doing here is we are saying my input is 4, but when I am going to the hidden layer, I am using n nodes. Let's say this is 1 and this is 10. And the activation function that it takes here is ReLU. Make sense? Now I say I want to add another layer to it. So I can add another layer to it. So what would be my next layer? I will again do model.add with dense. In dense, I have to define, I don't need to define my input layer because I already know my input is 10. Now, whatever I define is my output. Correct? So I can define my output layers, how many I want. Mostly people say you can reduce it by half. So in my first node of ANN, I have 4, then I have 10, and then I have 5. So I have 4. The next layer I am going with 10, and then I have 5. Now I want output. How many I should have in my output layer? Three. Why 3? Because I have 3 times in my output. So I should be having 3. So what I will do here is I have created my second layer. I will create my third layer. So what I will do here is I will have my output layer. Now, when I am defining my output layer, what should be my activation function? Softmax. The reason of softmax is because I have more than 2 categories which I want to identify. If I had less than 2 categories, I could have gone with sigmoid also. Just want to check what happens if I write this. So if you do model.summary, you will see what are the parameters and the dimensions which are there. Okay. Next step is this is how you build the model. Input output numbers can give any numbers. See, input this 4 comes from number of features. Let me just draw it for you. This 4 is coming from here. This I can assume. This I can assume. This is entirely depends upon. I usually what we do here is we half whatever is the work, we half it. This again can be either sigmoid, tanh, whatever you want. This completely depends upon and it is fixed on what is just this depends upon what is going to be my output. So softmax is because I have 3 classes. If I had 2 classes, I would have gone with. So 2 you can keep if you want to do binary. So if binary was there, I would have used sigmoid. I can still use softmax, but sigmoid can also work. This entirely depends on this value. Now, if this part is clear, what we have done so far is we have the data. And once you have the data, you can train model. Now, this model can be your ML model. This model can be deep learning model. But after you have done it, you have to, so training the model is you have to initiate and then you have to train. So whatever we have done here is actually is equivalent to this step. The step we did in the random forest classifier initialization with the parameter is actually equivalent to all these steps. Are you able to correlate between map between what is happening in machine learning, what is happening in deep learning? Now we have not given weight here. We can give weights initialization also. We can define our weight initialization as that is one of the parameters. We can also add dropout layer. Okay, we can also do batch normalization. We can do all those things if needed. Okay. One more reason we do batch normalization here is because when you see the neural network, so this performs action onto my next neural network and then reverse is also happening. So at any given time, this model is undergoing training. So if the data weights, if the data point, whatever it is, and the weights are not normalized, that means their standard deviation does not come within the range of 1, the volatility of training increases. So when the volatility of the training increases, it impacts your compile optimizer. That means if you're using Adam or if you are using AdaGrad or whichever you want to use SGD. So all those things get impacted because the data is not within the standard deviation of 1. Too much of learning, unlearning happens at every node level. And the impact of this can significantly different from this to this as compared to from this to this. In order to manage all those things, what we do here is we try to apply batch normalization where we try to target the volatility of the data. Okay, so how does your you understand the step? What is the purpose of scaling? You have two things that works. One is scaling. Other is transformation. Correct? What does scaling do? What does transformation do? If you understand that part, you will realize that they are actually similar to batch normalization. The only difference is they work on the data, batch normalization work on weights. What does scaling do? What does transformation? If I have a data point in my machine learning, and I think the data is not in normal distribution. For example, my data is 2, 4, 16, 9, like this. So what can I do? I can transform it by taking square root. So it will become square root of 2, it will become square root of 4, that is 2, square root of 16 is 4, and this is 3. So this will become normalized. This is what you do in the transformation. In scaling, you do standard scaling or you do min-max scaling. Standard scaling, min-max scaling. Standard scaling is nothing but your z-score. Min-max scaling is take the maximum value, subtract it, minimum minus max, something like that. Now, what happens over here? If you have a data point, In z-score, what do? You try to bring the mean to 0 and standard deviation to 1. Z-score is done when the data is already in normal distribution. That means, let's say I have in data in pre-processing, I have two functions that I can. I can standardize my data. I can, which is basically scaling of data, and I can normalize the data. This works when I evaluate the distribution of my data. So how do I get my distribution of my data? I can do SNS discount, or I can do SNS pair. If I do them, I understand my data can be like this, or my data can be like this, or my data can be like this. These are both skewed data. So in order to make them work, what I do, I take these data points and I apply some additional function. What are those functions? I can do log, I can do square root, I can do anything in box family, which comes from a scalar. Now, when I do this, my anticipation here is that all of this skewed data will become normal data. Okay. But if I have a normal data, the normal data may not be in a same scale. Scale might be pretty big between two different columns. Yes or no? For example, I have age and I have salary. Is it necessary that age and salary will be same scale? Age can range between 24 to 54. Salary can be 100K to 150K. Definitely not in the same scale. Yes or no? But individually, they can be normally distributed. So what we do in this case is we try to standardize it. Now, some people ask, some learner ask, how do I realize when should I standardize? It's visible. Scale is not same. You are talking 2-digit versus 6-digit. If not, think of if you are plotting age and salary. See, age is 20, ranging from, let's say, lowest is 0.20 to, let's say, 54. But let's say if I have to put everything together. So what I do here is I use the lowest of the age and highest of my salary. If I have more features, then whatever is my salary, that will decide the direction of my overall point. You apply standard scalar when you see there is a scaling issue within the features. Okay, so when you apply, what happens? Let's say you have this normal distributed. Let's say the mean is 9. Standard deviation, let's say this is 2. Now, if I have to create a z-scale, what will I say? This will become what? New mean minus old mean divided by standard deviation. This will become 0. What is this one? New mean minus old mean divided by standard deviation. This will become 1. This is new mean minus old mean divided by standard deviation. This will become -1, -2. If you observe your mean is reaching to 0, if you are applying z-scale on this data, and your standard deviation is closing towards 1. So your standard deviation is static, your mean is tending to 0. So when you want to train you know that my data points are not volatile. They are having fixed standard deviation. Same concept gets expanded when you are doing batch normalization. So when you are doing batch normalization, you have a weight matrix. Now, weight matrix will vary at every single node. Now, you want it to run in such a way that even if it is different, the standard deviation of the weight when multiplied. See what happens at this step. You have input and you have hidden your. Now, at this stage, you are multiplying by this, and you are generating an output. Now, when you are generating your y, what is happening? This is your input 1. So your y will be the weight of assigned word into input I plus weight of 2 input 2 plus weight of 3 input 3 plus bias. Now, when you are multiplying with different weights, it becomes very important that what should be my initial weight. And if my weight has to vary, why weight has to vary? Because back propagation is happening. The weights are getting updated. That is what the purpose of back propagation is. That's what we discussed. Then when they vary and I again start the second epoch, when I'm doing this multiplication, I do it at this node, then I do it at this node, then I do it at this node, and this information goes carry forward. In order to keep my training less volatile, I do batch normalization, which is nothing but something we understand here. Trying to bring your mean to 0 and standard deviation. Make sense? So when you have to initialize your weight, you can write the syntax. When you have to use a dropout, you can write the syntax. I think the syntax there is model.add, and then you write the dropout and define the percentage. Something like this is the syntax, right? This is how you add a dropout. All right. Now, the next step here is we have to compile the code. We have created the model. We have to now train the model. So while training the model, we will use this step. In this step, we use whatever model we have trained. We use compile for it. Then we define which optimizer we have to use. We can use SGD, Atom, all different compilers or optimizers are there. We can use them. Then there is a loss function that we define. So what is a loss function? Categorical cross entropy. Why we are using categorical cross entropy? Because we have a classification model. First, second, we have 3 categories. If I would have 2 categories, I would have probably used binary classifier loss function. Matrix is accuracy. Okay. When we do this, we create an object for the model where my optimization for back propagation is going to be Atom. This is going to be my loss function to calculate gradient descent, and this is the metric I have to use to calculate the gradient descent. This is theoretical part of how train the model works. Now what we do here is we fit the model. So how does the fit the model works? I'll just copy this one and explain the steps. In this step, we take the model, we use the fit method, we give the X train, Y train the way we have given in our previous method. But the only thing we do here is we give the number of epochs. Epochs is how many times this iteration has to run. I don't need 50 times, I can do it in 10 times also, because it's only for the learning. Batch size is what should be the batch size for every iteration when it runs. So I'm keeping it 5. Validation split, I'm keeping 0.2 to create my train and test data. Okay, so I run this step, it will start. You can keep your verbose as true, false in order to see the results. You can see what is your validation loss. It should keep decreasing. Your accuracy should increase. So this helps you understand if you're going in a right direction or not. So this is my model.compile method. Then we run our accuracy. Exactly same the way we have run our accuracy in our model evaluation. Model evaluation remains same. You want to run the model.evaluate in ANN. We do metric.accuracy in our random forest, or we did model.score in our random forest. So both are basically evaluation criteria. So this helps us doing model evaluation. Once we have model evaluation, we can do the prediction also. The same way we have done the prediction in our random forest case, we can do the prediction here as well. So this is for prediction. So my predictions all are correct. I was supposed to identify Iris virginica and I made a wrong mistake. I did a versicolor. Setosa, virginica, versicolor, virginica, versicolor. So with virginica, I am observing that I am identifying it as a versicolor. That's my observation. You want, you can build confusion matrix also the way we have done it in your random forest. This is a basic classification model. So the same data can be used. We can do this classification using machine learning. We can do it using AI. So it is basically from versicolor to 0, from 0 to versicolor. This is the inverse step. Not needed. These are just the fancy syntax which can help you in the writing assignments and other codes. Consider them to be the standard syntax of using things. On the similar lines, we can do the same thing for LSTM also. If I have to do, I can do the same thing using LSTM. I'll first show a very simple. See, what we are doing here is we are first taking the data, implement a random forest on that data. Then we are using Keras and we are using artificial neural network logic and we are building the ANN based model. Then same data we will be using LSTM. So the idea here is we will create a map between machine learning, ANN and LSTM to build our classifier. So what we will do here is I'll just take the steps and I'll show you. So in LSTM, first we have to load LSTM. Okay. So far we have not load LSTM, we have load dense and other variables, but then second step is all same. We are creating the model. We are initializing the model. Is this step same as our previous ANN? In my ANN, I was writing model.add and then I was using dense. But in this case, I will not use dense. I will use the block, LSTM block. So it is not my ANN, it is my LSTM block. So in my LSTM block, I am passing the input information. Input shape equal to 4, 1. That means I have 4 features, 1 target variable. 50 units of LSTMs are needed for building the model. Now, once the LSTM layer is come, we create our output layer. My output layer is same as what it was in My output layer is same as what it was in my Keras. If you observe, I have model.add, dense is 3. Whenever you use the word dense, what does it mean? Dense means fully connected layer. When all the nodes of the previous are connected to the next layer of nodes, we call that as a dense layer, fully connected layer. If you have observed in your VGG, you have learned CNN. In CNN, you have seen the fully connected layer in the end. Once you have created your convolution, you pass the output as a flat output, and then you give it to the last layer, fully connected layer. That is where you would have used dense again. The dense means it is a fully connected. Okay. Now, once we have done this, we have to apply the compile. Again, it is the same compile that we have. So basically, the only difference between ANN and LSTM is this step. So if I run this step, I can actually follow all the steps which we have done before, and I can generate the result. The reason here is of doing this method is to make you understand the structural difference between LSTM and Keras is not strikingly different. It is something you have already done if you have learned, understood Keras. Now your accuracy will be different because you are using LSTM as compared to basic ANN. So we can check our accuracy here. So earlier my accuracy was 80%, now it is 100%. Now, if you are training accuracy, so there is something called as a training accuracy and there is something called as a testing accuracy. All this while we are just checking the testing accuracy. So we already have this model, right? So if I do RFC, okay, dot 4, okay, I will just do one. Whatever is this model, I will replicate this step. Can I do it for X train and Y train? Now it says fine training accuracy is 96.67%. And my testing accuracy is 100%. What does this mean? So is it overfitting or is it not an overfitting? What is the meaning of training accuracy and testing accuracy? Now you have a data. Okay, everyone please pay attention. Okay, you have a data. You have split that data into 2 sections. This is your training data. This is your testing. This data is used to build the model. Okay, everyone, please pay attention. Now, when the model is going to get built based on training data, what is the process? But in a very layman terms, not in a technical terms. That means while building the model is trying to create an equation. Correct? In order to build this, model will predict or evaluate and say these are the values. Now, if you think the underlying process here is model is making assumptions. That I think this is important, this is less important. This is very important. and this is less important. These are all features. While building the model is making assumptions. Now, if I go and check those assumptions on unseen data, there are two things that can happen. One, whatever assumption I made was correct. Second, the assumptions that I made to build the model were not correct. If model, when built on the training data based on this assumption, if I check its score, and it says that if I use the same model to predict the same scene data, it gives me 100% accuracy. That means the model has made tons of assumption in order to give the result. Okay. So if you see the cricket, when team loses a match, the analysts who are present in that room, who are giving their verdict, they have every answer to the problem. They can explain everything why they lost the match. And then they take assumptions. The recent one is Babar Azam did match fixing, that is why Pakistan is out. That is not what Indian media is saying, that is their media saying. Have you heard this statement? Now that is called as assumption. Okay. Now, can you use the same? Okay. Yeah, ink, Bob, see the king. So in that case, can I use the same assumption and apply it on something which is going to happen next, that is Champions Trophy, which will happen in next 1.5 years? If it works fine, then that assumption has merit. If this does not work fine, it doesn't have any merit. Similarly, if you see the election result, everyone projected X number of seats. And it is not the first time. Every time some election guy will come and say, I am predicting XYZ seats. On a result day, it may happen, it may not happen. Yes, it may happen, it may not happen. Exit poll may go right, or opinion poll may go right and wrong. Now, if I do a post analysis, I can explain all the reasons why it went right or right. The point here is the model is overfitting if it tries to justify all the patterns on the training data. Are you getting the point? So if I have a data, I have created a training data, I have created a testing data. Testing data, I don't know. For example, in my data, I have a category called as age. Now, it's possible that while in training data, I have taken the value of age groups of between 20 to 40. In my testing data, I get data between 40 to 60. What will I do now? I never trained my model, but my model would have made some assumptions. It would have got a couple of data points from it. Now, when it takes the assumption in the testing data, it may go horribly wrong. Or it can go wrong, or it will be right. Now, based on that, I decide whether it is overfitting or not. If the model gives good accuracy on the training data and bad accuracy on the testing data, that means the assumptions were way too far-fetched. Yes or no? Right? So, this case where training data has high accuracy and testing data gets low accuracy, this case is called as overfitting. Now, what is the difference, it depends upon your business owner. I usually consider 5% as a huge threshold. So if I have 100% over here, if I hit less than 95%, I call it overfitting. But there is a possibility. Possibility is in my training data, my accuracy can be 100. In testing, my accuracy is 95. This is 95 and this is, okay, this is 90 and this is 95. And then there is 80 and 80. Now, this is my case 1, this is my case 2, case 3. Out of which, if you have 3 models, which one will you pick? Case 1 is overfitting, ruled out. What is case 2? Case 2 is like my Hardik Pandey. Okay. Or case 2 is like internally the model doesn't know what the working is, but externally somehow it is very lucky to predict everything right. Will I use this model in a banking system and predict a value? Will you be confident enough to test a model used in production where when I show him all the data, it did not learn anything, or it learned at only at a 90% rate, but suddenly on the testing data, everything was right. So testing accuracy does not make the case all the time. It has to look from a holistic viewpoint. So in our case, I know it is 80-80. That means if I am in a stock market and I know my scale of accuracy is 80%, I will reduce the size of my bets on the stocks in such a way because I know it will be only 80% time correct. I should not be looking at the big value. Does it make sense? And then definitely there is precision because which is a critical thing in designing models. But the term which you use, overfitting, has to be explained in this way. The second case is called as underfitting. That means you are not confident enough on the model. Now, you are asking how does it possible that the case 2 may happen? Okay. What is happening in the case 2 here is the patterns that is present in the training data are not explicitly clear in learning the model. But let's say the model has learned. Now, model has learned different type of patterns, and accidentally, the testing data was all about those patterns which the model learned. Right? Let's say the model was about predicting the behavior of people based on their age and spending. Now, I have the people ranging between, let's say, I have people ranging between for age 20 to 80, and the salary or the income is also from 20 to 100K. And accidentally, there are different patterns which I found. One is low salary, low age, high salary, high age, low salary, high age, high salary, low age. And let's say model is only good with this one and rest of the patterns it is not predicting well. That is why accuracy, let's say, is 70% in training. But in testing, all the data points came from this cluster just as a fluke, and accuracy became 100%. So in your training, your accuracy is 70, but testing the accuracy is 100. Make sense? How it will work? Yeah, so these are the challenge as a machine learning engineer you will face. That is why we use cross validation. That is why we use other techniques in order to be sure whether the model is right or wrong. Let's learn how we can build complex LSTMs. So I've just created one file. Okay, so there is a difference between RNN and LSTM. RNN is a single recurrent gate which keeps taking the input at different times. Whereas in LSTM, we have multiple gates which try to manage what is the important information that I should be taking. Now, what we have seen so far in the LSTM here is I have just used a default block. That means I'm using LSTMs in one layer and I'm not passing that information ahead. So within my one layer of LSTMs, I'm having X number of LSTM cells or nodes. So that was a default function that we used. But if you observe, we have hidden state, we have cell state that is also required as an information, and we will see those things getting covered now in next steps. So some of the theory part I have again tried to capture here, show how my cell state is, how my forget state is, how the important memory mapping is done here. Now, coming to the basic structure of how it can be implemented. So I will just, so now we will be using a random data sample. So let's say this is the data that we have created, a generic time series data. A data which is in a series where events are happening based on the instant of the time. Okay. So the data in the May will depend upon what happened in the April, or there is some insights that my previous data brings into the picture. Let's say this is a stock price that we have randomly created. So how does it look like? This looks like this data set, a series of data points of 100 data points. Okay. Now this is how my data set is. Now the first thing in doing LSTM project here is we have to curate the data set in such a way it can be consumed by LSTM. Okay. Why I'm saying this? We are passing the information. We want something as an, or do you want your input sequence to be of a some length, like you pass 4 inputs and then you get an output. Then you pass another 4 and then it's next an output. So if this is my data point, how do you want it to be? That's an important question. For example, in my LSTM 1, what should be my input? If I say 1, 2, 3, 4, pass this input, okay, and whatever this input will generate, let's say it generates 1.87. I have to compare this 1.87 with what exactly this was supposed to be. So then I will be comparing 187 versus 1.656. Now, this is where my error is calculated, and error helps me in learning. Now, how do I do this? Okay. There are two ways in which it can be done. One is I can follow the method of what we have done in our time series. How do you do in time series? You have time series data. You put into an order. You say this is going to be my first half, is my training. This is my testing. I will pass this data sequentially and I will generate this data. And then I'll compare this data with the real data. This is my predicted data. This is how time series works. Is there any other way of time series can be evaluated? Can time series be think through as a regression case? What if I have to think it this entire data as a regression case? What if I say, let's create 4 points. This is 0.88. This is 0.40. This is 0.88. And this is 1.61. And this becomes my target value. What is it? 1.65. My second record would be starting from here. 0.40, 0.88, 1.6, 1.65, and this is my target variable. What is 0.35? Similarly, I can create entire data set by converting into a table like this. And once I create this one, this becomes x1, x2, x3, x4. And this is my target variable. It is actually, I am handling LSTM as a regression. Whatever I will use this, I will predict another value, and that value will get compared with this one. The only thing different between a regression and a normal linear regression and LSTM regression is LSTM regression considers them to be followed in a sequence. First this will go, then this will go, then this will go, then this will go, and finally I will get my output, and that output will be complete analysis. Is it making sense? So I am converting it into a regression box. And I can very well do that. Right? I can very well do that. So what I'm doing here is I'm creating a sequence. And sequence, rather than 4, I'm keeping a 10. I'm creating a function. This function will help me generate me my sequence. So I will just create a data frame to show you how it looks like. So whatever I've created, rather than 4, what I showed you was what happens if I use till 4. When I use till 4, then these were my x1 to x4, and this was my target variable. But in real time, I'm using 9 sequences. If you want, you can use 7 sequence, 8 sequence. Deciding the number of sequence can be a little tricky, but with some experience and domain knowledge, you can understand. For example, if it is a stock market data, so what could be your sequences? I would say we will take the sequence of, let's say, 7 days, because Monday to Friday we will take the data and then we will try to predict the 5th day. Or somebody who is working in a stock market will say actually the point of inflection come after 18 days, not 7 days on it. So my sequence will be of 18 days. But whatever is that, I also need to understand the limitation of having large sequences like 18, 20, like this. So whatever is the sequence, the easiest one is take 7 days and then predict. Right? So getting your sequence is in your hand. It has nothing to do with LSTM. Once you decide what should be the input to your LSTM, you can pass that input to LSTM. In this case, what we have done here is we have created the data frame like this. Isn't model which maintains the state and takes care of the previous data? If you have you are aware of stock market. So if you want to predict the value on day T, what values you want in order to predict it? Case 1, if my day T, that is, I want to predict what is going to be the value of my stock on Monday morning tomorrow. Do I need last 5 days data? Do I need last 7 days data? What do I need? Or do I need the entire quarter data? It depends upon what? Does it depend upon model or it depends upon your business? Do you want information depends upon your model, or is this information depends upon business, or it depends upon model? Between model and business, who decides the nature of the data distribution? In this case, is it model which decides the structure of the business, or is it the business which decides the structure of the data? Who decides the structure of the data? Last 5 days, last 7 days, or last 5 Mondays? So if I have to predict on Monday, should I predict last 5 Mondays? So it is a business which decides how the structure should be. So model has nothing to do with it. Once you have created the data set, you can use the same predicting in GBM. You can do the same in ANN. You can do the same in LSTM. When I'm doing LSTM, the only thing here is it works better as compared to the others if the data in itself is suitable for time series. If the data is not suitable for time series, LSTM will work, but it will work as good as GBM or ANN. If the order is important and I try these three models, this will work better as compared to these two. Data mining helps get more information, yes, but how do you decide? I mean, how does it change LSTM? My question here is, does that make an impact on your LSTM? If you want 9, 6, 4, which data you want, that does not impact. LSTM is an algorithm which you are going to use once you have created the data set. Yes, right? So the first job here is to create a data set. Once we have created the data set, we can use LSTM. So data set is created. Once the data set is created, this is my target variable. Now my overall data is created. I have a target variable. Everyone is able to understand. I start from 0.88 to 0.95. If you will see, this is everything is shifted by 1. So similarly, we will create the entire data set. So what we can do here is we can say data dot shape. So my data has been reduced to 90 cross 11. Okay. Next, we are doing scaling of the data straightforward. We have reshaped the data and now my data is ready to be used for my LSTM. Okay. Now, what are we doing in this step? Please pay attention. This is, we are defining the model. This model is basically a Keras model. So what I'm saying here is create a structure for a neural net. Then what we are saying here is create an LSTM layer, which has approximately 50 units. We are going to pass the input to it. And what is going to be my input? My input is going to be my sequence length and 1. What is my input shape here? My input shape will be sequence length and 1. My sequence length will be number of inputs that I am passing. I am passing. These are what I am passing. From 0 to 9, I am passing as input. That is 10. So 10 values I am going to pass. This is nothing. Sequence length is nothing but my number of columns. So based on that, what we are doing here is we are passing the number of columns or basically the input shape of my data as my input shape. One thing which is different here is I'm keeping my return sequence as true. What does it mean here is I have created a model. I'm going to pass my input. My input will go through the series of LSTM inputs and the return has to be true. That means think of it in this. And the input is coming here. That means my hidden state, my cell state is going from one layer to the other layer in a sequential fashion. And then I will generate my output. Now I am having one layer. This is my first layer. This is my second layer. This is my second layer. This is my third layer where I am not passing my output. That means whatever I am passing it, I am sending it to one node. Dense means fully connected. And this is my output. So basically, I will be passing my series of sequence I will be passing my 10 sequence iteratively. I will be generating a value through this. This is the output will come, a 10th value. This I am going to compare with my actual value. True sequence says share your hidden state and cell state. So hidden state and cell state should be said. So this is how basic LSTM will work. So I will create the model, I will create the layers, and the final layer will not have any output. I am going to pass that return sequence is not needed. I'm going to use directly the dense as 1 because it is a mean square error loss. That means it's a regression scenario. If it was a classification, I would have given 3 if it was like iris taste. And this would have become categorical loss function. This would have been Adam itself. Next step is again, you fit the model and reuse the model. So I run this step and I run this step. LSTM is widely used in forecasting also because it is sequential in nature. When I say forecasting, I don't say stock market prediction. People usually equate forecasting is same as stock market prediction. No, stock market prediction is not same as forecasting. Forecasting is different. Stock market prediction is different. Stock market prediction can and cannot be done using forecasting. Weather type prediction, you can do it. Sequence is 10. See, it is not about big sequence. It is not about small sequence. It is about how does LSTM work. Whether the sequence is big or not is not we are concerned. We are only concerned if we understand the syntax of LSTM because it is important. It can be little complex. It is not something which all of us will be able to grasp very easily. It can be slightly confusing. So the idea here of this exercise is to get comfortable with the syntax of LSTM. Whether we should use it or not is a secondary question. It depends upon the distribution of data also, right? How the data is spread out. Okay, now next step is we can do the prediction and we will get our results. So if we have to do the prediction, this is how our data will look like. A very bad signal, orange is what is predicted, blue is what is the real one. Okay. So this is the basic how LSTM works. Now LSTM has further flavors too. What we learned so far was basic LSTM. In the next classes, or maybe in this class, we will see, we will learn that LSTM can be bi-directional in nature. That means if there is an LSTM, we will have another layer of LSTM, which is in reverse direction. And here I will get the outputs. That means if I'm writing a sentence, this case should be given to general. Now, if I have to predict what should be the next word for general. So general can be General Motors. General can be Army General. General can be general theory of relativity. General can be a normal term. What we understand from our analysis here is if I have to predict a term, it is not what is before this. It also should be knowing what comes after this to understand the context. This was something which was not done before LSTMs. So what LSTM says is first read the sentence in this way, then read the sentence in this way, and then try to find out what exactly is the weight of individual or what is the value of individual token. So what I was teaching over here is that if you read the data in both the direction, it is called as bidirectional LSTM. If you have understood LSTM, then you have to understand from a context that if input is given, if I have passing 10 sequences, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't generate output here. I will generate output. First, I read it in this way. Then I read it in this way. I will add all the points and I will get my final output. Bidirectional means back propagation? No. Bidirectional means when I'm reading from this part, I am creating my hidden states. Okay, I'll just show you. You have these inputs. You are passing these inputs to A. This is LSTM2, LSTM3, LSTM4, and we are creating one state. I'm passing my SO in this. At this stage, this input, I am also passing information in the reverse fashion. So at any given stage, I have two hidden states. Hidden state when I'm going in this direction, hidden state when I'm coming from this direction. And I am capturing both the hidden states. Vector direction is important. H1 having this direction, H1 having this direction. So at this stage, when I reach here, at this stage, when I reach here, I just don't have information at this value. I also have information what is of this input and this input, what is it impacting on the rest of the cases. So bidirectional LSTM says you read the sentence from left to right and from right to left and then make assessment on what is important. Let's say I have a sentence. The animal wants to cross the bridge, but it is too. If I use my X as heavy, obese, or tired, that means I am referring, it is getting referred to what? It can be referred to animal, it can be referred to bridge. It depends upon what on the X, whether it is animal or it is bridge. Are we clear to this part? If I write this sentence, the animal wants to cross the bridge, but it is too tired. That means the animal is tired to cross the bridge. If it is tired, it is going to be animal. But if I say my X is narrow, then animal cannot be narrow. That means my it in this case will be bridge. Right? Now, my it depends upon this value, yes or no? So what is happening? What are we trying to do? We are trying to say the animal wants to cross the bridge, blah, blah, blah. The animal wants to cross the bridge like this. And I want to see whether if I'm using it and my animal and my bridge. Let's say these are the points I have. If I see the impact, my this value can be highlighted or my this value will be highlighted depending upon what it signifies. So let's say this was tired. So my this value will be highlighted. If I have a sentence like this and I want to identify which word is related with which word, how do I do that? I have to find out a correlation of each word within the sentence. Guys, if you have a sentence has words. Okay, let's say it has 10 words. Now, in those 10 words, some would be noun, some would be adjective, some would be adverb, some would be pronoun. If you want to identify which pronoun is pointing to which noun, to understand the context, you should be able to read the sentence. Yes. We should be able to read all the sentence in a order in order to understand the context, yes or no? Now, when I say which pronoun is to which noun, that means which word, W1 is associated with which word out of 2 to 10. Word 2 is associated with which word between rest of the words. This is the relationship if I understand, then only I understand the context. In order to understand my entire sentence, if I read in one direction, from a systems point of view, where I am just predicting the next word based on the previous word, is insufficient. But if I read it in both the directions, then I have more data in order to predict my next word or to understand my next word. This concept of reading the data in both directions is called as bidirectional. Because see, the relation is basically parts of speech. So in order to predict the next word, I should be able to read this and should be able to read in this direction. For example, you have built a model and your model says either it should be tired or it should be animal or it should be bridge. Now you want to run it in both the ways with animal as well as bridge. How will you understand which one is doing better if you read it completely? If you have just predicted it to be animal and not coming back to see whether it makes sense or not, how will you be sure whether animal was the right choice? So if I'm writing a sentence and there is a word general, can I predict general based on what is mentioned over here? Or I also need to know if it is General Motors, then it is a noun. If it is general theory of relativity, then it is not a noun, it would be something else. It would be a noun, but not a personal noun. If it is General Bipin Rawat, it is a name. So this word general depends upon what is present over here as much as what is present over here. So the information that I have to generate for this word will depends upon this value as well as this value. And that can be achieved using bidirectional. So, make sense? Now I would like to show you how we will be developing next code. This was one of the important concepts I thought I should share it with you. because the transformer is based on this logic, especially the BERT. You have heard of the term BERT? You know the full form? Bidirectional encoder representation from transformer. It is bidirectional. That was what it makes. There is a separate term called as encoder. We will discuss this also. But let's today only limit ourselves to discuss the code which is given to us. What I have discussed so far here is I can handle our time series data in two possible ways. Right? We did a one flavor of it using a regression technique. So in this case, what we are doing here is LSTM also offers us additional concept called as attention mechanism. It is the attention mechanism which becomes the keystone factor in deciding why transformers are different from LSTM. Okay. So we are using this API in order to get our financial data. So what we are doing here is we are using the data of Apple. We are taking the last 1 month of data of Apple using this information. We will use this API, Yahoo Picker, in order to get our data of Apple from day 1 to day 100. We will split that data into training testing. We will take the training data, we will build the LSTM model, and then we will predict the value. Once we predict the value, we will compare it with the actual value and we'll see how close or far we are with the data. Okay. So if I have to convert my data, what exactly we are getting here is we are taking the data on a date wise. We are capturing the open, high, lows, close, and value data. This is basically data only for one stock, that is Apple, not for anyone else. Okay. So if I have to visualize it, this is how my Apple stock has traded from July 23 to May 2024. Now, what we want to do here is we will take the data set. We will say, let's say till this part is my training data. I am going to predict this value. Now this value can be like this, or this value is exactly on the blue line. So if it is on the red line, the difference between blue and red is my error. The idea here is to predict this red line. That is the use case. Okay. The more I can overlap on my blue line, the better my model will be considered. Are we clear with the final objective of the data set? So what we are doing here is, okay. So now we are capturing the information on the volume on the assets sold, which is nothing but this is basically the EDA we are doing. I'll show you the EDA steps once I will finish building the model. So coming to the step 7 directly, what do we do? I'm just continuing from where I left over here. Okay. We have a training data and here we want to test our testing data and see how accurate my model is. That means I want to see if my model is predicting something like this, that means this is the error that I am making. Or if my model actually predicts like this, nothing like that. This is what my agenda is. Okay. Now, leaving all the details aside for a while, and let's go to the step 7. So what we are doing here is we have to first create the data set. We have already created it. This is the data set that we are creating. We are taking the start date as the 1st Jan 2014 and date now is the end date, that is today's date. So we have a data which is pretty big. So what will be the size of the data if I have to put? Two 635. I have trades of 2635 days. Out of all the information that I have, I need only one information, that is the close date. Or if you are not aware of it, then just understand that if you want to ever analyze the stock data, what we try to do here is where the value closed on the previous day. So if I have to predict my value of my 3, I would say it closed on 19.75. It may would have done a lot of transaction in between, but where it closed at 19.75, it closed at 19.32. So if I can predict on this day, it will close at 19.42. That means it's slightly up, buy. If it is down, sell or hold or whatever. Are you clear? So we will be capturing only the closed data. So we will be getting a series of data for only column close. And that's what we want to predict. We always take on the closed data. Okay. This one is similar to that. The time span is changed. Now we will be creating a separate data frame that only for closed column that we have done. So I have my closed data set created. Now I have to split my 2635 records into two sets. One training, one testing. So what I'm saying here is let's capture 95% of the data in the training and remaining 5% of data in my testing. I got my data from Yahoo Ticker. I took that Yahoo Ticker API. I got my data from 2014 to this date, that is 2635 record. I filter the data on the close column because I want to predict the close price of the Apple next Monday. Now I split the data into two parts. 95% is my training, 5% is my testing. Are we good till this part? Got it, right? This is what we have done so far. The rest of the things I'm not touching because they are not going to contribute to my model building. They are just EDA activities. So I will discuss them maybe later. Next is I am standardizing my data. I am doing min-max scaling. I am fitting my data into my scaled data. And I have got my data scaled. Okay. Now the problem in this case will come if I have the data points. And I scale them into 0.16, 0.24, like that. So my predicted value will be something like 0.81, let's say. Then I have to find what is an equivalent value of it. Because I'm predicting on the scaled values. So usually I recommend don't do it. Unless very much needed. This is not the step I recommend. Okay. Don't scale your time series data unless and until it is needed, because you have to keep performing this step of decoding the value, whatever that will be. Are you clear? Are you able to understand the problem? Not the problem, a challenge or an overhead. Now this overhead will come sooner or later. It has to come. You have to pay the price if you are doing it. But let's see you if you have done it. Doesn't matter. Now we have split the data. We already have the data. We have split it into train test set. That's fine. 95% is my training data and 5% is my testing data. Now I am shaping my data to be used for my LSTM model. So if you remember from the previous step that we have done, before we start our LSTM, we shape our X. So if you see, we will create the sequence length of 10, and then before using it, we will shape our data. This is a very important step. Okay, because this is how we are going to consume the data. Now, whatever we have created the shape at step 38, we will be applying the same set of data points. Okay, we create the model, we add the layers of LSTM, we create an output layer, we use the model compile. So let's see what we are doing here. We are create a sequential steps. We are adding 128 units of LSTM. We are keeping the return sequence as true. If I keep the return sequence as true, that means I will be using another hidden layer of LSTM. Yes or no? Now my next LSTM is half of my previous one. It had 128 units. I'm using 64 units. And from the 64 units, I'm creating a return sequence as false. At this stage, my LSTM model is completed. What we are doing here is we are using our data and we are generating our output. We are passing the value one by one and we are generating the output. This is the input train shape that I am passing. So if I have to just see what is going to be my experiment shape. So what is my input shape I'm passing? I'm passing this shape. I'm passing 60 inputs. That's fine. So let's say I have trained this model, I have compiled this model, and I have got mean square error as my loss function. And I trained my model. So my model is trained on my input data, but I need to evaluate it. So how do I do the evaluation? Model building is fine. Model building remains same. Be it this model or be it this model. The only difference here is we have added one more fully connected layer. Apart from this, I don't see any difference between the syntax of these two models. Yes or no? Okay. So once we have trained the model on a couple of epochs, we have the data with us, we have done some. So what we do now here is we want to see whatever I am predicting. What exactly, how far is it from my real data? Because my LSTM is a model which is going to predict a value based on 60 inputs given to it. Right? That is the shape I have defined. 60 inputs have to be given in order to predict a value. Are we clear to this part? 60 inputs will predict a outcome. Right? So we make the predictions and we visualize it. So we can do an RMSE also and we will visualize it also. So if you analyze, your green is your actual one. Green is your predicted one and red is your actual one. So see, if you can visualize it, it works very well. So this is how my output is, and this is how we can decide whether the model is good or bad based on my RMSE score. So I am off the chart 5.56 units. So this is what covers the basic LSTM. All right.
Just a quick info guys, Intellipaat offers generative AI and prompt engineering course which will help you gain proficiency in creating generative AI chatbots and other Gen AI tools, along with mastering the latest tools and techniques with hands-on projects and real-world case studies. And the best part, This course will be taught to you by IIT faculty and the top 1% industry experts. What's more, you'll be getting your generative AI and prompt engineering certification from Microsoft. With this course, we have already helped thousands of professionals in successful career transitions. You can check out their testimonials on our Achievers channel, whose link is given in the description down below. Without a doubt, this course can set your careers to new heights. So visit the course page link given down in the description below and take your first step towards your journey as a Gen AI engineer.
So let's say if I have a corpus of data, I need to know what could be my vocabulary. Then I will start giving unique representation to my vocabulary. So initially we started with TF-IDF, bag of words. Then we move towards word to vec. Then we move towards the contextual part. In contextual, we have glove, fast text, etc., etc. Then we move toward Elmo. What is special in Elmo? Elmo is trained on bi-directional LSTM. And from Elmo, we move to ULM FIT. What is special in ULM FIT? This gives transfer learning mechanism. We don't use them. We don't use them in our conventional day-to-day activities. The reason here is these two gets covered as a part of transformer. So when you talk about a transformer, it has its own tokenizer, embedding, etc., etc., etc. You don't need to get it from third party. We will discuss all this. So what we learned there is how we can classify a model. There is how we can, everything is for embedding. You want to do it for word, sentence, it's your choice. Okay. And second thing is embedding. Now, at this stage, I requested you to brush up your NLP skills. And we need to know how document classifier works. Do we know how document classifier works? For example, if you're processing invoice documents, we can classify whether it's invoice or credit memo. Yeah, so how will you do that? How do you decide whether it is invoice or a credit memo? How does that function? How does that work? How do you design it? Semantic search. We are going, okay. So, how does your basic classification work? You have a data. It is in the form of a tabular data. There is a target variable. Okay. You divide the data into X-train, X-test, Y-train, Y-test. You know what is X-train, X-test? So these part would be your X-train, this part would be your X-test, right? This part would be your Y-train, this part would be your Y-test. This everyone is aware of. Then you use model, what that can be, random forest classifier, and then you build the model. This is how a classification model works. Now, how will you do a classification model if the data was text? You have books, a book from library, and you have to define whether the book is going to be in the maths section, the physics section, in the AI section. How will you decide? The last part, let's say the model has three parts. One is A, B, C. C is going to remain as it is. C will not change, B will not change, but how will you generate A? So the story is how to generate A. How will you generate A? How will you get a A? I'll give more context. Let's say you have books. Okay. Now books have pages. Pages have sentences. sentences have words. Okay. When you say you have to create a CSV, what is going to be your column? What is going to be your row? What is going to be your target variable? Target variable is clear. Target variable is either it is a maths, either it is a physics, or it's an AI. But what is going to happen in this part? Is the question clear? This part, what will come? What will be your column? What will be your row? Keywords of each subject will be what that would be. It will be a column, it would be a row. Be a column. Oh. Fine. Now, I said we have a book. Okay, and book has page. Page has word, sentence, everything. Now, what we have done here is we have done two things. One, we have identified which word is important. Second, we have identified what is the frequency of that word in entire book. So let's say I have identified words. What could be my words? This could be like W1, W2, W3, W4, W5. This is my target variable. Now, what is my book one? My book one has 4 of W1, 6 of W2, 0 of W3, 4 of W4, 2 of W5. And this is my maths book. What is my W1? W1 can be linear, a word called as linear. What is my W2? W2 could be a word could be anything. It could be probability. Similarly, W3, W4, W5. Then we have B2 going up to B1000. Now we have maths, we have physics, we have AI, similarly. This approach of finding 4, 6, 0, 4, 2 on this is called as bag of words. There is a possibility of the feature might evolve, isn't it? What does that mean, feature might evolve? The new words might come as a vocabulary. Yes, there is a possibility. Definitely. That is why you need retraining of model. But POW doesn't help in finding important words, right? I mean, won't work on context based, right? Well, that is separate story. We are just trying to identify how classifier will work. So finally, we understand how classifier works. So how does a classifier works? The A has to be handled using some embedding technique. Okay. Now, if we retry this, how does my text classification work? The first step here is I have to identify vocabulary. Second, I have to find my embedding. Third is I have to have my train test split. Fourth is when I say embedding, I would represent document as embedding. Train test split, and then we do model building. Are we clear how a text classifier is built? If my embedding is bag of words or TF-IDF or glove or word to big, I can use our conventional ML models. No problem in that. This is one combination of classification. The second combination here is use LSTM, transformer, and family of it in order to build a classifier. So either you can try this one or you can try this one. Most people explain the classification with the help of using bag of work, TF-IDF, and then add random forest, it is a decent classifier. Then they say increase the quality of your model. Go to XGBoost, up to XGBoost. Improvement will definitely. If the improvement doesn't happen at this stage also, people recommend change your embedding. Let's try to increase this part. Once you start increasing this part, again a series of modifications are made. Usually we all start with the root 2v, that is word to vec. That means every word can be represented as a vector. Word to vec, you can use it from the family of GenSim. GenSim is a framework that offers word to vec based embedding. You can use a pre-trained word to vec. You can do a self-training on your data also. This is one way. The second way here is you use a custom based model. That means replicate all the steps which are required in order to build a word to vec model. And then create an embedding. So what would be the output of word to vec? Whatever data you have used, it is called as corpus. Are we clear with term? Input data is called as corpus. Output data can also be called as a corpus. Basically, text data is called as corpus. Now, corpus will have sentences. Sentences have words. What I am trying to do here is I am trying to create for every word how it is represented. Now, it represented, this is called as dimension. So if I say 300, that means word 1 is represented using 300 dimensions. If I say 100, I'll say W1 is defined with the 100 dimension. That means my matrix is 1000 cross whatever is my dimension. Now this becomes my embedding matrix. So what I do, I find a equivalent embedding value for this word. But this is not directly done. First, before that also one step has to happen. So I have a sentence, sentence has words. So for first, I have to represent each word as a numeric number. Then this step is called as tokenization. Ever heard of the term tokenization? Okay, great. So once you have done tokenization, you have number representation for every unique word. So let's say I had chosen the vocabulary. I have a book. I have used the vocabulary. I have identified 1000 unique words. So each word will get a number. So I create a map, word and number, word and number. So doctor, let's say, has a word, has a value 1000. So this 1000 I have to find in a matrix. So I will say, where is the 1000? 1000 is here. What is its representation? This is the representation. So 1000 has this representation. 999, 999, what could be 999? 999 is this word. What is this word? This word is engineer. This is how I do a tokenization, then I do embedding, and then I build a final matrix. Are we clear till this part? Can you extrapolate this concept to other concepts? So if you are good to go, tell me one thing. If you have so many unique words, how will you find a representation of a sentence or a book on a page? This whole concept is about finding a unique value on a basis of, so we created this for a word, but my initial question is to identify book. Book has 1000 page. Each page has 100 words. Now I know only one word representation. How do I understand what is a 100-word representation and what will contribute to 1000 pages? How will I do that? Are you able to gauge the problem? Are you able to gauge the complexity of the problem? Bias? There is no bias. Look, you have a book. Okay. You have a book has 1000 pages. Each page has 100 words. 100 words as in 100 unique words, which is coming from the vocabulary. For one word, I have got my representation of 300 dimension. For second word also, I have this one. Similarly, for 100 words, I have a representation. This entire representation will represent a one page. Then I have to find similarly second page, third page, fourth page, up to 1000 page. Once I have this entire representation of 1000 pages, this will represent my book one. You understand how it is nested? Yes, no? So what part you don't understand? Everything or something? So let's read this again. You have one word is represented in 300 dimensions. That means some values are there as a part of this vector. Then you have second word identified and this you have done. Similarly, let's forget about the book. Let's think of sentences. Book can be a little hard. Let's take example 2. Forget about the previous example. I can identify word. What is the equal vector representation? This I am aware of. We are good to go with that, right? This part we know. This part we know, word to vector. Now, if I have sentences, one sentence, two, and sentence, three. How do I represent every sentence as one unique or one single? Unique is not the right way, single vector. For that, I have to split my sentence into number of words. Okay, let's say there are 10 words which represent sentence 1. So what I will do here is I will find all 10 words representation. Is this part clear? Then what I'll do here is I will take an average of all this and create, let's say this one is the average one. Take total, divide by 10, find the average value. This average value will represent S1. It is one way. The other ways can be other different ways are there. Okay. So this is called as sentence to vec. So first one was word to vec, second is sentence to vec. That means each sentence is getting vectorized. How? This is the maths behind it. Extended the same logic, you can do doc to vec. Yes, doc to vec is page to vector. You also, this is the way your Copilot is built. You know this GitHub Copilot? The basic idea of GitHub Copilot is code to vec. Every piece of code is represented as one vector. See, this is word to vec. When you take multiple word to vec and you average them out, it becomes sentence to vec. When you take multiple sentence to vec and average them out, it becomes doc to vec. So you have word to vec, lot of word to vecs. All of them combined average becomes sentence to vec. All of sentence to vec combined become doc to vec. Now, if you start doing it yourself, you will not be able to do it with that finesse. That is where GNSM comes and play a critical role. So please look into this library, practice this library. This library is very good. It gives you a good framework when it comes of these specific things. Word to vec, sentence to vec, doc to vec. It also gives you topic modeling with using different techniques. So it's a very powerful library I recommend. Another recommendation is NLTK. Please explore this library. Third is Spacey. These three things are sufficient for any beginner to start NLP journey. Once you are done with this, you need to move forward and experiment new frameworks. One of them is called as a RASA framework. RASA framework gives you different capabilities. Third stage of this would be going to Hugging Face framework. Now, since today we are going to discuss the Hugging Face framework, and as you know, I'm habitual of giving a little bit of historical trivia. I am just was trying to explain you what is an order in which you should reach Hugging Face. Now, I am not going to explain each one of the frameworks. This one is definitely part of the course, but this is the flow in which you should reach Hugging Face. In between, you can try this also. What is this name? Haystack. It's also a very good framework to explore. Once you have done Hugging Face, then you move to LangChain, where all the current work is happening, that RAG based. If you have come across these terms, you will understand which one is getting mapped to which place. Are you clear? Is the framework story clear? This offers you chatbot building. Okay. Now, in order to proceed, so we all understand how document classification works. No, tokenization is different, vectorization is different. Tokenization is giving ID to a word. Vectorization is representing into a dimensions. You can understand tokenization as label encoder. Okay. So how did this everything got problematic? So in 2017, something happened. What happened? Google published a paper. What was the name of the paper? Attention is all you need. Okay. This paper became synonym to term called as transformer. This was happening similarly. During the same time, what was happening? During the same time, we were trying to understand how transfer learning can happen in NLP, if you remember the story. And for that, we were working on Elmo and ULMFIT. They were built on top of using LSTM, that too bidirectional. So transfer learning was taking place. So when these two got combined, we started generating state-of-art transformers for classification. So in 2017, we got transformers. Then in next phase, we were getting back. At the same time, we got ULMFIT by 2018. By 20, then there was GPT that came, and then immediately once GPT came, BERT came. GPT came from OpenAI. BERT came from Google. Once BERT came, again GPT-2 came. And then when BERT came up with DistilBERT and Robata. So the journey and the competition started like this. And everything was based on transformer. Now, what was GPT and what was BERT? We have to understand. So GPT is called as generative pre-trained transformer. BERT is called as bidirectional encoder representation from transformers. Please take a note of it. I'll repeat it again. This is called as generative pre-trained transformers. This is decoder based and this is encoder based. Bidirectional encoder representation from transformers. In order to understand the first term, that is transformer, we have a prerequisite. What is a prerequisite? If anyone wants to understand transformer, there are three things one should know. One, what is encoder decoder architecture? Second, what is attention mechanism? Once we understand attention mechanism, we have to understand self-attention. Third is transfer learning. Transfer learning is okay. Conceptually, you will understand something you are doing in order to learn. But these two things are very important. Yes or no? And we have not studied them. We have not studied them. Yes or no? Or you know already encoder decoder. So these two things came from LSTM. What does it mean? It means when we were moving from RNN to LSTM, LSTM was improvising. The next generation architecture of LSTM was LSTM plus bidirectional, which we had a idea last time. We remember we discussed LSTM can be done using bidirectional concept. Then LSTM bidirectional plus attention came into the picture. Why attention? I'll explain you that also. Once this was done, we moved to the next part, that was encoder decoder based LSTM. This is base of learning transformer. So till the time we don't finish this, we cannot understand the real essence of transformer. So I will try to explain each one of it. Okay. Are we clear why we are going back to LSTM? Because in order to learn transformer, we have to learn three aspects of LSTM. What is that? First is bidirectional concept. Second, we need to understand what is attention mechanism. Third, we need to understand encoder decoder architecture. Okay. These three things are important. Bidirectional we studied last time, but I think one or two students have some confusion about the bidirectional concepts. So this is how my bidirectional LSTM looks like. Okay. Now, why do I need bidirectional? That was the question, if I remember it correctly. Why we need it was the question. Yes. Now let me write a sentence. John was hit by. Do you need more information, or this information is sufficient for you to decide X? What can be this information? Car, bus, something like that? John was hit by a kid. You are saying context is needed. Context is this context not sufficient? You also need W1, W2, W3. So X can be concluded as from John was hit, or X requires everything. For example, somebody may say John was hit by a bus. Let's say I say John was hit by a bus. This is my understanding. But what if I say this is not the case is this one is still blank, W1 is bus. Then what is X? X is something which qualifies bus. What can qualify a bus? The color, the nature. This is basically adjective. Okay. So I will say John was hit by a yellow bus. Now X cannot be found only by using this information. I would require this information also. If I only depend upon this information, this would be going in one direction. If I want the other direction also, I require bi-directional behavior. Are we clear? Bi-directional is important. Are we good till first part? Now the second part is attention. Okay. This is tricky. Why? What was the reason of using LSTM? Yes, if a word to be predicted is in the middle, then unidirection cannot be beyond that. Is that right? No, it's not in the middle. When you are trying to identify the significance of every single word, how does LSTM work? I have input, I have given it to an LSTM block. LSTM block is generating my hidden state, passing this information to another LSTM. Next timestamp input comes here. I generate another hidden state. This is 0, this is 1, this is another. So similarly, I am passing this information to my final output. This is my basic LSTM, yes or no? So this is H0, this is H1, and this is finally H2. Now my H2, I can say, is a hidden state which is going to be required in the final output. Hidden state also defines how significant my previous context is. This is where I was doing better than RNN, a simple RNN, because I was building cell state that will retain the memory of my past so that I carry forward the context. So H2 basically defines the weightage of my context, but I can't have a clarity on the context till the time I don't read it backwards. So the hidden states that I have to generate at every stage should be in reverse direction also. So H2 is not just H2, but if I go it back, so my H2 in forward direction and H2 in backward direction is my net H2. In prediction happens. For that, what is needed? Already we should know what is the value of name. And what is the value of name? It has to come from the training. How do you want to train? Training, you already have everything. Final output, correct? Based on training, you generated an embedding. This embedding will be used in prediction. Now, training can be done using LSTM. It can be used during bidirectional LSTM. It can be used during BERT. How do you train it? Then you create a model. Model gets leverage at a prediction. When you are predicting something, you already have the third part that I said, the transfer learning. In this case is required. How does it happen? It happens when you first build a language model. That means what is the next word? That is called as language model. Language model is built on my training corpus. Based on the training corpus, I can build my language model. This is built. Now, what happens next? I take this model and I put it into the target domain. What is target domain? Target domain is what you want to predict, WhatsApp data. Fine. This was trained on Wikipedia, and this is will be tested against on WhatsApp data, whatever is given. Third, when it is trained on, it is moved to the target domain. Third is we will fine tune. That means on the target data, we will say, okay, you are predicting L, you should have predicted M, like that. This becomes my final model, which is using a predefined weight. And if I require some tweaking, that happens. Small tweaking, not entire learning. Learning has already happened. Predefined weights I have extracted. So when I have doing this part, I am using different type of approaches. BERT is one such approach, right? So in the runtime, it's not possible because we don't know what is going to come next. But that is getting confused with the transfer learning. So you jump to the last part very fast. That is right. It's not possible. Otherwise, it will become a problem. Now, where were we? So we finished why bidirectional is important. Bidirectional is important because it enhances my training. Now the point here is, why do we need attention? What is the need of attention? So what was the problem which we were trying to solve? We were trying to solve the context. The context information in RNN gets lost. Yes or no? What was the problem in RNN? Context was getting lost. But if I increase the size, will LSTM be able to retain the context? Are you able to understand point one? Context is hard. Context is hard in RNN because sentence will create a problem. Now, what are we trying to say? We are trying to say, if I have this LSTM block, LSTM1, LSTM2, LSTM3, LSTM4, I am passing the inputs and everyone is generating a hidden state, cell state, hidden state, cell state. When we are passing this, I have to pass my hidden state. I have to pass my cell state, and then I have to make the prediction of the next unit. Is it right or wrong? This is how we have learned LSTM. So let's say this one is H0, this one is H1, this one is H2, and this one is H3. What am I using as an input for predicting next word? H3. How I'm getting H3? H3 I'm getting by adding H0, H1, H2. I'm taking them, but I'm not doing anything to them. It is getting diluted. The hidden state impact of H0 by the time it reaches H3, it gets diluted. Yes or no? So one such approach came that do one thing, create a context vector. And context vector will have representation of everything. And then that context vector will be used in order to ensure these hidden states have representation. So that the context, the highlight, the theme of the sentence is captured with the help of hidden states. This mechanism was called attention mechanism. That means if the sentence is long, which part requires more attention? So what does attention do? Rather than producing one single hidden state of encoder, that is input sequence, we should capture the hidden state at every step. Now, in order to understand attention, we will first go to encoder-decoder architecture. I'll come back to attention again. So don't think attention is done. Attention is just started. But in order to understand why context is needed, we have to first understand encoder-decoder. What is encoder-decoder architecture? So if you have a LSTM block, you are passing an input, you will get a final output, right? Is this block okay? In whichever way you go, you will get output. Output is final. Now, this kind of thing can work good if it is a classification. What researchers realized is, what if we pass this input, we replicate it at another place, pass this output over here, and then generate value again. And now everything that I generate here, this is output 1, output 2, output 3, output 4. Confusing? Case 1. I pass input to LSTM, I get 1 output. Yes or no? I'm repeating. You pass one input to LSTM, you get one output. Yes or no? You pass input to LSTM, you get more than one output. That is also possible. Why I need the second case? Why do I need a second case? My first case was very simple. I have input. I have passed it over the LSTM. And I have got the output. This output I will use. My second case is I have an input. Okay. This input is passed. I have got my output. This output is getting given as an input to my another block where I'm passing the value at every hidden state. I'm generating a response. Possible cases. Now, where do we use this? This is used if you have to do summary, machine translation. For example, I'm writing something in a language one. I write, these are the only two languages I can write, so I'm just using it. Mera, I don't know if I'm writing Hindi correctly. Something like that. Now I am passing this into my LSTM1, this to LSTM2, LSTM3, LSTM4. And then I start generating my output. What would be my first output? My. Second would be name. Third would be is. And fourth would be psi. Now, this is what? This is summary or machine translation. This kind of design is called as sequence to sequence modeling, where I'm passing a sequence and generating a sequence. It is commonly called as seek to seek. You have an input and your outcome you want here is series of word. You have an input which can be series of word. This was the example. No? Okay. You have a series of input and you want series of output. In which example you have it? You want example like summary. You want example like language translation. From German to English, English to German, like that. Are we clear till this part? How do I do this? I pass my input into one sequence of LSTM blocks and I generate my output from another sequence of LSTM blocks. This is where I give my input, I create my context, I pass that context, and then I start generating output. Okay, this is sequence 1, this is sequence 2. This is called a sequence to sequence. Now, how does it work? Like I gave an example, you have an input sequence. Input sequence can be a series of a sentence written in German. I don't know German, assume something is written in German. Now, based on this, I pass this as an input to LSTM. So LSTM will take inputs, generate my outcome. What is the outcome? Hidden state. And that hidden state will be passed to another sequence. Conceptually, is it okay? This is called as encoder. This is called as decoder. I'll give you more detail. Just understand the terminology. This is sequence. Input sequence is called encoder. This is another sequence. Output sequence is called decoder. One is your input sequence. This is encoder. Output sequence is decoder. Just to clarify, we are still training. We gave input sentence, my name is Sahir. Yes, everything is training. There is no prediction. This is learning which is happening. Right. This is encoder and this is decoder. Are we clear at least till encoder decoder part? What is encoder comprises of? LSTM. What is decoder comprises of? LSTM. No, it is not word to word translation. It is sentence to sentence. The hidden state that we pass next sequence will be a series of values or will it just be one? It will be a vector. Vector will depend upon the dimension. Okay, this is a better. So let's say this is the example that we try to correlate with. This is my sequence. Since it is an input sequence, I called it encoder. This is another sequence. It's an output sequence. I called it decoder. First, is this part clear? Input sequence is called encoder. Output sequence is called decoder. Let's do step by step. Encoder, decoder done. What is the job of encoder? Read input. What is the job of decoder? Give output. Are we clear till this part? Okay. Now, why do we need encoder, decoder? For generating the output where we require output in the form of summary or machine translation between two different languages, or anywhere where we want to train input sentence with the output sentence. Are we clear? Okay. Now let's say this is my source sentence. Thy protest Warren am blah 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 blah. I am not good with German. I can't speak it well. But let's say these are the words in German written. Are we good till this part? Certain things you need to ignore, certain things you need to follow. I'll tell you what to ignore, what to follow. I have passed this input. This input is, let's say this is going to be embedded and let's say this is the entire thing as an LSTM block. I am passing the hidden state over here. I am also maintaining my hidden state over here. This is my H0. This is my embedding. This is my whatever calculations I have made. And this is again going to be my H0. I am going to pass my input 2. When I pass my input 2, I do the encoding. I pass this encoding above. I get my H0 and this one. Input value, it gives output as H1. This H1 is also passed over here. Do you see it, one? Sorry, this is passed over here, H1. This is the embedding which I am passing. Embedding is combined with H1. I am generating a new hidden state that is H2. This is my H2. This again is getting passed over here. Similarly, I am doing it. And finally, the last word which I am passing is going to be the starting point of my. So this is my final output, which I am generating as my final hidden output, H3, H4, and H5. H5 I am giving as an input. Okay. This is the word is only for the explanation. It doesn't come with the words. So I am saying I have forget about it. So this is my input. Every input has my encoding equivalent. Not encoding is not the right word. I will say embedding. From the embedding, I am basically going up and generating my H0, and the same H0 I am passing it like this. So I'll get H1, H1, H2, H2, H3, H4, and H5. Whatever is my H5, I am going to pass that value. Along with H5, I will also pass the actual value because it's a training. This concept of passing the actual value is called as teacher forcing. That means you are educating the model start from here. If it is right value, fine. If it is not a right value, still we pass the value. But when you have given the value as the next words which are generating are coming purely from this word. Encoder does not play any role here. Can we replicate this part in our drawing board? I have an input. Mera naam Sahil hai. Now, what is my output? This is also given to me. My name is Sahil. But how am I training it? I take my encoder. What should be the size of my encoder? What should be the size of my encoder? Size of my input. What should be the size of my decoder? Size of output. Okay. Now, what do? I pass the information. Which information? This information. Everything what I have seen, I'm making it in only one block. I passed one input. What is it? Mera. I generate hidden state 0. I pass that hidden state here. In between, what is happening? Embedding is happening. Mera is first represented as an embedding. What is embedding? A vector representation of a word. Then naam, and this I am passing over here. Sahil is passing over here. Output is coming here. And hai. Now, when I pass this as an output, okay, I pass this into a decoder. Along with this, I also pass this value, mine. So I passed H3 and I passed mine as my input to decoder. How many values I need in decoder? 1, 2, 3, 4. 4 values. So I will have decoder 1, decoder 2, decoder 3, decoder 4. Now, I am not only interested in the final output, I am interested output at every level. Okay, so I am passing this input, I am calculating same thing what I have done in encoder using it. And this also becomes input to my next state. So if I am passing mine with some context, I have to predict what is going to be the next one. The next one is going to be name. So basically, in this particular context, what is the next word which should come after mine? The word should be name. Again, a language model concept is getting repeated. I'm predicting the next word based on the previous word, but my previous word comes from the encoder, and I also get some context from the encoder. Is a basic encoder decoder idea clear? A quick recap, you have input sentence, you have output sentence. You generate encoder, you pass it value into the decoder. Decoder take this as an input, take the first word. This is called teacher forcing, and then it will generate this kind of a order, and every single state which is generated from a decoder is my output. This is the method of generating summary. This is the method of generating title. So if you pass the entire page, it will generate a title of that news story based on training data. So training data will say if this is the input that you are passing, this is the title of the news story that you should be generating. That is one use case. Another is generating summary, small summaries. So you have to understand if you increase this size, the value and the quality will diminish because it is getting degraded. So usually you will see the output of these things are encoder decoder output is very small. How about the next blocks after first block in decoder? Will we be again passing hidden state of the first decoder? Yes. We are passing the hidden states. Input encoder can be long, but output decoder needs to be short and sweet. It doesn't work very well if you put it long. So hidden states are getting passed. You look at here, these are the hidden states. They are getting passed. They are needed in order to understand what my first LSTM in the decoder is saying. What is my second one is saying, what is first one is saying, what is second one is saying, third one, fourth one, fifth one. But I am retaining the values also. So these values are also I am retaining. This is just basic understanding. It goes very deep. I don't want to touch that all those things in the first 10 minutes of the lecture. We will get over there if it is needed. But this at least should be idea what part of encoder impacts what part of decoder, because attention comes after this. So I can't explain the attention, or you cannot understand the value of attention and self-attention if you don't understand encoder decoder. So what we will do here is we will any role of cell state in encoder decoder, the first value that you see here, this part is actually your hidden state of your encoder, cell state of your encoder as a final output generated and then passed along with the first word of your decoder. That is the. To make it complex, bidirectional will be within the each LSTM blocks. So LSTM bidirectional. So LSTM bidirectional will be this final output that we are generating. We will have another layer on top of it, which will be taking this encoded value. This will take this encoded value and generate final values over here. This final value will become input. Rather than this or this, we will take this as the final output or passing the value. So this will have one bidirectional here and one bidirectional here if needed. Make sense? Similar to hidden state, does cell state are also bidirectional? No. Cell state are not bidirectional. Hidden states are bidirectional. Not for word. Once again on this bidirectional part, sir. See, bidirectional will happen for encoder separately, same as it was happening here. Let's say this is your encoder part. Bidirectional will happen over here, and whatever is your final one, softmax value will be passed as an input to the decoder. Okay. So it will not be like what is happening at one stage. It is like overall, whatever LSTM you have created, its final cell is an outcome of a bidirectional LSTM. But is bidirectional LSTM required when we are doing encoder decoder? We have to see that. It is, because the BERT is based on that. So now you can see that when we started, the GPT is based on decoder part. The BERT is based on encoder part. No, attention is not that class. So we understand encoder decoder, right? Encoder decoder is also called as seek-to-seek model. So let's close the encoder decoder by writing about it. So it was LSTM and RNN family that started and gave us the idea of sequence to sequence modeling. Okay. This here in this case, we have encoder and we have decoder. The job of encoder is to encode the information which is coming from the input sequence. We encode it into a numerical value. And this is called as hidden state. It is the last hidden state that is passed to the decoder, which generates the output. Then decoder is itself a LSTM block. Is this slide okay and clear? You have input, you pass it into the encoder. Encoder is nothing but stacked LSTMs. What is stacked LSTMs? Group of LSTMs put together in one block is called stacked LSTMs. From here, you start the stacked LSTMs output called as decoder. This becomes your encoder, this becomes your decoder, this is your last hidden state. Are we clear to this part? Okay. Now, sorry, encoder, decoder. Now let's say whatever is my LSTM, let's say this is my input. Okay. EOS is end of statement. Yeah, keep going. Okay. Now this is my input sentence. How is your sister? Now, how does this part as an encoder will work? We will be passing some values at HO. It will be giving us hidden state. This will give me another hidden state. This will also give me other hidden state, right? I will be also passing this value like this. And let's say if this is my final token, this is going to generate my final output. That is the first word. Are we clear to this part? This first word will become my input. So whatever is this first word, this will be passed over here. And what it will give me an output. Now, this is going to get passed here. Thank you. You will give me she. She will be passed as an input. And she will give me G2. G2 is going to give me output as is. Thank you. She is fine or whatever you want to say. But I will be passing this information like this as well, because this is also an LSTM block called as decoder. Are we clear? Encoder, decoder. Is this example fine? All right, let's assume this example is fine. Now, what we are saying here is pass this entire information into one vector called as a context vector. What is context vector? A context vector should have the global information about the whole input sequence. And if I have to say, it should have a precisely how each step of the input sequence is related to the current state in the decoding phase. So what are the things that context vector should be having? So context vector should be having a couple of things. What it is, it should have a global information about the whole input sequence. Not just one state, entire input sequence. That is part one, it should be having. Earlier, without green color, everything, whatever we have done is encoder, decoder. We remove the green part, everything is encoder, decoder. Green part is attention mechanism. So please pay attention to attention mechanism. In attention mechanism, we create a context vector. What does context vector do? It holds a global information about the entire input sequence. Apart from that, what it does, it also maintains the information. It also maintains the information of how each step of the input, that means hidden state of the input, is associated with decoder part, that is GS, hidden states of decoder. So how is H0 associated with G0, or how is H1 associated with G1 or with other states? So this is what is we are trying to capture, not just taking an average of context vector, which maintains that which state requires more attention, weightage. It also helps identify how the relation is established. Is the statement clear? Why it is needed? Why it is needed? Since if the number of hidden state, if we have a large sequence And when I say large sequence, large input. What happens here is I have to maintain, if I want to maintain or want to create a mechanism to identify which hidden states need attention. So I have to create a mechanism which ensures which state needs more attention. So in order to achieve this step, we created context vector. So what does it do? It helps attention mechanism helps decoder to assign different weights to each encoder state at every decoding step or time step. Coming back, this is clear? Green part is clear? Now we will talk about how this, what does this mean? How this can be interpreted from this example. So let's say we are at G2. So if we are at G2, what is the input that I'm having? I am passing the value here as she, right? And I'm getting, and I'm also passing the value of hidden state of G1, and I'm getting output as is, right? Here, the idea here is we have to identify when we are passing this information of G1 to G2, how is my G1 associated with, so what is my G1? Let's say G1 is generating value of she, what is she associated with which of this part? Now it comes the English language. You understand English language to some extent? There is something called as noun, pronoun, preposition, adjective, right? If not, you can do a basic revision. She is associated to sister. How? She is associated to the sister using the verb is. So the is here. So she is related with the sister using is. How is she? But this is how I do it theoretically. I know that is a verb, is going to be most important part. Out of H0, H1, H2, H3, she will have a lot of importance coming from state H1. Why? Because it defines its relation of what it is. Are you clear till this part? At G2, what we need input from G1 plus we are getting she as an input. So G as an input, let's say she, and then we are getting the context vector. So how does this help? What does it help here is it identifies how is my G1 associated with H0, H1, H2, H3, H4 like this. So how does it find what is important? It applies this formula. C of I is J of I to N alpha ij times hj. Hj we already know H0, H1, H2, H3, H4. What is alpha ij? Alpha ij is exponential of Eij divided by summation exp of Eik. This is nothing but a soft max function. And what does it do? It basically tries to find the coefficient E, which defines the similarity between G and H. So basically, in simple words, if I don't want to understand maths part, I am trying to find out the similarity between G1 and all the hidden states. And which one has the highest probability, I am going to use that hidden state as my reference hidden state. How do I get a probability? will pass whatever is my relation of, so I will pass G1 and H0 into a softmax function. Find the softmax of G1 and H0. Find the softmax of G1 and H1. Find the softmax of G1 and H2. Find the softmax of G1 and H3. Whichever softmax gives you the highest probability, because it will highest probability, take that hidden state as a reference state. That is happening behind the scene. Are you clear to this part? So I'm trying to explain it from English and maths both perspective. So what we are trying to do here is, so on a high level, it tries to identify the relation or importance between the words. Yes. So at a high level, I have encoder, I have decoder. And what I'm trying to say here is, at decoder, in order to predict next word, I just don't need previous word. I need previous word. Plus, I also need to know which part from encoder is important. I am also taking all hidden states into consideration. And how do I find which part is important? I use the attention mechanism. How does attention mechanism works? It takes the dot product of vector 1 and vector 2. What is vector 1? It is my G0. What is vector 2? All set of hidden states from my decoder, and I apply a softmax function on top of it. Dot product, softmax, what it gives? It gives probability. What does probability says? Which one is more important? Yeah, decoder hidden state is the previous word. When I say the previous word, I'm saying Gn minus 1. So I just don't need decoder information. I also need encoder information. And that is what is called as attention mechanism. This was done by LSTM. Are we good till this part? Or is it too much? It's fine. Excellent. So let's do again a recap. We keep on doing recaps so that you don't. So we are applying LSTM here. We don't want you to forget what we have learned so far. So what we learned so far, we did LSTM. Why we did LSTM? Because RNN was not taking care of large lengths. Then we realized if we increase the length size, we are losing the context. So in order to understand the context, we did bidirectional LSTM. Then we upped the ante and we said, okay, there will be encoder and decoder mechanism. What does it do? It gives us a better way to interpret input sequence. Then while doing it, we realized we should not only rely on the decoder part, we will apply attention mechanism where decoder has information of decoder plus hidden states of encoder in order to generate output. So all of this we did, and it became part of our sequence to sequence model. So if somebody asks you to build a sequence to sequence model, technically it would be having all these things. It should have an encoder, it should have a decoder. Preferably, there should be attention mechanism. But if you have only encoder decoder, that is also sequence to sequence model. Are we good till this part? Then something happened in our life, and that was the year 2017. In year 2017, Google was not happy with our life, and they said, if you have an attention mechanism, and the attention mechanism has significantly changed the landscape of encoder decoder architecture. So they emphasized and they said, what if you have self-attention? Second, what if you have more than one attention? Together, it became one paper, and that paper was called as transform. Now, self-attention is different from attention. We all know this part. If I have to give a very brief difference between attention and self-attention, attention focuses on decoder's relationship with encoder. Self-attention says, find the relation within your own sentence. That helps you give you more priority on what is the relation of one with the other. Okay. More than one attention, we will see what is it. But 2017, we have reached. Okay. What we got here, we got this design. Do you see this design? How does it look like? Okay. Yes. This part is your encoder. This part is your decoder. What are we passing? We are passing input value. That we know. We are taking embedding. That also we know. This is new. Positional encoding. Something new. Okay. Multi-head attention. This is also new. Add and norm. This is what? This is same as your batch normalization. What is feed forward? Feed forward is same as your fully connected neural network. Add and norm is again your batch normalization. What else is there? This arrow. Apart from that, I don't see anything. These are the components of this block. Yes or no? Yes or no? I'm going to mark it. 1, 2, 3, 4, 5, 6. And arrow is 7. So out of these 7, 1 is known to you, 2 is known to you, 3 is not known to you. I am putting it in a square. 4 is not known to you. I am putting it in a square. 5th is known to you. It is batch normalization. 6th is known to you. It is fully connected neural network. 7th is something you are not sure what it is. Okay. This arrow is part of 4, multi-head attention. Now, 7 is very similar to, if you know in vision. You have learned computer vision. There is a concept called as ResNet. Are you aware of the concept ResNet in computer vision? Vision is not started. You have vision after you have completed. Yes, it is part of your computer vision. Vision is completed, but ResNet is not completed. Okay, are you aware of VGG? Is VGG part pre-trained model? Yes, VGG. Yes, yes, yes. Okay, fine. We will understand separately. We will not touch vision into the picture. We'll just understand a very important concept called as residual. Okay. So let's take one step at a time. If you will see, this part is getting, see, if I consider this to be one single unit, or if I convert it into 2 units, one is this is 1 unit. So you will see this unit is over here, same unit is over here. The only thing is you have 2 separate units for this. That doesn't make So CNN, okay, come to this part. And then you have this part. This part we already all know that softmax is there to get the probabilities. Okay, so what we have to do now here is we have to understand one by one all the components: position encoding, multi-thread attention, and residual. Okay, are we good to start? Yeah, I'm explaining the self-attention from the beginning. Okay, Vilas, I'm explaining. Now we are starting. I'm just saying there is attention and there is self-attention. Self-attention is slightly different from attention. Now, how it is different, we will see that part. Okay. So in transformer, what is happening? We have input. Okay. And then we are passing the input to the self-attention or attention group. Now, what are we trying to achieve? In this layer, what we are trying to achieve here is, we are trying to say that this layer will help the encoder, because we are now first talking from the encoder part. Similar thing, whatever we are doing in encoder will happen at a decoder level. So if you have understood encoder, you will understand decoder automatically. So we will just try to focus on one part, that is encoder. In encoder, the first part here is attention. So this layer will help the encoder, it will help encoder to look at the other words in the input sentence itself. So every state in the encoder should look at the input stream of data that we have and use this information when we are encoding our input. That means if I have a sentence, input sentence, my input sentence is I used this example last time also, I'm again using the animal did not cross the street because it was too. Now I can have two options. One is tired, another is narrow. If I say it, the word is tired, I am associating it with animal. If I say narrow, I'm referencing with the street. At any given instance, which is the word in my input sentence which gets impacted? If I change animal and street, which word in my input gets impacted? I'm marking all the words in the box. From the pure English point of view, which box will be impacted if I change the last word? It is it. It gets the highest impact. Right? Okay. What is the value of it if I write the last word is animal? Ram sat on the table. What is subject? What is your verb? And what is your object? Subject, predicate, you would have learned, right? So Ram, the noun is your subject. Table is your object. What is the action that the Ram is performing? Sat. Okay. Now, if I put a comma and I say it, and then I say broke down. Now, what does it? It is a pronoun. What does pronoun signify? Pronoun signify the last used noun, that is Ram. Now, since there is only one noun and there is one pronoun, I know that pronoun refers to noun. But if I have more than one noun, what happens? It creates ambiguity. You would have learned this in your NLP, or you should have learned this in your NLP to remove the ambiguity. Now, what does it mean? It means if I have noun one and then I have a clause, then I am talking about noun two, and then I have a clause. If I use a pronoun, English line grammar says this pronoun is technically representing noun two. Technically, it represents noun two. Ram went to a cafe to meet Sita, where, okay, let me just change Sita to some. Ram went to cafe to meet Sahil, where he was. Now, what does he refers to? Is he Ram or is he Sahil? So that depends upon what I'm trying to write. If I don't, let's say now I complete this, where he wanted to exchange notes. Who wanted to exchange notes? Both are okay. Ram wanted to exchange notes, or Sahil wanted to exchange notes. So pronoun to noun, a relation creates ambiguity. Humans can solve this, machine cannot. Are you getting it? This is the base of NLP. The reason we are studying all these things is because this is the problem we can't solve. So we have to understand what this problem is. How do you write a rule to identify what this he should be? You can't write the rule, right? So there are a lot of, this is called as ambiguities. Now you can have different type of ambiguities, lexical ambiguity, structural ambiguity, 10, 15 types of ambiguities. You can search them. Very interesting to learn. This is solved or interpreted using parts of speech. This part you have learned, parts of speech. You would have learned it called as POS tagging. There are three things that is possible. You have learned and you have forgotten. Second is you have not learned, not forgotten. You have heard it was mentioned, but not in detail. So out of A, B, and C, which part you are currently going through? Hello. Now I don't know whether you have not refreshed or it was not taught. So if you don't know these things, whatever we are learning in attention will make zero sense to you. That's the problem. You will have to assume now what was the problem. Got it? Now, let's start with the assumption part. So what are the problems we are having? One, whenever I have a pronoun to noun relation, I cannot establish a clear-cut indication. How do I usually solve this? I usually solve this by using POS tagger. How does that work? It has dependency parsing. What does dependency parsing do? Whatever you are writing a sentence, right? That sentence gets structured or identified with their respective POS, and you start creating the tree. I'll just show you, that would be much faster. Okay. Now, just quickly see how things work. Dependency parsing. So this is how our dependency parsing tree works. Copy image, paste here. Now, this is what, have you seen this kind of a thing ever in life? So this is my input sentence, right? In my input sentence, I have applied POS tagging and I have got these tags. What are these tags? Subject, object, determinant, modifier, whatever it is, doesn't matter. Okay. Now, this helps us identify what is on the left-hand side, what is on the right-hand side, if we have to create a tree out of it. For every subject, what is a relation? Now, this defines how my one entity is related with the other entity. No library is there on earth which gives you this. There is no library. If this library comes, it will solve 90% of NLP problems, where every entity, what it is linked with the other entity, can be seamlessly built. This is, at this stage, considered to be impossible. This is called as entity linking. What it is called? Entity linking. What I'm showing you right now is dependency parser. If I say in this sentence, flight is important. So what is defining my flight? Which arrow comes and hit the flight? Prefer. Prefer hits the flight? Yes or no? This is an arrow. This arrow hits flight. How does it hit the flight? Prefer hits the flight. What hits prefer? I hits the prefer. I is hitting prefer. Prefer is related with I. So flight word has importance coming from preference. And what is I? What is I? I is right now subject. Okay. What is flight impacting? Flight is impacting Denver. So Denver is getting impacted because of flight, right? So preference of flight impacts Denver. This is the crux that I have identified from my dependency parser. Does it make sense? Now, how do I resolve this problem if there are complex sentences? If the sentence goes up to 15-20 lines, how do I hold which pronoun was defining which pronoun? Isn't that a problem? Is that a problem or is that not a problem? See, one sentence we all can do. Very easy. I can make 20 rules and it will give me all the valuable insights. But if it is a long page, how do I do it? Exactly. Now we have come to the first part of the problem. If sentence increases, context evades. Why it evades? Because we cannot retain the memory of my dependency parser. I cannot create rules to ensure my tree works seamlessly. Resolving my pronoun with noun is also a big issue. Okay, there are libraries which helps you doing that. In the pre-transformer era, that was Spacey was one of that. It has a neural co-reference like functionality. It used to try to resolve the pronoun problems. Okay, so let me give you an example of a pronoun. So I'm going to tell you one sentence. Arvind is a great cook. He cooks very well. He cooked. I call it biryani. You can call it pasta, whatever works for you. And everyone, he cooked biryani and everyone was in awe of is off or with his cooking. What is the main idea in this sentence which is talked about? Why no? What grabs the attention? So if you see the news channel, at some stage of time, what happens in the Maldives, black magic on the president is a bigger news than what is happening in India. Now, some people get confused by thinking breaking news is relevant news. And they get angry. How can you call this as a breaking news? Now, tell me one thing. When somebody says it is a best-selling book, does it mean it is a best written book? Then why you don't get angry then? That's my counter argument. What I'm trying to say here is, do not bring the domain knowledge into the algorithm. Domain knowledge is, I know certain things are not important, but based on the algorithm, things will be important. These are two different things, right? If a context is given to you, you can find an answer to it. But if you add your own information on top of it, it will bring the bias. So first thing is we should not do that. Second, what is more frequent becomes important is a gospel truth. Can't deny that one. Now, in this case, how do we decide what is important? What is the first step we can do here? The first step here is I have the entire sentence in front of me. This sentence, as I have to identify what is the important theme of this sentence. How does I identify the important theme of a sentence? I need to break the sentence into individual themes. How do I do that? I call every single word as one theme. What does this step called? What does this step called? It is called tokenization. So I have this word. What will be the first step? My first step here is tokenization. What does tokenization do? I will create a list of words in which my first word is Arvind. Second word is. Third word is A. Then there is great. Then there is cook. Like that, I am doing it. How do I achieve tokenization? NLTK. Word dot tokenize or sentence dot tokenize for sentence tokenization. Once I have done this, what is the next step? I find the frequency. What is the frequency of Arvind? Arvind is only once present. What is frequency of is? 1. Similarly, what is the frequency of cook? What is the frequency of cooked? Cooking. Right? Are you following? Frequency is 111. So if everything is 1, how come anything can become important and something is less important? Cook is important or not? How do I decide it? Since cook comes from the family of noun, so if it is cook, it is noun. If it is cooked or if it is cooking, it becomes different word by adding ed and ing. Right? Ed becomes verb, ing if I put becomes adjective. So what do? I want cook, cooked, cooking to be represented as one word. Cook. How do I do that? Lemmatization. Have you heard of this term before? You should have, ideally. This has to be applied in order to get my root word. Now, what is the frequency of cook? 3 times. What is the fourth step I have to do? Arvind is a good cook. Fine. What is he? He qualifies Arvind. So he is Arvind. He cooked biryani. Arvind. His cooking. Arvind. Your choice. Individually, you have to do now. First, you tokenize, and then each word needs to be lemmatized. First, tokenize. Second, lemmatized. Third, now my Arvind also has a reference at 4 times. So what are the 2 important themes that I have? Arvind and cook. Okay, is this twice? Okay, make it twice. Does is make any difference? Is a and of. Now these are called as stop words. I can remove them. But what is important? Arvind is important, cook is important. If I put a parser, which type of cook Arvind is? He is a great cook. So the relation between Arvind and cook is great. Why he is great? What has he cooked? He has cooked biryani. So Arvind, great cook and biryani, if put together, defines the idea of this tweet. The sentiment is captured here. If a machine can do this, what I am doing right now, then the machine is exceptionally brilliant. What human does as a part of a common sense is the task which NLP needs to be performed. Because if you write 2 words, SAHIL, and then you write SAHIL, are these 2 words same or different? They are different for a machine. They are same for a human because the case is important. So please go back, refresh your NLP if you want to understand the higher concepts, because they are built to solve the problems which the statistical NLP was facing. What is the problem? What we are trying to solve? Why we need these complicated algorithms? Are you able to understand?
Just a quick info guys, Intellipaat offers generative AI and prompt engineering course which will help you gain proficiency in creating generative AI chatbots and other Gen AI tools, along with mastering the latest tools and techniques with hands-on projects and real-world case studies. And the best part, this course will be taught to you by IIT faculty and the top 1% industry experts. What's more, you'll be getting your generative AI and prompt engineering certification from Microsoft. With this course, we have already helped thousands of professionals in successful career transitions. You can check out their testimonials on our Achievers channel, whose link is given in the description down below. Without a doubt, this course can set your careers to new heights. So visit the course page link given down in the description below and take your first step towards your journey as a Gen AI engineer.
Now, when we talk about document classification, we basically are talking about text classification. Agree? Yes or no? When we talk about the text classification, what kind of scenarios can come? We want to classify or label the page. Sentiment analysis is also part of it. Whether it is a positive sentiment or a negative sentiment or a neutral sentiment. When you want to find anything in terms of true or false, same thing comes. When you want to identify defects, whether it is a hardware defect, whether it is a software defect, whether it is basically defects as in customer care. If I ask you to build a customer care problem, it becomes hardware, software issue, or it's a joining issue, or whichever issue. All of these things are basically part of text classification. The extension of text classification is chatbot. Okay. Now you will be surprised by how I can say it is an extension of a chatbot. So let's say somebody writes up in a chatbot a question. How are you? What is expected? Some answer is expected. Yes or no? Now, how does the answer comes? Step 1. We read the question. Okay. And we find the intent. Basically, if a question is given, in which category it comes in the category of greetings. This action is done using classification. Agreed? Yes or no? Okay. I have a list of lines, statements from user, and I have labeled them. It is a greeting, it is a good morning, it is good evening, it is a regular professional greeting, it is non-professional greeting, or apart from greeting, it could be condolence, it could be congratulations, it could be anything. So basically, I'm trying to identify a intent. Now this becomes my classification use case. So first step in a chatbot is you have to develop a classification model based on the data given, which helps you identify the intent of your question. Once the question has been identified as greeting, what you look, you search for all the answers which are present for greeting. Now you try to identify out of this, which one is going to be the best answer. This can be done using similarity. Now, similarities can be two ways. One is keyword and one is semantic. Got it? So all these things come under the family of document classification. So what we are going to do here is I'm going to show you how document classification can be implemented in NLP. And I'll be going through different techniques. First, I will talk about TF-IDF based or bag of words based techniques. Then I'll talk about embedding based techniques. I will use only word2vec. You are free to use other embedding techniques. Then third, I'll talk about LSTM based techniques. Okay. And then we will see how they are similar and how they are different from each other. Are we clear? From the agenda for first, whatever time we will make it to complete. So I'm going to use this file. I'm using the data uploaded in my GitHub repo. I don't need to load it here. I can directly load it from here. So this is how my data is. What is it? Candidate confidence, relevant. It is a sentiment analysis of Twitter. There is a text and there is a sentiment analysis done on this. Okay. So what we are doing here is we are capturing a filtered part of it, that is text and sentiment. So I have a tweet, there is a sentiment. Are we clear till this part? There is text and there is sentiment. This becomes my filtered data. This I have to use to identify whether it is a neutral, positive, or whatever category. Okay. Next step is we are trying to find the distribution. So when we see the distribution, we see there are 9,000, close to 8,000 cases for negative, 3,000 for neutral, 2,000 for positive. First of all, this is an imbalanced data set, but my idea here is not to teach balancing of a data set. The idea here is to learn how models are built. If you want to use a real-time scenario, you have to first do the balancing factor here. Okay. Now we are taking a sample of 1,000 data just so that the training becomes fast. Okay. So you can reduce it to 100 also, it will become even more fast. Okay. Now, if I see this, the final value of 100 is got exactly in a proportional way. I don't have all 1,000 coming from negative. I have equal representation based on their proportion from negative, neutral, and positive. Yes or no? One way of sampling is, since we have least number of values coming from positive, so what I can say here is take 1,000, 1,000, 1,000 from positive, neutral, and negative, and create a data set of 3,000 tweets and use that data set to do it, or take positive as a benchmark, 2000, and have all the tweets not more than 2000. So that is also another way of downsampling the data and making the data balanced and then start working on it. It is up to your preference. So are we clear till this part? Next, what we do here is we do the pre-processing. There is at the rate, RT, capital letters, small letters. Nothing. Your data will be, model will be biased. There is emojis. So what we do next here is we pre-process the data. So we convert all the text to lowercase. We replace X in the text. So we do all these things in a function mentioned here. Now and some additional code. So what we are trying to do here is we are creating a clean text where we are converting it into lowercase, cleaning all special variables. One thing we have realized here is there are still RT present, which makes no sense to my data. So what I'm doing here is I'm replacing my RT with blank, so that what my clean data set doesn't have any word called as RT, because it makes no sense. Cleaning is over, and there is much more cleaning you can do. The more you clean it, the better the results would be. Okay. For example, why do we need to keep the value of @real Donald Trump should by @Fox News? Okay. Next is the first approach, that is our TF-IDF based model. So how do we do our TF-IDF based model? Anyone is aware of how TF-IDF works? I believe you should have seen it once at least. You have never worked on TF-IDF vectorizer? Okay. So it's a vectorization technique. Okay, which emphasize on the rear vectors. So first step here is we import the TF-IDF vectorizer. Okay, this is step number 1. I'll just add one step and then I delete this. First step here is I import it. Okay. If you want bag of words, you should use count vectorizer. If you want to use TF-IDF, you should use TF-IDF vectorizer. Okay. Now we have to initiate the vectorizer. Okay. Now, if you will see in the vectorizer, there are a lot of features which are present. If you want, you can type here TF-IDF vectorizer documentation. Whenever you want to understand anything, just go and hit the scikit-learn documentation. It will give you all the possible features it has. So it has encoding given, input value, decoder error, lowercase, you want to keep it, it will automatically, you don't need to put the lowercase as a separate processing. Tokenizer, how do you want to tokenize? You want to use as a word or something else, stop words, token pattern. How do you identify a token? That means a word, whether it has a special character or not. Ngram, are you aware of Ngram? Are you aware of Bigram? Are you aware of Bigram? So if let's say I have a sentence 1. Sentence 1 says, I like data science. Okay. Sentence 2 is, I like social science. Sentence 3 is, I like machine learning. Which two sentences are ideally similar? In your opinion, which two sentences are similar? So, Bhumi said, sentence 1 and sentence 3 are similar. Perfect. I also believe it. But if NLTK has to identify, how will NLTK will work? It will split everything into a token. Okay. It will try to identify all possible unique values. So how many unique values are there? I'll put it in green. U1, U2, U3, U4. This is same. U5, this is exist, U6 and U7. How many unique words are there? 7, right? I'll just zoom in so that we are on the same page. Now, I'd say for sentence 1, sentence 2, and sentence 3, this goes from U1, U2, U3, U4, U5, U6, and U7. Now, what is my U1? I like data, science. This is social. This is machine, and this is learning. So sentence 1 was I like data science. So wherever the value exists, I will say 1. 1, 1, 1, 1. This doesn't exist. This doesn't. No 2 points. Sentence 2 is I like social science. Right? Are you clear with S1 and S2 marcation of 1 and zeros? Okay. Sentence 3 is I like machine learning. Okay. Point 1. Does it make a difference if I put social science and social has come? Can this equation captures what is coming first? Data is coming first or science is coming first? Social is coming first or science is coming first? The answer is position is not captured. Second thing is we are just taking the frequency here. Okay. Are we clear to this part? Now, if I have to find the similarity between S1, S2, and S3, how do I do it? How do you identify a similarity between two vectors? Are you aware of this concept? So I will find the cosine similarity between S1 and S2 or Euclidean distance between S1 and S2. Since it is text, I will prefer cosine similarity. If it was a numeric data, I would have preferred Euclidean distance. So text is preferred for cosine similarity is preferred for text. So we will use cosine similarity. And if I use cosine similarity between S1 and S2, I will get distance. Then I will find similarity between S1 and S3. And then I will find similarity between S2 and S3. Whichever similarity is best, I will consider and I'll identify which sentences are similar, which are not. Just think of, if you are not aware of cosine similarity, for sake of simplicity, just think of Euclidean distance as a distance calculation. It is basically a distance metric. Okay, I'll quickly explain because then we won't be able to cover our important topics. If I have two vectors, vector 1 and vector 2, if I want to calculate my Euclidean distance, I will calculate this distance. But if I have to calculate my cosine similarity, I will put a perpendicular over here, and this distance will be my cosine distance. So that means if this is the theta, if I increase the theta value above and I create a new vector, this vector, if put here, will always be smaller than this vector. So V3 to V1 is this distance. V2 to V1 is this distance. Which distance is bigger, D1 or D2? D2 is V1, V2. D1 is V1, V3. Which distance is more significant or more big? That is how cosine similarity works. Understood? You increase the theta. So if you make the theta 90%, what does it mean? What is cos 90? 0. What is cos 180? -1. What does it mean? If I have a vector v1 which talks about love, I have a vector hate which goes in this direction. Their angle between them is 180 degree. Okay. So if something is 90 degree, we call it orthogonal vector. Clear? Now, important part here is, if you look from a logic perspective, why model has to increase the theta? This is mathematical interpretation. When you put the data on a XY scale, your vectors are created like this. All vectors are representation, words are like this. If I have to find relation between this word and this word, I can put here, identify what is the distance between them. Model will not increase the theta. It is a representation of the data based on the corpus that will decide the theta. Yes? Okay. Now, coming to the main topic. If you think logically, S1 is more similar to S2 because the commonality between them is almost 3/4. 3 words are same out of 4. The commonality between 1 and 3 is 2/4. Okay. Are you okay with this statement? Commonality between S1 and S2, commonality between S1 and S3. The reason is because I am not calling them as one single word. This is 1 gram. This is also 1 gram. When I combine 2 grams, I call them as bigram. If I identify 3 grams, I call them as trigram. Okay. So if I have a sentence, these are the tokens I can generate. I like data science. Okay. If I say take all unigrams, but what if I'd say take all unigrams as well as bigrams? Then this will come along with this. I will also give this I like data science. This will be unigram plus bigrams. So based on how my data is, which I will get from my EDA, I will decide, do I need to prioritize my bigrams or not, trigrams or not. So there are ways in which you can quickly identify a bigram or a trigram, but whether it is required or not has to be a human decision. For example, somebody would say, you makes no sense. Yes, but thank you makes sense. You makes no sense. Thank you make all the sense. Now, if you remove the stop word as you, but if you have already identified bigrams and then you remove it, then this you will not get removed. So first step here is identify bigrams and then remove stop words. Are you clear? This step of n-grams decides how many n-grams you want to use. You want to use 1-to-1 n-gram, you want to use unigram and bigram, or you want to use only bigrams. For example, you are working in a healthcare or a very niche domain, some niche domain. You know that, or a banking, you know that if I have a word like trend, it makes no sense. You know that I need prefix to it. And this comes from experience. So I would need to know what is it an upward trend or if it is some other word is mentioned before it. Otherwise, I cannot find a difference between, I cannot distinguish between three different things just based on one word called as a trend. Trend is applicable in banking, insurance, healthcare, everywhere, social media. But trend is very prevalent when it comes to stock market. So where is this trend getting used is also very important, and that information can come using the concepts of bigram and trigram. So this step becomes very important. Are you clear? Okay. So this step means how much vocabulary I want to keep. It all depends upon how many unique words I have and overall I want to keep it. So what I'll do here is I will just copy this one, paste it here, and okay, sorry, already done. So not needed. So I'm just running this step. So this step once run, it gives me whatever is my size of the total document, which I'm going to use 1000, right? 1000. And this is a maximum feature. I am only getting 3579 out of 5000 based on my documents of 1000. So this is my DFIDF matrix that I have curated out of it. Are you clear till this part? Are we clear till this part? We have created a TF-IDF matrix of 500 records, and for each record, I have 3579 features. These 3579 features are like this features. Here I have 7 features. In this case, I have 3579 features. Okay. Now, we build a basic random forest classifier on top of it, and we print the accuracy. This part you are aware of. No need explanation on this part, right? So this is the data I have created. Using this data, I am creating text split, Y split, and I am generating the value. So this is how my data works. Basic ML model. Are we clear? Okay. Now, this is one way of building a model, also called as statistical ML. The next method is we can do word to vec. Yesterday, I told you word to vec can be used using GenSim. I'm not going to run this step because it's a very big model, takes time to load. But if one of you wants to load it, you can load it using this step. And you can see how much time it takes. Anyone wants to run, can run the step. So in this case, what we are doing here is we are loading word to vec model from GenSim, whose dimensions are 300. It's a pre-trained model. We are not training it on our data. We will be using this data to predict our data. Is it clear? Now, other than word to vec, you can use any other embedding model also. It is of your choice. But when you are using an embedding model, you need to first create your data set in such a way that embedding model can be utilized. Because what right now we have one model, embedding model, where every word has a vector whose representation is done in 300 words. How do I do it for my tweet? Right? So what I'm doing here is I'm creating a document to vector. That means whatever is my tweet, I will take my tweet, I will split my tweet into separate token. For each token, I will look into, I'll look into in my model where exactly is that word and what is the representation of that word. If that word exists, that means it is present in my vocabulary, I will take the average of the entire vector saved here and I will find that detail. I will represent this entire step in a form here so that you understand. This is the code. Okay. Now, what is happening here is, let me put the sentence. So this is my 1, 2, 3, 4, 5. Okay. Now let's try to see the working. At step 1, we load embedding model. So what do we get here? We get from a pre-trained model where I have word, and these are the dimension going up to 300. Are we clear with step 1? Let it be any number of words. Let it be 20,000 words. Right? It is a pre-trained model trained on some corpus. Second step, we split the word. That means if my sentence was I am splitting it like this. I like data science. Okay. Step number 3. I want to represent. What I'll do here is step number 3. I will check whether I is present in this word list. Okay. If I is present in the word list from 1 to WN, I will get back a dimension. Else I will get 0. Now assume if the word does not exist, then step 4 will come. This means word not part of this corpus. Okay. But if word is part of the corpus, what we do? We take this dimension and we have taken all the dimensions of all the words one by one, and we are taking an average mean of it. And what we are returning? We are returning the word vector for a document. So every tweet will get one vector as an output. This value will get returned. Are you clear? Mean would be average of every word will have a dimension. So let's say there was one sentence. We call that as one document. One sentence has 10 words. We will create embedding for word 1. We will create embedding for word 2. So on and so forth for word 10. So for this document, what I'll do here is I will take an average of this entire thing. And this average will represent this document. Okay. Now this step converts my data into vectors. So what I'm doing here is I am just showing you a couple of steps without running them because it is in memory. Let's say I'd write document as a subset of my data and I just take 3 documents out of it. So what are these? These are the 3 documents. That means 3 different tweets. So everyone understand what is document? Document is list of tweets. Okay. Next is I am taking my document to vector as a function. I am passing the value of doc and model from 1 by 1. So I am taking 1 by 1 each sentence, taking that value and passing it over here, and I am generating a array. So I will take 1 by 1 from the list. So a doc will come here. That is first tweet. I will pass this value along with word2vec model, and I will generate a vector out of it. Okay. I will generate vector out of it using this logic. So for if I have 1000 tweets present, so what I will get for every 1000 tweet, I will get one vector each. What is the dimension of vector? 300. So that means for 1000 tweets, I will get a 300 dimension vector. So overall, my shape is 1000 cross 300. Okay. Now I create my Y. What I do next here is I run my model on random classifier and I generate my result. Second part of the classification. Are you clear? That is vocabulary. I am not running the step. This is for the only for the previous one. These are I'm using pre-trained one. Have you tried running this step? How much time it takes? It is almost 1.5 GB model. It takes 5-10 minutes. That's why I'm not running it. To try it, you will see I am not running. I'm showing you the steps which I've already executed. So, are you clear till these two approaches? You have TF-IDF or you have Word2Vec. Now, third part is if you have to do the same thing using LSTM. I am really not looking forward for the accuracy because primary job here is to teach you how you can use these models. Accuracy is secondary. For that, other set of activities will come into. But are you able to build a model using TF-IDF and using Word2Vec? Are you able to do these two things? Can I say that this is my data, this is my embedding, and this is my model? So can I say this is my data, and can I say this is data and pre-processing? Then there is embedding, and then there is model. And can I say that this remains same and this remains same? I was using a random forest for all the both cases, and I'm using the same data setup for both the cases. It is just that in the first case, the input of the model was coming from TF-IDF. In the second case, the input of the model was coming from Word2Vec. The rest, everything remains same. So if you can just use these two different functions, you can switch between whether you want TF-IDF or you want a vectorized embedding technique. Because model remains same. Yes, it will be left to 0. So let's say your sentence is I like data science. And let's say data is not available, then you will get the vector for I, like, and science. You will take an average of it, divide by 3 or whatever, and you will get a final vector. Okay. Are you clear with this approach? Is it possible if you have to add a third embedding as glove or something else? Just keep the same structure, replace the embedding. Rest everything will be same. What will not be having impact on train? 0. See it. You are going to get a one vector for one sentence. That anyways you will get. If you have 2 words are also not available, for other 2 it will add and take an average. So you will be getting the words. If the entire sentence is not there, it will give you an error. That you to handle in error handling. But it is very unlikely that you will not be having at least one word present from the embedding because it is trained on a pretty large data set. It is 1.5 GB, 1.6 GB data model. So it is not just trained on 100 or 200 sentences. It is trained on probably an entire Wikipedia or on the Google News, which they have captured historically. So it's a pretty elaborate model. So there is very few chance that your words are not present here unless and until you are using a completely different language. Now comes the difficult part, that is LSTM. Now, if you have to do the same thing for LSTM, so what we do here is we take a subset of data. Again, we will get our X and Y. What we do the label encoding of our sentiment. We put it into 1, 0, and 2 category. And we process our data and do the test building. This is common. This is same as this step. Now for embedding and model building, LSTM is quite different. Why? We have to first establish these steps. So whatever you have seen so far from the LSTM example was a sequential data. The example that you have seen so far here is that there is a time series data. There is a time series data. And that data you are going to, this is your sequence, input sequence, and this is your output sequence. This is the model you have seen so far, right? And this model is coming from a data set. So you know the line input is fixed. Now the problem here is you are getting the data from Twitter. Your tweet 1 can be of 10 words. Your tweet 2 can be of 15 words. Tweet 3 can be of 3 words. Now, what should be your input size? If I say 15, what will happen to the rest of the 12? Is this a concern? Repeating the question. In LSTM, when we pass the input into the LSTM block, what do we pass? We pass and we define what is the size. If the input sequence was 4, we created 4 blocks for LSTM. If the input sequence was 6, we created 6 blocks for LSTM. But if this becomes variable, how will I define how many blocks I want to create? Now the text is not static, text is variable. You can write a long tweet, you can write a short tweet. Are you clear? For that, to make the size uniform, what we use here is called as padding. That means if I have a sentence, I like data science, and second sentence is I do not like data science. So this has 4 words, this has 5 words. So 5th word, I will just call it as dummy. Open. Now, this is what I have padded it with. So that size of this also becomes 5, size of this also becomes 5, but I know internally the last word does not exist, so that the design becomes uniform. That is what we are trying to do here. We will first identify what is the length maximum words. Then we are finding the length. This is my vocabulary. This is the size of my LS, the input string that I have to pass every time. Next here is we will tokenize. We will build a tokenizer. That means splitting of words will happen here. Then we will fit the word on our training data and we will create the sequences out of it. After we have created the sequence, we will add the padding on it. Basically, if I have to split all the steps, you have data, you have to curate the data. And while creating the data, first we identify the vocabulary, then we set the max token size or length, of my input sentence, and then I transform my training data based on these conditions. Fourth part here is, if the size is less, I maintain padding based on the maximum length sentence can have. That comes from this one. So if my sentence is of length small, that is 5, I will start adding the rest of the words as the padded numbers. So if I run this step and I just run the step to see how it looks like. So let's say this is the vocabulary that I am getting. First of all, step 68. Is step 68 clear? Don't focus on any other step. Just focus on step 68. Step 68 gives you the curated data. Is it clear? Okay. So we have curated the data. Now I'll come to this step. Model building. And I'll go back there later. No, 1 second. So at this stage, I have talk as an object created from the tokenizer. Then I have trained it on the text. So what are the things that talk will give me? It is going to give me a tokenizer. Tokenizer means whatever word is present in my corpus, I have found out all the unique words. Okay. And each word I have given a value. So if I say for each in talk dot word index item, print each. So what I'll get here is, for every single word, I have a unique ID. Basically, you can think of it as a label encoding. So as many words are present in my dictionary, I have in my total corpus, I have done it. So how many number of maximum word I will take it from the corpus? 1000. So if I see talk, I am going to find out the 1000 words from my corpus, and I will, I'm going to find out the tokenizer from the corpus for every single word which is present. Okay. So this is what I will get. Now, for every single word that I have, there is a representation to it. For example, I am saying real Donald Trump, its ID is 8. If I say AKA, its ID is 3216. If I say, let's say Trump, its ID is 6. So basically, every word is getting mapped with an ID. So the next step here is, if we take this word, so we have a word and we have its ID. Are we clear till this part? This is my talk object. Are you clear till talk? Next step here is, I take my talk and I train my training data and I pad it up. So I have something called as a sequence matrix. So if you see, what is my sequence matrix? It has list of all the input training data. Let's take one step further. Sequence matrix has sequences. So what does sequences have? It also has training data. The only difference is sequence matrix has padding data and sequence has normal data. So first we create the sequence which has list of training data, and the difference between this and this is it is training data which is getting padded. Now if I print sequence, what should I get? So if I print sequence, what should I get? If I say sequence 1, what should I get? This is my first training data. If I write sequence 0, it is first training data. What are these things? Numbers. What are these numbers? Okay, so the sequence data is represented in the form of numbers. Okay, if I have to regenerate this number, training data with invariable tokens. If I have to regenerate what this sequence 0 would be, for every number, I have to get back my word, right? So if I just find the word, I know the number, I can get back the word. Relation is mutual, correct? So I can always generate the sentence using talk. So this is the tweet I have got. Is this step are you able to understand what is the sequence matrix, talk, max length? It's very important. If you don't understand, you can ask the genuine whatever is the related question, we can discuss them. Are you able to visualize what is happening here? You have the data, every data has a unique ID, then you take the data, try to find and create the data in such a way that your input is in terms of the token ID. Okay. The reason we are doing it for the token ID is because it is the ID which is associated with the embedding. We will see it. So we have understood how my sequence matrix is. Sequence matrix is of the same shape, 850 by 150. Why 150? Because 150 is what we have set the max length. That is the dimension. You want to reduce it, you can reduce it. That's fine. Okay. Now this is how my sequence matrix is. It is having the values. These are all sentences. This is one sentence. This is another sentence. Basically, these are all the tweets. Okay. Now my data set is curated. All tweets are tokenized. I had 1,000 taken as a data, out of which I have taken train and test. Train is 850, 150 is my test data. And I have tokenized all my 850 input data. Now what I have to do here is, I have to pass this value in my LSTM because now it is everything is a number, and I will create my LSTM layers. Now, this is how we can create our LSTM layers. This is slightly different from how you have done. If you remember the first class last week that we did not have this layer was absent. We were taking the input, then we were doing the LSTM, and then we were doing the dense, and then there was an output. You remember this structure? In the previous class, this was the structure that we implemented. Input, LSTM, dense, output. Whatever we wanted to do, we were doing in this part. So after input, we were directly using LSTM. I could have taken a bidirectional LSTM, that is my choice. I could have added activation function, dropout, batch normalization, and then finally I will have a dense layer and output. These three I can add anytime, doesn't make a difference. But this is the structure I was using. Now, how does new structure is different from this structure? LSTM does not take input value. It takes input plus embedding value. So it will have an input layer. It would have a embedding layer. Now, what we are doing here is we are defining our first layer, that is input. While defining input, we are defining the size. Size is coming as max length, that is 150. Step number 2 here is we are creating a layer for embedding. That means every single word, I, like, everything has to go through the embedding, generate a matrix out of it. Okay. Now, what should be the size of the matrix? Maximum words. Maximum words are 1000. From up. 50. Input length is mentioned. And we are doing a dot product of it on input. So whatever is my input size, so I pass my first sequence. I take that input, I multiply it with a matrix, which is of this size. And I create a embedding matrix. I call it as EM. This EM will have some rows and columns as a dimension. Okay. Is this screen clear? Visible? What is happening here is, let me repeat. I have defining the max word. I have defined the max word. First, I define my input layer. What is the size of my input? This defines size of input. Okay. It depends upon what is the maximum length I am defining. That is length of sentence or a tweet. Make sense? Are we good till this part? All of you, please say yes or no. Next is, what do we need? Next step is we need to represent every word as a embedding. Embedding we have just learned. We want word to vec embedding. So what we do here is step 2 here is embedding. Now while defining embedding, what do I need? While defining embedding, I want to create a matrix. Okay. And I am multiplying it with my input. This is my embedding matrix, which will come from how many maximum words I have? 50. For the time being, just keep it 50. Is how I want. Is the another dimension I'm adding to it. Then input length, which is nothing but my size of my sentence. So my embedding matrix is a 1000 cross 50 cross 150. This is my embedding matrix. This I have to multiply with my input. What is my input? This is my input. What is the length of this? The length of this is 150. Because it is 150 same. So I have done multiplication and I have created, let's say, an embedding matrix. What is my embedding matrix? My embedding matrix is embedding layer multiplied by input layer. Okay. After I have created my embedding layer, I will put an LSTM on top of it. Okay. I have input. I will first do embedding, then I will do LSTM, and then finally I will do a softmax. This is how we designed. This is how we designed, right? How did we design our LSTM? If I have an input sequence, I will do embedding. It will give me a vector. This vector I'll pass into LSTM. Another LSTM. And finally, I got my output. What is my output? Hidden state. So what I'll do here is I'll pass this hidden state here. I'll pass my embedding matrix on the second input. This I'll pass it over here, then here, and let's say I got another hidden state. This hidden state I'll pass here. Third input will come, but before it comes, it will go through embedding layer 3. So on and so forth. I will get my final output. Yes or no? This is how I do it when I was saying my encoder, decoder, or whatever I taught you. This is how the steps were. The difference is when you learned the basic LSTM, this layer was not there. We were directly passing the input because it was a numeric data. But when it is text, this layer plays an important role. If you have a numeric data, you have text data. The difference is if I pass input, I can directly pass it to LSTM, which will give me the hidden state. But if I'm doing for the text, if I have input, I have to first give it to the embedding. Embedding will give me the output. I'll pass it to LSTM. This will give me the hidden state. Are we clear in this part? Are you able to understand difference between numeric and text? If you are using this one, you will pass input layer, LSTM, dense, and output. If you are using this layer, you will have input, embedding, LSTM, dense, and output. One layer will get added. But this layer is a bridge between these two layers. Yes or no? This is also a matrix. This is also a matrix. So 99.9% of time, your code will fail at this layer because the size will create a havoc. It is very easy to run this code. It is very difficult to run text code because embedding layer is a bridge between input and LSTM, and the size, the dimension size creates a problem. 10 out of 9 times, this is the problem that happens. So it requires a little bit of tweaking, checking the shape of your embedding layer at every step if you see an error. So in this code also, if you observe, we have created an embedding layer. Then again, we are following the same stuff. And this is my final model, which I am returning. So if I run this and I show you the summary, I have an input layer of none and 150. Then I am doing embedding between 150 to 50. 50 is the dimension size of my embedding. 150 is my, sorry, it's a 3D one. Let's assume 50 cross 1, none cross 150 cross 50. Assume that way. Then I am passing LSTM with 64 LSTM inputs. Then I'm creating a fully functional layer of 256 neurons. Then I'm doing an activation. Then I'm doing a dropout. Once I do a dropout, after this step, my number of neurons will come down. And this is my output layer. Output layer, I am going to apply another activation function to convert my output into probability. If I look back and see what are the steps, input, embedding, LSTM, this is nothing but creating, fine-tuning my LSTM. Then I have a final layer, output layer, and I'm passing it through a sigmoid or a softmax function in order to generate my model. So this is the model I am generating. I should have preferably used here as a softmax. And here I am compiling the model. So we have just reached on training the model. This is where the model training has ended. Next part is still pending. How do we use this model? But are you able to understand how training happens? Yes, it will be 3D. As you go to the encoder decoder, you will understand it in more detail, all the dimensions. Everything will come at a specific time, but everything has a meaning. So the dimensions I'm going to explain more in detail when we reach to encoder decoder. Here, just try to focus on layers. If you have understood the layer and not understood the shape, I'm okay. Fine. That's how it has to be done. Understand the layers, not the shapes. Shape will come later. But always remember, shape is a problematic area. So you might find issues in the shape. But at present, if you want to run it, the code will run perfectly fine. But are you clear with the shape, the layers? This is what is called as building a LSTM model. After this, it is just like compiling and training the data. Okay. So before going, we learned how do we build a classifier in LSTM, right? So how do we build a classifier in LSTM? We have input. We decide what is going to be the max length of my every sentence. Okay. Then we do a pre-processing on curating the data set. When I say curating the data set, that means we have to convert all the sentence into the fixed length. Then we pass this into our LSTM block. The internal working of LSTM block here is we take the sentences one by one, pass it through embedding layer, then passing through LSTM and generate output. This entire thing is our training step. How do we do training? Same model dot compile. Okay, this is how we train the model. Is model training clear? Is the model training clear? Anyone has any questions on model training? This is trailer. What will happen when we learn encoder decoder? So expect more complexity in the next part of the discussion. So far what we have seen here is it was very easy when we were doing machine learning modeling. Why? We had the data. We curate the data. When I say curate, let's say we impute the value, we transform the value. Okay. Then we build the model. Now, when we take the testing data, what was the flow? We will repeat these steps again. Impute will happen, transform will happen, and then we will do the predict method. Yes or no? Right? Now, same thing has to be done, this prediction in the terminology for prediction is called as inference. So when we say in inference part, what is the step one? Take the testing data or take the predict data which has to be predicted. Second step is curate it. When we say curate, that means do it the same way you have done it for training data. Why? Because the size, the dimension and the size should match. Why? When we are putting the data into model. Now, these are the three steps which is part of my testing or prediction pipeline, that is inference pipeline. Okay, so going with this logic, what we will do, we will tokenize our sentence using TOK. We will pad it, our sentences, and then we will use this data for model evaluation. Clear? Okay. The other way of writing the similar code, if you find this code difficult, we have the another simpler way of writing the code here is we define the vocab size, we define the maximum length, we define the embedding dimension, and we create the LSTM model like this. This is much simpler as compared to this one, but this one gives us options of adding complexity in our model, whereas this way of writing will not. But if you are starting, this is the best way of writing the model. You initiate using Keras. You define your embedding layer where you define your vocabulary size, embedding dimension, and the length, 3-dimension, right? Then you add the LSTM. In that you add dropout at recurrent dropout. You can ignore this value, you can keep this value, adding a sigmoid function and then a loss function. This is another way of writing LSTM code, which is much simpler, but has other limitations. You can't add attention mechanism to it. You can't add encoder decoder design to it. So the other representation of that model is using this type of syntax. Is this syntax easy? Are you first following it, or is it very confusing and you have not understood anything? If this is the code, if you will see, this is clear over here. Embedding dimension 50 is represented like 100. We are defining the model. Then we are adding the embedding layer. Embedding layer is nothing but this layer. We are defining the input length. And then we are using the input length. Sorry, we are applying the LSTM after embedding. And then whatever is this entire thing, like I said, is nothing but your fine tuning of LSTM and dense function. So in this ways, you can add activation and all those things inside this. So this is complete Keras based. Completely encapsulated. So you can use either this way or use this way. Are we clear? So if somebody writes bracket, layer and all those things, don't get confused. It is same as this. Only the structure of code is different. Add is doing whatever the layer is doing, this add function is doing. Getting it? Slightly nuanced differences are there. Now, now why are we learning all this? Again, the question comes. I'll tell you briefly why. The end goal is to learn BERT. Okay. In order to learn BERT, you need to know how transformer works. Okay. In order to know how transformer works, we should be knowing a couple of things. One, encoder decoder, attention, and transfer learning. Yes, the encoder decoder can be learned only if you know LSTM. Attention will work and will come if you know LSTM and also you know NLP. Context is important. Transfer learning is a framework. You will understand transfer learning if you understand the concept of language modeling. Now the challenge here is when we talk about the NLP, there are certain things which we should be aware of. When we talk about NLP, we should be aware of parts of speech. we should be aware of how English grammar, our normal English grammar, that is some sentence verb agreement is. We should also know about our statistical NLP, that is TF-IDF. We should also know word-to-vec and glove-based embedding. If we are aware of them, then only we will be able to understand the structure of a transformer. Otherwise, transformer cannot be understood. So, while learning transformer, it became clear that this part is not clear for most of you. So we had to do a deep dive on this part. Are you clear why we have spent so much time understanding this part, whereas this is not part of a transformer? Are you clear where we are with our learning plan? So all of you know now what is tokenizer, what is splitting of data, what is embedding. So if I roughly use these terms, it is not going to now, what are the problems that we have faced so far? One, we have faced a problem whenever we are dealing with NLP. The first problem here is we have to tokenize. Okay. A word can be familiar, a word can be unfamiliar. When I say familiar and unfamiliar, that means a word is present in my history. If it is unfamiliar, it is a new word. I have no idea. I have never been trained on it. This is part one. Part two, once we have tokenized. Once we have tokenized the data, that means a sentence has given to me and one of the sentences in German, Polizei. Now I don't know what that word is. Is it a police or it is something else? How do I represent that word? A word which is not known to me, because if I just take it directly, it will become zero. It will become unknown word. But can I find a relatively similar word to it? That is the point. Right? Let's say you are writing a sentence and you got, or some people write these kind of things. How do you tokenize them? They are not part of any dictionary. Or some people write great. Is this a word? These ones I can't do anything, but can I do something for this one? Can I check out the root for it and replace it with the root and say, okay, tokenize, this word should be tokenized as great. Yes or no? Ayana bol bhai. Yes. So this is my problem number one. Not lemmatization. Lemmatization is there, but tokenization itself. Tokenization. When I'm reading the word and I'm saying, how do I deal with the token? Second problem we face here is embedding. Okay. There are different types of embedding. First, we have TF-IDF and back of words. Then we have word-to-vec. Then we have glove. And then we have something like LSTM, where we are encoding it using Keras based inbuilt embedding. This inbuilt embedding is something which we will be doing it in transformers also. Okay. Now, what we have understood in this part, the position of the point is not something which is always getting maintained. This is another challenge we have observed. Now, in order to move to the next part, that is the transformer, we have to understand how encoder decoder works. Okay, so let's take the theoretical concept into consideration and Let's start understanding the transformers now. So first thing here is transformers has two parts. One is encoder, one is decoder. Clear? It has, this is your encoder, this is your decoder. In encoder, there are components. What is a component? You have input, you have embedding, you have positional encoding, and then you have self-attention, then you have normalization. No, we are assuming we understand that part. So this is fifth one. Sixth is feed forward, and seventh part here is this arrow. The name of this arrow is called as skip connection. Now first start with understanding what is skip connection. So if we are you guys aware of VGG? Are you guys aware of what is CNN? Convolution neural network. What does it do? Are you guys aware of pooling? So if I have an image, 64 cross 64, I have 3 channels. Now I have to do a feature map. That is right. Feature map happens in convolution. 3 cross 3 kernel. Right? This image will work on this one. So this would be probably 64 cross 64 minus 3 is 61 plus 1 cross 62. That would be the size of this image. 62 cross 62. Yes. If I apply a 3 cross 3 filter on 64 cross 64, I will get 62 cross 62 image. Yes. If I apply max pooling on top of it, what will happen? Let's say 2 cross 2 max pooling, I do it. So this image will reduce to half. 31 cross 31. Yes. Okay. So if I have a CNN, I do another CNN, then I do a max pool. Then again I do CNN, then again I do CNN, and then again I do max pool. So if I have an image 512 cross 512, and if I'm following these steps, will the information will increase or decrease? As I'm moving downwards, it will decrease. Yes. Those who are confused why it will decrease, think of this logic. The image always decreases once you apply CNN and max pooling. Okay. Information will decrease. Image will be compressed. So if let's say this is my one block and this is my another block, and if I have 16 such blocks, my image will get compressed quite a lot. That is what VGG 16 is. It has such 16 blocks. Okay. The reason I'm saying VGG 16 here is because a lot of concepts that we learn in the transformer comes from the idea of convolution. Transfer learning was first developed for convolution neural networks, and then we used it across everywhere. Are you clear? Now let's say I have data. Okay. Are you guys aware of Chinese whisper? So this person gets the input. He will tell in his ear. So one person will tell the other person in their respective ear, and this person will give me the final output. Are you aware of this game? So what information this person gives is always with the information is always compressed. plus it has noise, and which you can call as error associated to it. Imagine this is your one CNN block. This is another block. This is another block. This is another block, another block, another block. So when you pass this information, finally where the information reaches, it becomes very compressed. So a new network was created called as ResNet, also called as a residual network. What does it do here is when you are passing here is it also skips two blocks and passes original information also. So at this stage, original information is also coming and processed information is also coming. And from here, this also. No, if your information is getting compressed, that does not mean noise will get compressed. Noise means when you have values which are not part of the data, but they are present due to some assumption, due to some transformation that has happened. Okay. If you upscale your data, noise comes. If you downscale your data, noise comes. Certain things get removed, meaning gets changed. Okay. So this is called as skip connection. When you pass the information directly as well as in a processed way also. Taking this concept and let's say we have NLP based task. I am passing, this is my input. I am passing my input here, LSTM. It goes here, hidden state is given here. Now this, at this step, it has some assumption what my T1 was, input at T1 was. And this is T2. T2 does not know what T1 is. Whatever the value of T1 is, it is coming from hidden state 1. At T3, whatever is there is coming from here. So if my size increases, and let's say I have reached to 100th LSTM, the information which is coming from the T1 have no impact by the time it reaches here, or if the impact of this will end by here itself, right? Because it has passed through two of the sigmoid functions which are present in LSTM. One sigmoid will kill it, other sigmoid will make sure that it becomes very significant small. So mathematically, after two steps, the input of the first step is less. So what if I pass at T4, I just not pass my T3 hidden state. I pass for T4, I take input from hidden state 3 and something which is two step behind me, that is T4 minus 2. So any input at T4 will come from my previous hidden state and input coming two steps before. So this will give T4 more knowledge about input. Yes or no? Noise is may present, may not present. But original information is not something which will come. It is a combination of original and new information. Because you are applying you are taking both the information. See, it's not a human, so you are getting an input stream, which is actual data. You are getting a hidden state stream, which is coming from previous steps. Now their plus function is going to work. That means two vectors are going to get combined, concatenated, or if you think from a wave point of view, this is one wave, this is another wave. We are going to do a convolution. So there will be a new wave which will come. Now this wave may have noise, may not have noise. Generally speaking, when you do convolution, noise comes down. Noise doesn't remain there. That is the property of convolution because it takes the intersection of it. It will park this path like this, and that is how convolution works. Okay, so noise is not the issue. Issue here is, am I able to up the data in such a way that it is not compressed to so much level that original essence is lost. So this is called as skip connection. Okay. This is step number 7. We will connect all the dots once we have seen. So let's start from the step number 1. Step number 1 is I have passed my input. Then I will do embedding. Are we clear till this part? Input is passed through embedding. And that embedding goes through positional encoding, and then it goes to attention or self-attention. Now, in order to proceed, first let's try to understand what is self-attention. Then only we will understand what is the purpose of positional encoding. We kind of understood what is attention. We studied attention. We understood that in order to, if I have encoder, so we will create one mechanism over here for hidden state. Okay, that's how we learned that for attention mechanism, if I want to know what is happening, what about G2, G2 will take the input from G1. It will also take consideration of how G1 is associated with all the hidden states. Then it will find the similarity. So now you understand how similarity is found using cosine similarity. Okay, and that will tell me which hidden state is more relevant to G2. So when I am trying to understand how she is to be inferred, she is most likely is associated with what? Let's say the similarity with H1 is the highest. Then we say that she is taking, the G2 is taking input as she and is in order to create the hidden state out of it. That is next limit. So this value depends upon these two. Got it? You remember yesterday we discussed it in detail that attention mechanism, if I have to analyze any hidden state at a decoder I have to rely on previous hidden state and all the hidden state from encoder. Then I have to compute the similarity. So how do I do it? C of I is alpha I of j, h times j. This is my hidden state. This is my similarity. What is it? This is nothing but my soft max function. You remember this? This is my attention mechanism. Yes or no? Now we have to learn what is self-attention. So self-attention is quite different from attention. Okay. So the self part of the self-attention refers to the fact that the weights are computed for all hidden states in the same set. That means in self-attention versus attention, in simple words, I have to say here is, in attention, I am calculating my GI with respect to all the edge. In self-attention, I am doing it at an encoder level. So I am saying the weights that I have to compute for self are with respect to itself. That means if I'm writing a sentence, I should be knowing which sentence at an encoder level as an input sequence has which word has significance which associated with which one. Are you getting the point? Example, if I have to give you, I will say, first of all, give you one example. My input, if time lies like an arrow. My next sentence here is fruit lies like a banana. In my sentence 1 and in my sentence 2, this is my input sequence, not the output one. My flies is associated with which word? Clear? Makes sense? In my second case, my flies is associated with banana. Why? The flies is a fruit fly. In this case, flies is with respect to the time. In this case, my flies is an insect. In this case, flies is not an insect, it is a verb. Sentence 1, sentence 2 is clear? Sentence 1, sentence 2 is clear. So what happens at my first layer here is, in the multi-head, within the multi-head, what is happening here is, I have an input. It is passing through an embedding. From embedding, we are passing it through an encoder. Encoder has two parts. First is self-attention and other is fully connected layer. Okay. Which we also called as feed forward neural. This layer, what does it do? It helps Is this line clear? Can we say in layman terms, we are trying to develop relation between input words. Can I say that time is flies is associated with arrow based on subject verb agreement? Time, flies, and arrow are related with each other based on subject verb agreement. When I say relation, what kind of relation we are talking here? A word 1 can have a subject verb agreement with word 2. Word n can have a adverb based relation with word j. There are different relations, or one word can have multiple relations with another word. Is it right? Is this information required or not required? If understood, help me understand. Why do we need to know the relation? Because of the context. So imagine I am writing a paragraph. This is my sentence 1, sentence 2, sentence 3, sentence 4, and sentence 5. I need to understand, if I'm using some context here, what is its relation with context mentioned here? For example, I start the communication with Siri or with conversational AI. I say, hey, I need to book appointment. AI will say, which appointment? I'll say, okay, book it for haircut. Then AI will say, where? I will give a location. Go to X place. They'll say, this is booked. X place for 4:30. Now AI will say 4:30 is not available. 5:30 is available. AI is saying 4:30 is not available. 5:30 is available. And nothing else is present. How do I develop the context that what 4:30, what 5:30, what is he talking about? Because as a human, I have a chain of thoughts with me. But as a machine, every single input cannot, if taken as a single input and no historical information is there, it is difficult for a machine to behave. Yes? Are you able to understand this problem? Are you clear? So if I have a long context window, self-attention helps in understanding the relations. Now there can be multiple relations in play. How do I evaluate all the relations? I can have multiple self-attention on the same input, creating multiple relations and maintaining that entire information. Yes or no? I will have multiple self-attentions to find multiple relations. This concept is called as multi-head attention. Is it making sense? Now, there is a way, mathematical way in which attention can be calculated. We will come to that later. So, in technicalities, we say that the multi-head attention helps the model to focus on different positions. This provides us multiple set of informations. When I say information, everything in data science is a matrix when it comes to information. This information is fed to linear function, which is called as feed forward neural network. Okay. So I have an input, embedding, encoder, self-attention, feed forward. If I do self-attention multiple number of times and then pass it to feed forward, this entire block will become multi-head attention. This is done using three vectors, Q, K, V. Query, E, value. Let's say you have imagine you are at a supermarket, okay, and you are buying all the ingredients you want to need for the dinner. So you are at a supermarket and you want to buy ingredients for dinner. Okay. In order to make the dinner, you should know what dish you want to prepare. So you should have dish. If you have a dish, you need recipe for it, how it is prepared. So let's say this is with you. Okay. So you have the dish recipe and each of the required ingredients can be hot. Whatever is the ingredients which is required for the recipe. Salt, pepper, can be called as query. Okay. So you have the dish recipe and each of the required ingredients you can assume to be called as query. Now you have gone to the supermarket. What will you do? As you scan through all the products which are listed there on the supermarket, you are going to look for where can I find salt. So how do you find it? You will look for the label for salt. You know you need salt, you need to find salt, right? From a supermarket. Now, when you look at the labels, you can assume these labels as, and you check whether they match an ingredient on your list. So you are going through all the labels. So there are keys. There is salt, there is sugar, there is pepper, there is pepperoni, there is so many things. So one by one, you take the key, you will check it with your query where it is going to get matched using similarity function. So this is key, this is Q. So you are going to do a dot product of Q and K. So, and whichever has the highest value, you will get the similarity function of that. If you have a match, then you take that item. If let's say Q and K is giving you a good match. So whatever is this value product, you will take that value. This is called as a value from the shelf. Are you clear with QKV? Q is what you are looking for. Key is your embedding. You will multiply Q and key. And if this function gives you a good value, whatever is value associated with the key, you will fetch that value. That is how attention works. Attention works with Q, K, and V. So once you are using Q, K, and V, it becomes very important to know the position, input position also. To maintain the input position, we use position encoding. Nothing else, no fancy thing other than knowing the position. So coming over here, is this part clear? Then we move to the embedding. We maintain the position of our words. in input sequence. Then we pass it to the attention. This will give me the all relations, list of relations. Then we normalize the data. Why do we normalize the data? The weights are updated here and training becomes easy and simple. Then we pass this value to feed forward and again normalize. And whatever we have done, we are going to skip function so that whatever decrease in the knowledge has happened, we are going to pass that information again. This is where our encoder ends and passes the information to decoder. Is encoder clear? Position knows where the input sequence is. This has Q, K, and V. This does not. This only ensures where the position is. This step is also called as residual. And you should be aware why it is called residual, because it is coming from residual network, which comes from CNN. Are we clear? Shall we do a quick recap? Okay, so you have a sentence. Now, the first step here is we do encoding. The first step here is we do embedding. In order to do embedding, we should be knowing tokenization and embedding with us. Now, each word has its own numeric value. Okay. Then what we maintain here is we assign its position. Its position is 1, it is 2, it is 3, it is 4. So we know the order in which the words are present in my input sequence. Okay, this is my positional encoding. Then I pass this information into an attention mechanism. Attention mechanism will give me a list of relationships. Okay, for example, data is associated with science, like is associated with data science, I is associated with like. Okay, all these relations are maintained. Okay, data and science are related, that means it is a subject. Like data science is where you are defining your adjective for a noun subject. I like is noun subject is related with adjective. All these relations are identified. Now I cannot humanly feed this. This is not humanly possible. So what we do, we assume if I take 100 combinations on this, or 8 combination, let's say this is how BERT is built, then all possible combination will come through my calculations. So this I am going to fetch if I am taking all possible combinations. Once attention mechanism is done, we pass it through the normalized layer, and from normalized layer we do feed forward neutral network. What is the purpose of normalization? It is same as batch normalization. It reduces the training time and it understands the volatility to minimalistic. But the thing is that we are struggling to finish the basic LSTM structure. So the code is quite complicated. It is with me, but I want to first understand it at a theoretical level. Because the way we use it, we don't use any of these steps. We directly call the BERT. We directly call the GPT. We don't write these steps when we are trying to write the code. Okay, so you have input, Input goes to embedding. Embedding goes to position encoding. Position encoding goes to multi-attention. Multi-attention go to normalization. Normalization goes to feed forward neural network. In between, if you want to increase these blocks, you have skip connection. So this is what happens at encoder level. Taking this input and decoding the output using exactly same steps is called decoder. Okay. What happens? We take these values, the output of the top encoder, the final top. See, encoder is nothing but encoder layer has list of encoders, list of transformers, or you want to say. Then it goes down into decoder part. You take the final most encoder, and then what you get, the output of the top encoder is then transformed into an attention vector K and B. We don't use Q. Q was our input value, which signifies our ingredient. I don't want ingredient. I know what it is. In the decoder part, I use only the key and the value. And then we have the series of steps, which are almost similar to it. Okay. The last part here is applying the softmax. The softmax in any function is applied only to get the probabilities. Okay. This entire thing, one single unit is called as transformer architecture. If you want to write it from scratch, you have to write class for everything. And I can show you that code also. You have to write class for every single component. And then you have to add it together. This is method 1. Method 2 is you can use Hugging Face. Hugging Face has created a generic transformer library, which you can use in order to import. So what happens in Hugging Face is we can see both the methods. I don't have any issue with them. The only thing is you will find it very hard to understand. It requires a lot of mathematical coding. So if you see the Hugging Face, are you aware of Hugging Face? You are aware of Hugging Face. So in Hugging Face, we directly use the model. So what we do, we use the model, we import the tokenizer, we import the model which we have to use. That means predefined weights. If you pass any token, it will give you the output. So Hugging Face offers us multiple models. And once you have the model, we can use the tokenizer, we can use the model, and we can build our own product. So it has in NLP different categories available. You want to do summarization, there is summarization. You want to do text classification, there are models for text classification. It defines what is the size of it, how many people have downloaded it, and how many people have liked it. All these information are available. You want to use a specific model, you can just type BERT. You will get the model also. Now there is a BERT which is based on Indonesian sentiment analysis. There is a uncased. There is a fine-tuned on spam detection on SMS. So you have BERT for medical, BERT for finance, BERT for everything. Okay, so there are different people who uploads these models, and the rest of the folks use them. Okay. So if you click on any of the model, it will tell you how many have been downloaded. So if you want to compute it, it gives you the accuracy, and you can also click on files and version. Here it will give you the model. You can download this model and you can use the weights. Okay.
Just a quick info, guys. Intellipaat offers generative AI and prompt engineering course, which will help you gain proficiency in creating generative AI chatbots and other Gen AI tools, along with mastering the latest tools and techniques with hands-on projects and real-world case studies. And the best part, this course will be taught to you by IIT faculty and the top 1% industry experts. What's more, you'll be getting your generative AI and prompt engineering certification from Microsoft. With this course, we have already helped thousands of professionals in successful career transitions. You can check out their testimonials on our Achievers channel, whose link is given in the description down below. Without a doubt, this course can set your careers to new heights. So visit the course page link given down in the description below and take your first step towards your journey as a Gen AI engineer.
Now, in transformer, transformers is again, you have an encoder block and you have a decoder block. Once transformer came, and transformers was built by Google's paper. What was the name of the paper? Attention is all you need. So if anyone is interested, can read this paper. From here, encoder decoder architecture of transformer came, which extrapolated the performance of my models. Yes or no? Then came the two branches, BERT, and then came two branches. So BERT was encoder based and GPT is decoder based. Okay, so BERT was encoder based and GPT is decoder based. That means it takes whatever is an input, only uses the decoder module to provide my output. And BERT is encoder based. It only takes the encoder, whatever value it gets, it just uses that value. Yeah. So in the BERT, if you will see the full form, it is bidirectional encoder. Okay. I'm looking for the GPT. So GPT is generative pre-trained transformer. So that means whatever you are using, you can use a default encoder, but the decoder part will be used for getting the output. Now using this, we have different use cases. Okay. The third family of here is which uses both encoder and decoder. You can call that as BART or T5. They use both encoder and decoder architectures. This is in general how architectures is split. Okay. Now BERT has been advanced. It has a lot of new variants which are available. You don't need to do it, but still, if you want for just for knowledge purpose, you can explore that particular section. Now, in this entire case, where does Hugging Face comes? Where does Hugging Face comes? You are aware of what is Hugging Face? Are you guys aware of what is Hugging Face? So what did Hugging Face did? They built the Hugging Face built the library where they actually formulated or standardized transformer. If you have to correlate Hugging Face and this entire thing, what is an equivalent of that in machine learning? You can build your own KNN. You can build your own decision tree. You can build your own random forest. But you can also use SQL. It gives you a direct implementation of decision tree, random forest, or KNN. Right? So your decision tree is nothing but a concept of decision tree. which is called as cart, is same as transformer, and sklearn is same as Hugging Face. Are we good to this part? Now, is it not a repo of models? It's a not just repo of models. Before Hugging Face came into the picture, there was nothing called as import transformer. Okay. When Hugging Face came into the picture, they first outsourced import transformer to all of us, which speed up our work. Before this came into the picture, everyone was writing the logic for transformer individually. So that created a kind of an imbalance in the system also, because I cannot use someone else's transformer because that would have a different dimensional size or something. Now, whatever advancement you see, which is BERT, GPD or everything, is inherently they use this transformer as a base model. Then they build series of transformers, and how the relation of one transformer is related with the other defines their uniqueness. Second thing which Hugging Face offers is a platform where anyone can host its model. Hugging Face also offers a platform where you can use it for your own inference purpose. So let's say you have an organization, you want to use an open source model, but you don't have the GPU with you. You don't have GPU with you. So what you will do here is you will go to the Hugging Face, you will take its service, and whichever model you want to take, you will use it only for inference. You don't want to train the model. You don't want to put data into the model. You just want to use it like an API. That is also doable and possible. Are we good till this part? It's like Keras on top of TensorFlow. What's GPU plus here? GPU plus, this is not equal to. GPU is graphic processing unit. If you don't have a graphic processing unit, you have to run the model on CPU, that is centralized processing unit. The way the models are built, GPU can be used as an accelerator. That means it fastens your training process. Colab has TPU, GPU, whatever you want to call that, they have these tensor units available. Okay. If you want to train your own model, like your own BERT from the scratch. Now, next part is, the reason I'm focusing on here is because this is the area where most of the people have confusions. They misrepresent one word with the other word. Now, we got the transformer. On top of it, we build multiple transformers, stack them together, and we call that as BERT. Okay. Now, BERT has multiple transformers, not just one, it has series of transformers. Let's say it has 12 transformers used inside a BERT. This is my hardware. Then I need corpus. Corpus is text. So I took the text, I used the hardware, I trained my text onto this hardware, and what I generated is a model. Correct? Are you able to relate with it? I have data. I am training it on a BERT, and I'm generating a model out of it. What is BERT? Stacked transformer. Are we good till this part? Now, what others did was they changed the data. This was the normal text data. Let's say, what is it? Unpublished books. So what another person did, he took the financial data and he used BERT and then created a model, called it as a FinBERT. Another person used medical data, trained on BERT, called it as a BioBERT. Similarly, you got a lot of BERTs available to you. Are you able to understand till this part? We got a lot of pre, and this is called as, and they were finally called as pre-trained models. Now, let's say Jaya is a developer and Jaya wants to use BERT in financial domain. So what Jaya will do here is Jaya will take a pre-trained model and load it in his space. Okay, this developer will load it into the personal space. When I say personal space, I say its own AWS account or the laptop. Now, either you use this directly and get your output, whichever is your, whatever is your use case, you want to use it. So what are the two things it can provide? Any model that you take will provide a token and will provide a embedding. These are the two things any model will provide you. After that, it is up to you. What do you want to do with that embed? You want to do a classification, do classification. If you want to do NER, do NER. Whatever you want to do, you can do with that model. The other flavor is that the boss of Jaya says, our output is not coming good because this was trained on investment data. We have core banking data problem. So can I train my model on top of whatever is my finance BERT? What if I put my data, personal data, and train it? This process is called as fine-tuning. The reason it is called as fine-tuning is I am not building it from the scratch. What I'm saying here is whatever finance BERT model I have, pre-trained model I have, just add a couple of more layers where the data gets, the model gets customized to this data. So if this is my BERT, which has series of transformers, what I'm saying here is put another layer, which is my personal data, and then train it on here with the help of a loss function, readjust the weight. Understood? So I have three different problems to be solved. So first thing is I can use, okay, first is I directly use only BERT. Then I can use pre-trained BERT, which is specific to a domain. Third is I used the pre-trained BERT, which is on domain, and I add my personal data. This process is called as fine-tuning. People often call this as training of BERT. This is also sometimes people loosely call it as training, but actually it is fine-tuning. So don't get confused that somebody says, I have trained a BERT model. Nobody is training this. Nobody is training this because it requires TPUs. It requires TPUs. Most of the companies do not even have GPUs. How will they get TPUs? TPUs is tensor processing units. Advanced version of GPU. And the kind of hardware that is needed, it is simply not affordable. And the amount of data that is needed is simply not available. So what people do here is they take the domain-oriented models, add their own personal data, and then they get their final model, which they use for their custom application. Is the picture clear? This is difficult to write. You want to use this or this, it is easy. What is the difference between first and second problem? Does that mean that the model in the first problem is yet to be trained? This is BERT. It is built on generic data. For example, unpublished books, which I mentioned. There is a process to fine tune. I'll first show you these two parts and then we will come to the fine tuning part. Now, how does BERT work? That is important. We have understood how LSTM works. We have understood how transformer works. We will see how BERT works. But before we go into the how BERT works, let's discuss couple of things where it will get used, because that understanding is more important, isn't it? Now, what are the applications of NLP? What are the applications of NLP? I can teach you BERT, but where will you use it? Is that a question? You want to use BERT in recommendation system. Okay. Forget about BERT. Let's talk about the basic NLP applications. Understanding the context of the text. What is the application? The first application which most of the people use is called as classification. I have shown you an example of classification based on LSTM, right? Now the subset of classification is sentiment analysis. What is classification example? I have a data. These debates can be held later on WhatsApps. I have a data. I have to predict this class. This is my normal classification model that I have seen in machine learning. What changes in text? In text, what we are trying to say here is, if I have this document, document 1, document 2, document 3, what is the class of this document? Are we clear? Are we clear? This is the first one. What is the second one? Second one is summary. Summary means I have paragraph. I have to get 2 to 3 lines out of it. Okay. In today's world, people are doing summary, all these things using OpenAI. Okay. I'm not against them, but the problem here is that is not a feasible solution across board. So how does summary works? In summary, there are two categories. One is extractive summary and the other is abstractive summary. In extractive summary, what we do here is we take the paragraph and we extract a couple of lines out of it. These lines are within the paragraph. I am not creating anything new. Whatever is present, I am only finding what is the most significant line. Now, how do I find the most significant line? I can use different approaches. This is usually comes under the statistical analysis or statistical NLP. One such method I can tell you is sentence ranking. I can split my paragraph into sentences. How do I do that? How can I split my paragraph into sentences? How do I split my paragraph into sentences? Can you hear me? Sentence embedding, no. Embedding means vectorization. I am saying splitting. So in NLTK, I can split word into a sentence into words. Correct? NLTK can split paragraph into words. Those words are called as tokens. Are you aware of it? Okay, search it. You will get it. Now, you can also split the paragraph into sentences. That is called as, the first one is called word tokenization. The second is called as sentence tokenization. There are other ways or methods where you can tokenize a sentence itself. No, not sentence to vec. You are not vectorizing it. You are just tokenizing it. So if you say my name is Shiv Kumar, full stop. I live in Bangalore, full stop. I work in XYZ company, full stop. I like to learn about data science. These are the 4 sentences. So what you want to do here is you want to create a list in which my list number 1 is my name is Shiv Kumar. Second is I live in Bangalore. Third is I work in XYZ company. Fourth is I like reading about data science. So when you create a list of individual sentences, yes, so you are splitting with respect to full stop because that is a sentence. But what if you say my name is P. V. Shiv Kumar? Then are you going to split at P. The answer is no. So we can't just split at the full stop. We have to understand whether it is a sentence or not. So either you write your custom way of writing it or you split it. Are you clear? The issue. So that is why it is good to use a library to tokenize your sentences. Now, once you have tokenized your sentences, in this one, if you have to find the summary, each sentence you have to rank it. How do you rank it? You try to identify how many of the rest of the sentences are pointing toward this sentence. Okay. I'm just giving a theoretical concept. You can try and work it out on a mathematical way also. That means you can try to find each sentence association with the other sentence based on cosine similarity. And that will give you the sentence which has the highest cosine similarity with the rest of the sentences. In that particular order, you will figure out which sentence has the highest level of understanding. The reason I am focusing on explaining you this is because if you use the latest OpenAI, you can get a summary in one line. But if I ask you, can you customize it? The answer would be no, because it is how it is. Agreed? So let's say I have a paragraph, and now I have tokenized it. This is my sentence 1, sentence 2, sentence 3, sentence 4, sentence 5, 6, 7, 8, 9, 10. These are 10 sentences. Are you following it? So I will create S1 to S10, a matrix. This matrix will have the value. Value will come from cosine similarity. So I can see which sentence has highest cosine similarity numbers crossing the threshold with respect to the others. Let's say this sentence is important. So this will become my highest ranked sentence will be this particular sentence. Make sense? But what is the problem that I can face? The problem that I will face here is, which we discussed last time also. You remember the last time the cooking problem? What was the cooking problem? Arvind is a great cook. He loves cooking. You remember this problem statement? He cooked biryani or pasta, whatever you like. What was the issue that we faced in this problem statement? Problem statement we faced here is this: he represents Arvind. Now that similarity between this and this could be high, but because this is not resolved, what does he refers to can become a problem. So while doing this summary, the one of the step here is to resolve pronoun. But that is not an easy method, because if you take a larger sentence, in the paragraph 2, if I have a reference on paragraph 1, how do I resolve it? This is my paragraph 1. This is my paragraph 2. This is my paragraph 3. And this is my paragraph 4. Let's say these 4 paragraphs are your appraisal or your feedback from your manager. Are you following it? Assume this is the feedback given by your teacher, manager, whoever, your parents, in your whatever you want to say. So 4 paragraphs letter has been given. Are you okay till this part? Is there a possibility paragraph 4 has some references to paragraph 1? Is it a possibility? You are praising your person here, you are giving the criticism here, and again you are ending with the praise. So there is a relation between praise in P4 to P1. Now, when we talk about the previous concepts, whatever we have done, the issue that we face here is, what if I find 3 sentences from this entire paragraph? The chances that they are related with each other is less. Very less. They have randomly figured out 3 important sentences. Second, we don't know how they will start and how they will end. So first issue is coherence. If you do a statistical way of summary, the coherence is bad. Because pronoun resolution does not work, I am picking the sentence based on its rank. The contextual continuity is not with me. Right? Second thing is, if the context is large, I anyway cannot create the map of how this entire paragraph is written. So what I have to do here is I have to split my letter into multiple parts. That will also use the context. Okay. So these are the problems which we faced in the statistical summary, and the solution was abstractive summary. So what does abstractive summary says? Abstractive summary says you have taken the entire paragraphs 1, 2, 3, and 4. Rewrite all of them in such a way that all 4 are represented, but in just one paragraph. New paragraph. This paragraph is not from here. This is completely new or augmented. Are you following it? It's just like a story. Abstractive summary. So but still the base of the new para is the other 4 para, right? Yes. So what it does here is, when I say new part, it will try to use a synonym. It will try to find the central theme of all 4 and merge them into one. The example of this summary is, if you have seen InShots. Have you seen InShots news? It gives you the brief summary of the entire news. Okay. Now this can be done using LSTM. How you will do it using LSTM? You will have an input data. This is my P1, P2, P3, and P4. 4 paragraphs. Okay. And this is my new paragraph 1. This is how my data is. This is the data, and this is how my summary should be. This will become my encoder, and this will become my decoder. And if I build this encoder to decoder, I will be able to create a model which, if you pass an input, will give you a summary. And it is very complicated to build, let me tell you honestly. Everyone finds this complicated to be built. So what we have learned so far here is, in all industry, the basic applications is 1, classification, that you will use everywhere. Second, you will use summarize capability. Everything is built on top of it. So what is the third most common application everyone see in their industry is chatbot. Like I said, chatbot is nothing but how a classification model works. If the answer is mixed, you summarize it. You first identify what should be the type of answer you want. Okay. Fourth is NER, name entity recognition. That means if I am passing a text, can you identify what are the values in it? For example, if I pass a text like this, HDFC Bank has reduced the repo rate by 50 points. This will impact of the lending capability, and this will impact the lending capability. Let's limit to this point. If this is the section I have written, what does NER says here is identify the entities which are important from a banking point of view. So what are those identities? HDFC Bank. What it will say, it will call it as an organization. Then it will say repo rate, or repo rate will be different. 50. Okay. Then impact lending. Lending is nothing but loan. Now these are important entities. How do I identify them? So we have a framework called as a SPACY. SPACY has NER enabled. If you don't want to use SPACY, you want to use a custom, then you can build your own custom NER. You can use SPACY, you can use transformer architecture or LSTM or anything else. But this activity is important. Understood so far the applications of NLP? Fifth is topic modeling. Topic modeling says if I have a corpus, can I identify what are the key themes the corpus is talking about? That means, let's say you work in a company like as Infosys. Okay. You want to identify whatever data I have across all accounts. What are the important themes they talk about? You will do something called as a corpus analysis. This, if you want to use, there is a framework called as GenSim. GenSim enables you to do LDA. LDA can be done to use the topic modeling. Are you clear with the applications part? These are broad applications. Now we are coming to how does BERT help us to solve them, or Hugging Face. All the things that I have mentioned have challenges. Some of the challenges I have mentioned, some of them I have not, because it will take a lot of time to go through each and every topic to explain the challenges. But mostly what you can see, the challenges are same. The first one here is context is missing in all places. Second, ambiguity is there. Okay. Ambiguity is not just in terms of pronouns, but all possible. The meaning gets convoluted. We are not writing the sentence in a proper way. A lot of assumptions have to come. Prepositions are not fixed in nature. Grammatical mistakes can happen. Spelling mistakes can happen. So ambiguity is there. Context is missing. And third is the volume. If I increase the volume, that is the size of my input, the things changes. Now this volume is still a problem because even with the new tech stack that we have, like a BERT or GPT or GPT-4 or the new model that has come, ambiguity means when you are not clear. Ambiguity means when you are not clear. The example that I gave you was animal wanted to cross the bridge, but it was tired. When I say it was tired, it refers to animal. If I say it was narrow, then it refers to bridge. But what if both the words are same? That means if I write something like this, sheriff or police, you can say, was running after a thief until he was shot. If I just write this one, then what he refers to? Sheriff or thief? It can be anything, right? He can be sheriff as well as thief, isn't it? Sangari Yalla Babu, isn't it? Now this is called as ambiguity. Now, if I try to handle it using an old method, I won't be able to do it. I need advanced methods, and that is why I will use transformers. Okay. Let's take few questions and then start. Questions? Do you have any question? He, she still has all the ambiguities. Yes, a lot of things have ambiguities. Pronouns are the biggest problematic area when it comes to NLP. Context get lost over the period of time. That is another problem. One word can have two meanings. If somebody says, I have lost my years getting my hair silvered. If somebody says this, I have lost a lot of years of my life getting my hair silvered. That means he's talking about experience he has gained throughout his life. At the same time, if someone is saying, I got a silver medal, he's talking about an accomplishment. Somebody says he was born with a silver spoon, then it will become probably an adverb. So the word silver can get used in different contexts in different places. So it gets little ambiguous when you do a rule-based mechanism, lexical mechanism, then it gets difficult. So advanced methods can help us in these categories. Okay. Okay. So nobody would be, if somebody asks you about how do you build a chatbot, this we have covered last time also. The inherent principle of chatbot is to identify a intent. So when I say intent, that is, how does a chatbot works? Somebody asks you a question. How are you doing? Now, what you need to do here is step one. You need to check if this value, what exactly is the intent of this question? Okay. When I say intent, that means, is it talking about a greeting? Is it talking about something else? Is it a query? Is it a greeting? Is it just a statement? Then if it is a greeting, what type of greeting it is? If it is a query, what type of a query is it? Is it a health query? Or is it a banking query? If it is a statement, what do you expect from it? Now, what we do here is we have a step two. In step two, we already have a data with us. Okay. Different data are with us. If it is a greeting, this is the data that we take. If it is a query for health, this is what we take. If it is a query for banking, this is what we take. Now, what do we do next? We check. First step is we identify from the intent what it is. So intent model will hit it, identify. Okay, it is greeting. If it is greeting, it will point out to this place. Then whatever is my text, which is known to me, I will compare my let's say this is G1, this is G2, this is G3. I'll compare G1, G2, and G3 against my question. I will check the cosine similarity between them. If this has the highest cosine similarity, I will take whatever is my output, is my response. I will put that response into. I will put that response into as my output. So let's say the response is, hi, I am good. How about you? Or the response is, I am good, thank you. Or response is, I am not well. So that response will get captured. So what is happening over here? A classification model is over here, which identifies it. Then there is a mapping between which category it is. From there, we identify the response, and then in between we do a cosine similarity, which is basically embedding match. So if there is an embedding which is getting matched, cosine similarity, responses. So this is how we build a chatbot. But if you have to make it in a proper way, then you have to write a lot of things associated to it. But from an interview point of view, the question is to be answered in this way. Now your chatbots can be of two categories. One is generic chatbot. Second is directed chatbots. So if you will go to any bank, HDFC Bank or any other bank, what do you see? You get a question, and in response, they give you answers. Answer 1, answer 2, answer 3. You need to select one answer, then only the next set of questions starts. These are called as directed chatbots, where you know that you will answer only in one specific way. It is a story-based chatbots. Generic here is the one I have shown. Directed is pretty straightforward. What do you do in directed here is, you say whatever is my question, I can have these category of answers. For example, if it is a bank, if you just write hello, what I will say? I will say 3 answers. Do you want core banking? You want loan? Or you want credit card? I am not going to give you any other option. You will say core banking. Then I will say, okay, do you want core banking? Option 1, option 2, option 3. Option 1, I have another set of answers. For 2, another set, another 3. In that, whatever you select, let's say you select this one. Here again, I will have 3 options. This one, I have 3 options. Like that, I have created a map. This you can build using a Python-based dictionary. One dictionary calls the other dictionary. Is it clear? Okay, so now the question here is, if you have a problem statement and somebody asks you, how will you build a chatbot? What is going to be your question number 1? What will you ask to the interviewer back? If he says, can you make a chatbot? Type of chatbot. What is the type of chatbot? Are you going to make a generic chatbot, or is it going to be a directed chatbot? In a generic chatbot, do you want it to be based on learning, or is it static? Okay. How do you decide whether you need a directed chatbot or a generic chatbot? If I have to make a chatbot, most of you will be working in some organization, right? Every year, this time we have to file tax. If I need a chatbot, which is to be built by the finance team or the tax, should you be make it generic or directed? Should you be making it directed or directed? So not every time people require Google. Most of the time, directed will work fine. In directed, you can make hybrid also. That means you don't give the options, you give options. You also give user a chance to write question outside these options. That question, that will make it a hybrid chatbot. So these are the different variations first you should clarify. Then you should design your chatbot. Now, how do you improvise? Final step suggestion might become generic, correct? What do you mean by final step suggestions might become generic? Generic is you can ask anything. You open a chatbot for the entire company. They can ask about HR, they can talk about leave, they can talk about tax, they can talk about promotions, they can talk about outings, they can talk about anything, cabs, meals, whatever you want to ask. Directed is when it is very specific to specific set of questions. Hybrid is in that specific set of questions, do you give them the option to write a query which is not part of your. Okay. So you have to first understand the hierarchical order of making a chatbot. Okay. Now, I will talk about BERT. Okay. So if we see this one, can you see this slide? BERT is a transformer-based architecture which includes transformer includes encoder and decoder. However, BERT uses only the encoder part. The encoder part of the BERT has multiple layers, that is usually 12 for BERT base and 24 for BERT large. These layers are of self-attention. So if you see the transformer architecture, it has self-attention. The transformer, if you are using it for BERT, you will only use encoder part and you will use 12 layers. Okay, this is the basic design requirement of BERT. Okay, are we good till this part? The key concepts in BERT which we have to understand here is, first is it is bidirectional in nature. Bidirectional means, yes, it means we are not using the decoder of transformer. We are only encoding the value. Okay. Second key concept is bidirectional. That means same what we have understood from the LSTM, that the model is trained on a bidirectional concepts. That means if you are passing any input sequence, it will be read from left to right and right to left. Okay. This has to happen. Next part here is, after bidirectional, BERT has two important concepts. One is MLM and another is NSP. LMS is masked language model. So BERT is based on the concept of masked language model. NSP is what is going to be in my next sentence, predicting my next sentence. So BERT trains on these two ideas. These two ideas is what is used for BERT's training purpose. Okay, we will indulge more into it, what each of them is and how it works. So far we are clear. We have BERT built on transformer, only the encoder part. It has bidirectional in nature and it has two important concepts. One is called as masked language model and second is called as next sentence prediction. MLM means if I have a statement, okay, the sentence here is BERT is a pre-trained model trained on transformer. Okay. Now what happens in the MLM here is, MLM will take this input and it will mask some value. It will say BERT is a pre-trained model and this information will get masked. So what happens in the training process here is, BERT will try to predict everything which has been masked. Now, what is the advantage of doing this? Advantage here is I don't need a labeled data. I will take an actual data, make 10% of the data as masked or redacted, and then ask model to train on it and predict these values. And then I will see how these values are predicting better. Are you able to follow it so far? So how does BERT works? BERT says take input data and take 15% or 10% or whichever percent you want to keep and replace it with a mask. Mask means redact that token. Then you ask the model to predict this masked value. Before training and testing only itself, you first mask it and then you do the training testing. Yeah, you're right. You can do that. So the thing here is we are trying to predict our model on masked data. Okay. Now, how the prediction is achieved? What we do here is we add a classification layer on top of our encoder model. Whatever output I get, what I do here is I multiply the output vector with the embedding matrix, transform them into the vocabulary dimension, apply a softmax function, and I get a probability. This probability helped me apply the classification. Just to make things simple, what we are trying to do here is I have an encoder. We get the input statement. After my masked data, I will put another layer called as a classification layer. I predict the output, apply the softmax, and generate the output. This output I check with my actual data and say, okay, I am doing X amount of percentage. That is good or bad, whatever it is. This is, BERT is also called as MLM model, that is masked language model. It is also a language model. Will it mask based on the importance of the word or it will be random? It is random. Masking is random. The next thing that BERT does is, along with MLM, it does NSP. NSP here is, it will take the pair of sentences and it will identify whether the next sentence is associated with my first sentence. So what it does here is, during the training, 50% of the inputs are pair, in which the second sentence is subsequent sentence. In the, 1 second. How does NSP work here is, we have, let's say, 1,000 sentences. We will split it into 2 parts. In first part, we have sentences where first sentence and second sentence, if passed in the pair, they are actually related. In this part, when we pass 2 sentences, they are not pair. This is how we try to train them. You remember in the summary part, I said we face huge issue because there is no coherence between sentences when we generated the summary. You remember it? So NSP helps me identify if my 2 sentences are related. MLM identifies what is going to be my next word. The purpose of MLM is to predict next word. The purpose of NSP is to predict if my next sentence has coherence with my first sentence. That is, it is associated with my previous sentence. We train both of them together, reduce the loss, and that is how the model is built. How do we do that? We create a CLS token, that is the start of the token inserted before the start of the first sentence. Then we use a separated token to identify end of each sentence. A sentence embedding indicating sentence A or B is added to each token. Sentence embedding are similar in concept token embedding with vocabulary. Positional embedding is added at each token to indicate the position of the sequence. These things become inherent part of my BERT for getting trained. This is how the working works. Are we clear to this part? BERT is trained on transformer. We use multiple layers of transformer. When I say multiple layers, I mean to say we use multiple layers of self-attention mechanism. After that, how does it get worked? It has two aspects to train. One is MLM, that is language model part, which predicts the next part. Second is next NSP, that predicts the next sentence. NSP's purpose is to find out the coherence between two sentences. LM's part, language models part, is to predict the next word or a sentence. Based on this, we build our BERT model. So if you will see the BERT PPT from Intellipaat, you will be able to relate with all the concepts. We have covered it. It has 12 layers. It has 24 layers. Is there anything that we are missing? Okay, CLS and separated. Okay, fine. We are doing it. Let's understand the basics. I have a model. Somebody raised the hand, or it was a mistake. You have an encoder. You have a decoder. Question number 1. If I use only encoder, what does it mean? I have input. I have done embedding. I have applied attention. When I say attention, it is self-attention. And then I get my output. I put a classification layer on my output, and I will get an output in terms of a word, or in terms of a class, or in terms of something. Yes or no? Vector got classified now. After I got my vector, here I got my vector. I used the softmax on top of the vector, and I got my output. Right? Now, question 2. What will happen if I have passed my input and then I'm going to put it into a decoder? Decoder will start generating the output. Right? Now, if I have a use case which requires classification, which requires name entity recognition, I will go with BERT. That is, I will go with encoder model. Why? Because whatever is my input, I am finding out final output as single entity. This can be done only using MMAST language model. Are you good till this part? But if I want to generate, if my use case is generate output, just generate. If I have given input as some string, what will you generate? For that, we use GPT. GPT means decoder based model. Why? How does decoder model work? Decoder model works by saying you have passed your input once. After that, it keeps working of its own. Input is passed only once. Input can come from encoder. Input can come from human. Doesn't matter. Once passed, decoder starts generating the output. So if you will see, if your task is completely generative oriented, the idea was to use decoder based model, that is GPT. Now you see chat GPT and all those things, but if you will ask the folks who are from the previous generation, for them GPT means decoder based model. So there is a funny story. Some friend of mine asked me, do you use chat GPT? I did not heard the term chat. I just heard the term GPT. I said, no, I use only BERT because I was working on classification and NER. The friend was talking about how chat GPT works. I heard the term GPT. I said, no, I'm using BERT. So he got confused because my friend was from a different domain. He said, oh, there is another model in the market which is called as BERT. And I got confused what he's saying. And then I realized the question was chat GPT, not the GPT. So that is how the tech lingo got confused between the tech jargon that we have. Are you able to understand what is encoder and decoder? Now, does it mean that GPT cannot be used for classification? Or the encoder cannot be used for the generative purpose? No, they can be used. They can be, but purpose of a decoder is to generate. Purpose of encoder is to have a classifier. Now, if you reroute it again, and again, the classifier can also be, see, anywhere if you have a language model's purpose is to predict the next word. If you do it in a repeated way, you can generate a sentence. If you don't do it in a repeated way, you can only generate a word. Once you generate a word, you can use it as a class. You can use it as an entities. Now, at what stage I will use encoder and decoder? When I have an input and I want a specific output. And that use case is summary. And that is why I said, if you want to take a hybrid approach, then the models names are BART, T5, etc., which are completely encoder decoder based. Now what we will do here is we will learn how to program them in 3 different ways. Pay attention, there are 3 different ways. One is if I want to encapsulate everything, use direct Hugging Face library. Second, we will use simple transformer. Third is if we have to use BERT based transformer. You will automatically understand the difference between if we use this one, my complexity get encapsulated. When I say encapsulated, that means you are only going to make a call, you will get your answer. You don't need to worry about how it is done, where it is done, how do you train it. You just call it and it get done. Okay. Are you good to start from the programming point of view? You go to your labs, generative AI, you open BERT 101. Okay. First, I'll show you the Hugging Face. If you open the Hugging Face web page, you can do a login. There is 4 options. You can click on the models. Okay. Are you with me till this place? Now it offers a lot of services. What is the services it has? It offers you classification, question answer, token classification, text generation, summarization, translation, lot of things it offers. So let's say we want to do the summarization. So we click on summarization. Okay. So a lot of models are present. You can click on any of the model. Let's say I click on the Google Pegasus model. Okay. Now it talks about a lot of details. What is it? What are the docs associated to it? What are the files which are present for it? What does the community is talking about? You can do that. You can see on which data set it is trained, how it is performed. All these things are available to you. It also tells you about the data that it is trained on 1.5 instead of 500K. The model uniformly sample a gap sentence ratio 15% to 45. All tech details are present. You want to use it, you can just pass any input over here as an example and compute it. It will directly give you an API to run. Whatever input you will pass, it will give you the summary. Okay. Now you can pass any input. Let's say I want to talk about any input on, you can pass any input over here. Okay. I think I have used some information and use it over here. So this entire thing is about global warming. I will paste it here. So you can pass your own input and you will get an output of it. This will tell you whether this model is up to the mark, whether you want to use it, don't want to use it. Now, when you are running it somewhere, it is getting run. So Hugging Face hosts all these models. And based on the availability, you will be able to use it for free of cost. If you don't have money, if you don't have money, you can do it in this way. But if you have money, you can take a pricing service where the same model can be used on a faster instances and you can use them directly. So it is more like a chat GPT version for you. Can you see this? You are getting the entire thing talks about how climate change is working, but in a small, concise way. Can you see it? Yes or no? Okay. Now this is your inference API. Okay. This is your inference API. You don't want inference API. If you want to deploy this model somewhere, you can deploy it by having your own space in the Hugging Face. If you want to use directly in the collab, then you click on the use this model, libraries transformer, click over here. What do you see? You see that you are defining the model which you want to use in two possible methods. One is using pipeline or other is you load the model directly. When you load the model directly, there is a tokenizer and there is a model. Okay. This is how you will load tokenizer and model. If you click on the model documentation, you will be able to see the piece of code that you can use for this specific purpose. So you can give an argument, you will tokenize the argument, you will create the summary of this argument. So this is how you need to navigate in the Hugging Face in order to see which model is what. I will repeat it again. Please take note of it. If you go into the Hugging Face model, you can select any model of your choice. I have selected, let's say, in summarization. I have selected, let's say, Pegasus XM. Last time I checked Daily Mail. You can check how the output is using inference API. If you have money, you can use it using your pricing. You will be able to understand. If you don't want to do it, you can directly go to the transformer. You can take the model here. Most of the rest of the steps will always be same. So this is how your documentation will open. From here, you will copy paste your output. Everything remains same, only the model inputs have changed. Okay. These are the things that we can do. Right. Next is if you want to train the data on your own data set, you can do it using auto train. Again, it's a costly. One second, any QA or NLP might have pre-trained using. If I need to train specific example in Hugging Face Q&A, I need to train my own manual PDF data and get points. See, you want to train, that's what I'm saying. If you want to train all your data, you can use auto train. You can also train the data using what I have explained here. That you can do it using training of your model. All three things are possible. It is up to you what you want to achieve. Okay. So this is how we can use it. Now let's see how basic BERT works. I'm going to connect, but I'm going to change the runtime to T4 GPU. Okay. The first step here is from transformers, I'm importing BERT tokenizer. And here I'm going to mention the name of my model. You can use any model of your choice. Okay. If you run these steps, it will start loading this model. So if you see here, it is loading and it will showing you how much is the how much is the size of the model which is getting loaded. So it is going to be runtime load. Whenever you are running the Collab notebook, you need to run this step every time. So it takes lot of effort because it is not saved somewhere. Okay. So we have loaded the model. Are we good till this part? Loading of model. Yeah, there are spell corrects are available. Easily available spell corrects are there. You can do that. Spell checker. All those libraries are available in Python. You can build your own spell checker. Now, what does these steps means? I'm just trying to teach you the steps. So 101 is your CLS. Clear this. And you are ending at 102. That is your end of the sentence. So 101 and 102 represent those tokens. Now, once you pass this text, Chat GPT is a language model developed by OpenAI based on the GPT. So what exactly is happening here is we are creating the tokens. Okay. Now, if you want, you can try something like this also. I'll come to it later. Now, if you want to convert it back and see how the tokens are, you will pass your encoding into the tokenizer and it will give you the token. The first one is CLS. The 24705 represents CHA. The thing here is there is no word as Chat GPT present in the vocabulary of BERT. So what it is doing here is it is splitting the Chat GPT into 4 tokens. CHA, #T, #GP, #T. Okay. This is called as it is CLS. That's what I said. Now it starts with CLS, it's end with the SCP, end of sentence, and SCP is 102, CLS is 101. It is the initial token, right? Now, whichever word it does not have, it will try to identify what is the closest word it can take. So OpenAI does not have is not present in the vocabulary of BERT. So it will split OpenAI into 3 parts: Open, A, and I. Open, BERT is aware of, A and I is not aware of. So it will take A as an individual character, I is an individual character. It will just append 2 hash to it so that it does not become a single character here when you are breaking it up. So this is A, this is capital A, open by. This is how the tokens are built. So this is the for how when you start with your project, or start with the BERT model, if you could use a tokenizer and encoder, this is what it happens behind the scene. So are you clear what happens behind the scene? If you want to run the model, I'll come to that part. Just so your dictionary comes from the model that you are using. If you want to change the dictionary, you have to change the model, but you cannot change the dictionary of the model. So it depends upon which model you used. If you used uncased, a different set of dictionary will come. If you used cased, different set of model will come for you. Everyone has a different. So when you see 8 billion, 9 billion, 10 billion, that is why billions of parameter makes a lot of difference. Are you able to relate now? Otherwise, one BERT model would have fixed everything. Okay, fine. So my tokens is done. Now, what if I have to save the model? Okay, what I'll do here is I am giving a path. Okay, I'm giving a path of collab notebook. In that BERT full. Okay, I will just delete this folder. Okay, cannot be deleted. So what I'll do here is I will just use _1. Now what I'm doing here is I'm saving my tokenizer as BERT paste. That was the name. I'm saving a tokenizer. I can also save the model. I can save everything like this. Dot save pre-trained over here. So a new folder will get created in this particular folder, where I can use it. So if you will see, it will have all the files which are available. So if I run the step, and if I then run this step, I will be able to create a new path. Now, this is where you can use it directly if you want to run it from your local machine to have safety or other things. Then you are not hitting the Hugging Face. You are directly hitting your path. So that means if you want to run the tokenizer now, you can directly use here the new tokenizer from this particular path. You have to change this path. Okay. Are we clear till this part? These are the libraries that you have to import. Not necessary. I have not run it. I have just kept it. I was testing something. Now, if you want to run transformers, there are prerequisites that are needed. That is, torch is needed. Why? Torch has either you have to use TensorFlow or you have to use Torch. They provide you the framework under which you can call transformers. Okay. Initially, TensorFlow was a bigger player in this game, but most of the new, I think I have not seen TensorFlow in the latest amount of time anywhere getting used much. So Torch is something which comes from PyTorch, needs to be used. In Colab, you can use it directly, but if you want to use it on a local machine, you need to identify which version of Torch is suitable for you. So you need to see that. So what you're doing here is you have to say PyTorch installation. So it will open this page where you have to define which build you want. You want a stable build. Is it Windows? Is it Linux? Is it Mac? You want to do a pip install. You want to do a conda install. Which install you want to do? Which is your language? You want to take a default. And whatever options that you select, you will get a command which you need to run. Is it clear? If you run it locally, are we good till this part? Okay. Now, the first thing here is we have to run the model. Okay. So I will just run this model and I will parallelly talk about the steps. I have installed the model. This is the basic text I want. I have copied this entirely from here. Okay. If you want to use Pegasus XM, I have used Pegasus XM. You can go to Pegasus XM. Here you can go to use the model, transformer. You can use these models. You can go to the documentation. We'll tell you what do you need to write. Okay, this is what I have copy pasted here. Okay, now what are the steps? We need to define the model. Step number 8 is we need to define the model. Are we good till step number 8? Are we good till step number 8? Import. This is the text. I said it is the input text. Now, this is the text you want to pass. You can change it. Where it is different. You can write, my name is Sahil also here. That is okay. 3.3 apostrophe does not make any difference. You can write it anyway. I have written it in a different way. So this is not important. This is just the way you write it. The important step is this one. What does it means? Okay, let me just go through this step and then we will come to your question. First step number, this is model. Okay, this is the model I want to use. This step specifies, do you have GPU? Is your GPU aligned with your machine? Can you use GPU based model or you want to use a CPU based model? This step will take care of identifying whether you have to use CUDA, you have to use CPU. That means whether you have to use GPU or whether you have to use CPU. Step this number 10 here is, we will download tokenizer from our Pegasus. We will download a model from our this model. So what we have learned so far here is, I will define my model name. Then I will get the tokenizer for this model name and I will get a model of this model name. If I change the model name to daily and something else, Pegasus X daily and all those things, I have to first get these two things installed. That means they should be moved to my device. Device means, in this case, RAM or cache. That means it should be up and running. Are we good till step number 10 and 11? It is same as what we have done for BERT cased. Now we are doing it for Pegasus XM. Are we good till this step? The way we have downloaded the tokenizer, we have to download the model also. Okay. So whenever we are, first step is, we go to Hugging Face, we identify the model. Second thing is, we go to Collab, we load model. Now, alone model will not work. I have to also load tokenizer. Okay. Then third step would be, in Collab, once I have loaded, I want to use it. So how will I use it? I will pass my input into tokenizer. I will get output token. I will use that into a model. That is what I'm doing here. Okay. I'm taking the model name. I am using it on a device for identifying CPU. Do we need step 8? Yes. Can model name be passed into step 10? Yes. It's a variable name. Definitely you do that. Okay. Now we have passed our tokenizer and model. What we need here is, we have to pass our input data, okay, into the tokenizer. These are nothing but the steps. These are nothing but the parameters for my tokenizer. Nothing fancy in it. Whatever is my input data, after tokenizing it, I will pass this into the model and use the function generate, and it will give me the answer. So this might not be clear. I will do the same thing by breaking it. So this is, let's say, my input. Okay. And this is what I'm getting is my summary. How do I get my summary? I'm using the model.generate. Sir, where we set the safety filter? Which safety filter you want to set? Where is the safety filter? Okay, we will come to the next text. Let's say this is the text that I have to pass. Okay, What I will do here is I will convert it into the text, which is in the form of a list. First step here is I will first convert it into a tokenizer. I'll again split also this part, create a new step. So we will convert it into a tokenizer. So my input has been converted into a tokenizer as a part of the tensors. This is my attention mask. This is my final output. Okay. This is how it works behind the scene. Okay. Now my tokens have been identified. My input IDs is what I need. Attention mask is not what I need in this case, and labels also I don't need. Okay, I don't have labels, so fine. Yeah, attention mask is this one. So this is my input I have passed. This is I have tokenized. If you don't, after that, I have to pass this tokenized one into the model.generate, and it will generate my final output. The United Nations framework, convention on it will not happen in this way in this case because we are using directly. It will take care of it. Everything will be taken care behind the scene. Okay. So internally, when it is passed, it will mask it with 101, end with 102. Everything will happen, but it will happen behind the scene. You are not supposed to do it. You are not supposed to take care of that part. Everything happens behind the scene. You are only making a call. You pass the input, you get the output. So this is what we are talking. I said that the first theorem is directly Hugging Face library. Everything is encapsulated. You don't need to do anything. Easiest way of using BERT. Similarly, you can do it for text generation also. So if you will do it for text generation, you will get some output. Now for that, I have used this one. You can try any of these models. So this is how you can do for text generation, machine translation, whatever you want, you can do it. That's the easiest way of using BERT. You can use BART, T5, whatever you want. You can save it on your hard disk or in your collab, and you can use it. Are we clear till this part? It's a model name. Somebody said, can we use directly step number 8 and 10? This is how it is done here. We are not giving the model name separately. You can use any model. You go here and check which model you want to use that model. Are we good? Okay. Now we will come to the next part of our learning. That is, how do we do it using simple transformer? That is little bit in detail. Let's say I have to build a classification model. Okay. This again has been shared with you. You can go to IP. You can use this as a data set, and this is a model, and you can follow the steps. I'm doing it in a separate cloud because I needed more compute for this. Okay, no other reason. Fine. Now, if I see this data, my data is yeah. Okay, I have not connected yet. Okay, now it is connected. I am mounting. I am mounted. Oh, this folder itself is missing. Okay, my bad. The folder itself is missing. I'll create a folder. So I am creating a folder called as IP_labs. In this folder, one second, I made a mistake. This is already there. Okay, I have changed the position. So let's see this thing. I have a file present here, correct? Everyone can see this one in my Google Drive. This is the file I want. Yes or no? Yes or no? Couple of more yes required. Okay. I click on these three dots. What do I get? Copy path. I will copy this path and I'll paste the path here. Okay. The path is same as whatever I am here. I got my path. Now, what do I want? I want to read this CSV file present here in my collab. So what I do here is I will give this path and it already has CSV. So I don't need to pass the CSV here. I'll just pass it like this. Right? Make sense? This is how I read the data in collab. Yes or no? At this stage, the data is 5,000 records. There is a column called as binary. I don't need it. I'll drop it. This is the column which I need to predict. So if you will see this file, I have three categories: other, abuse, insult, profanity. Okay. The data is not balanced, but that is not my use case. So what I do here is I'm first trying to call these values as 1, 2, 3, 4 or 0, 1, 2, 3. So I will do a label encoder and I'll convert it into a 0, 1, 2, 3. Okay. Second thing is I don't need this much amount of data to teach you how it works. So what I'll do here is I'll take a fraction of data out of it. That is sample data, which is df.sample fraction. Now the fraction of data is nothing but 250 records. I am just taking 250 records for my lab, okay, for this particular data. Are we good till this step? If I have to build a classifier, what will I do? I need a tokenizer. I need to embed. I need all those things if I have to use any other way of working. Are we good till this part? Are you good till this part? Now we will do the train and test split. So once we do train and test split, we have 225 record in train, 25 in test. Okay. Now what we need to do here is we will be installing accelerate and simple transformer. Understand one thing, if you are using these accelerate and simple transformer, always connect with T4 GPU. Okay. Always connect with T4 GPU. Otherwise, it will not work. So let it run. It will give you a runtime error. It's okay. You have to restart the work again, installing the game. Okay. We are still installing the libraries. Okay. So simple transformer is built on top of BERT transformer to simplify the work. It has its own category of things. So let it get installed and then I'll show you the rest of the steps. So in this case, we will see we are defining the training parameters and we are directly building the model. Here is the case where we are defining the classification model as BERT and defining which one we want to use. Okay, we have to restart the session. That's how it works. Once it is restarted, we will run again, but this time we will not run the pip install. That part we will not run. That is to be run only once. So again, we are running it. Clean test split. This part we will not run. Now we will run directly simple transformer. So what we are doing here is we are directly training the classification model by using this class. If you want to explore, simple transformer is available. Okay, so you can explore this data. So you can define the classification model. You can load the predefined model and you can directly use it for work. Now, model has been loaded, right? What is that? What we have to do here is we take the training data. If you see, there is no tokenizer also here as of now, correct? Yes or no? No tokenizer, no model. Directly we are using it, directly we are training it. Everything is encapsulated. Are we able to follow to this part? This is exactly how we can use using sklearn. We get the model, we define which model, and we just train it. And we can evaluate it. If you want, you can increase the training data size and train it. Are you clear to this part? So if whatever value you want to pass now, let's say this is a tweet you want to analyze, you have to just pass into the model.predict in LDist, and it will tell you which category it is. Since it is trained on less data, it is not a very effective method. Now at this stage, what you can do here is you can save the model. Okay, you can save the model, and whenever you want it, you can use it at a runtime. So whichever you will say, it will not going to work better because we know that most of the data is in the other category. It is not easy to identify these values with less data. So if you train it on the whole data, you will be able to make a better prediction. But the steps are very much clear. What are the steps that we are using here? We are using simple transformer. In simple transformer, we are just using the name of which model we want. We are not doing anything else. This will create a model. We can use model.train on data, and then we can use model.predict. This is another way of building a transformer-based classifier.
Just a quick info guys, Intellipaat offers generative AI and prompt engineering course which will help you gain proficiency in creating generative AI chatbots and other Gen AI tools, along with mastering the latest tools and techniques with hands-on projects and real-world case studies. And the best part, this course will be taught to you by IIT faculty and the top 1% industry experts. What's more, you'll be getting your generative AI and prompt engineering certification from Microsoft. With this course, we have already helped thousands of professionals in successful career transitions. You can check out their testimonials on our Achievers channel, whose link is given in the description down below. Without a doubt, this course can set your careers to new heights. So visit the course page link given down in the description below and take your first step towards your journey as a Gen AI engineer.
We used simple transformer and we downloaded the BERT and we used it. You guys remember it? It is actually not constructed in a right way. We will reconstruct it. So simple transformer is the one flavor by which we can use BERT. But this takes away most of the customization that are needed. So for that, I am sharing with you the BERT explainer. This is it. Okay. So now, how do I use BERT for an classification? Okay. So how do I use BERT for classification. Now for that, we have one method, that is the basic method is we can use simple transformer. It is a very high level transformer. It uses an API. API will get the model loaded into the system. Model is loaded into the system. And we can make all the calls onto the system. Okay. This is basically works like a framework. The second way of doing here is we can use BERT from interface. Let's see that code. So what are we trying to do here? We have been given the data. This is the data that has been given to us. These are my classes. Are you able to understand this part? Data is given to me and classes are known to me. Data has text and labels. If you will see, it is basically like this. This is your text. Yes. Then next step here is we are splitting the data here. Okay. So the next step here is we are splitting the data. So how do we do that? We will use our basic train test split. Next is if we have to start with a BERT, what is the first step that we need to do? Yes, I hardly have 4 lines because it is for more of an understanding how it will work. You can take an Excel sheet and you can build a whole model on top of it. Right? This step you can take it from an Excel also, isn't it? Yes or no? Every individual sentence is a context. This needs to be tokenized and embedded. Okay. Yes, this is context which we'll use for predicting. We will train. Okay, yeah. See, understand this part. How does any classification work? This is your classification model. How will it work? How will it work? You need to tokenize it. You need to create embeddings for it. Once you have created the embeddings, you will create a model out of it. And that model will be used for prediction. Yes. Now, how will you do with the basic model? You will do it with NLTK. You can use TF-IDF, or you can use Word2Vec. Then you will create the model. Model you can create either with your neural network or your machine learning model, and then you do the prediction. Similarly, if you are doing it in a BERT or in a transformer-based method, not BERT, you are going to repeat the steps. What are the steps? You have to tokenize it. You have to perform the embedding. Okay. But when you are passing this model into the BERT, the main character will come whether whatever you are embedding should have size 512 or less, depending upon how much BERT model can take. Okay. Now there can be multiple cases to it. You can have case A. Case A is you have size less than 512. And you have case B where size is greater than 512. If your size is less than 512, it can directly get here. Will directly go. The problem will only come if the size is greater than 512. Right? So for that, if you have a size Yeah, but why that is a, why you are worried for that? I'm missing that part. So let me outthink it. You are worried because the model that will come out of it will not be a best model, right? Yeah. But what is your goal here? Build the model or to first understand how do you write a custom logic for BERT, right? So there are steps that require attention from you guys to understand how it can be done. Okay. Once that is done, we can always build a custom model which is on a bigger size. That's not a problem. We have to just change the input here with an Excel sheet which has a lot of data. Because this step, we all know we can convert every data frame like this. Yes or no? So what are the steps? We first tokenize it. When we have to tokenize, we have to first get our BERT models. So we have to get the BERT model, we have to get the BERT tokenizer. In this case, we are using BERT base uncased. Everyone knows how to go to Hugging Face and get the model, right? Now we are defining here the maximum length is 512 because that is a size which we take. 512, you can think of it as a 512 words. Okay. So every line should have words which should be less than 512 if we have to embed it. If it is more than that, then it is a challenge. Now that could be an interesting thing. What will we do if the word size is greater than 512? So I can have a paragraph which is less than 512. This will get tokenized, embedding will be created. I can have a large paragraph which is greater than 512. For this, what will we do? Because the tokenizer will end automatically at 512. The rest of the part will be left without getting properly treated. So one method is just go by default. Don't worry about whatever gets truncated because we are going to check the first 512 words. That is approach A. First 512 words. Approach B is take a model which is bigger and has a bigger context window. Okay. Okay. So there are different models like LBERT, BigBERT, BigBERT is there, or XML, XLM. This is basically a shortcut method where the context window goes probably up to 1024. But then there is a problem because you might have documents which are above 1024. How do we handle them? So the theoretical way is if you have a document, let's say of the size 2400, what I can do here is I will convert it into small chunks of 512 each. Okay. Then I will get my embedding from here. I will get my embedding from here. I'll get my embedding from here. I'll get my embedding from here. I will take an average of the entire embedding and I'll get my final embedding. That will represents my large document. Make sense? And this is, yeah, this is BigBERT. Is it possible to repeat once? A little hard to understand. Okay. So we were talking about the context window. The issue is context window. Before that, we had TF-IDF. It does not have any issue. It has dimension. Then we have LSTM. It has the size. What is the length that we are keeping? Let's try to keep the length restricted. You remember this? In the class one, we understood that the length of the sentence should be restricted. So size matters. Then when we were progressing towards this size, we realized if we have to use a complex model, the size is going to make a lot of difference. Then we started with transformer. Transformer has more context window as compared to LSTM. If we see LSTM averages out at some stage when you start giving long sentences. Transformer do slightly better on that length. But transformer also has the limitation. Okay, now transformer has variations called as BERT or GPT. Let's take BERT. In BERT, the context window is 5112, already defined. Now the problem here is the input size is increasing. I can have a document which is of the size 512 and I can also have a document which has the size 1024. That means it's a big document, it's a small document. This I can directly pass into BERT. Why? Because the size matches. But for 1024, directly if I will pass, I will miss the information. Yes or no? Okay. So for that, what I will do here is I will split my 1024 into two documents. 512, 512. Okay. Both of them will generate their embedding and I will take an average of it. When I will do this step, I will miss information. That is for sure. But that will be relatively less as compared to just taking only half of the document and leaving the other half. Now, if you pass even 2024 document length into the BERT, it will take it easily. It will not make a fuss because the parameter itself is set to 512. Can I take the need for such a long context is required because if we want to predict executive summary of report, then the entire report has to be read. Similarly, if you want to generate a movie or an image sequence, it requires lots of previous data to compute. Yes, exactly. Your data is always big. Whatever use cases we were trying to solve at this stage are no longer the point. Okay, I will just explain what Vilas has mentioned in a slightly different way. The best use case everywhere you used to go was summary or let's say Q&A. Okay, so that is there. But now, if you will observe, people are not only looking for summary and Q&A. People are also interested in the summary should have certain attributes. The Q&A has to be done from the document that I have asked. The size of the document is increasing. Okay. So the sophistication around the use cases are becoming more and more focused, concise, to the point. This is what I need. 2 years back, people were happy if something was generated on the computers. Literally, they were happy with that part. When ChatGPT came, everyone was happy something is getting printed. But now people are looking into it, what is getting printed. Okay. Am I missing an information or not? So the size, actual size is coming into the play, the real size. Earlier, we were taking one paragraph, passing into the system, and we're asking, what do you think is happening in this paragraph? Now we have extended that into a book itself. So now we want to pass the book and want to find the summary. Because of that change, this architecture has to enhanced. Clear? Make sense? Make sense? Okay. The point here is you can use simple transformer. Why can't we leave the size to the customized by the developer? You are the developer. You are the developer who has to write it, right? What will be the job of an NLP engineer if not this? It goes back to vanishing and exploding gradient. I won't say that. It goes into the missing information domain. If you don't take care of the size, you miss the information. Now coming back to the BERT, how it works. So we have BERT tokenizer, we have train encoding, we have text encoding. So encoding is done using BERT tokenizer. So embedding have been, let's say, created. Now, if you want to use a custom BERT, we have to first construct a data set. How do we construct a data set? Now we are taking the library from Torch itself. We are constructing the data set using this particular library. So please pay attention. You have two ways of doing it. Either use TensorFlow framework or use Torch framework. The most commonly used and accepted framework at today's time is Torch, PyTorch. So please stick to Torch. Okay. Now what it says, please pay attention. We are declaring a class called as text data, which inherits dataset. Dataset is a predefined class in Torch. And when I say Torch, it means framework PyTorch. Is the first line clear? We are defining the class text data, which inherits its property from dataset, which is a predefined class in PyTorch. Are we good till this line? Okay. Next step here is we build the initializer that is called as init function. What does it take? It takes input of encoding. It takes the label. So for any given text, I should have the encoding. So if I'm passing the input A, I should have its encoding with me. I should have its label with me. I will pass that label and the initialization will happen. So if I have to do the training, what I have to do here is I have to get the text from my input one by one in a sequential fashion. At every stage, I have to have its encoding and its label. Encoding will come from encoding class, which we have already done up. Label is we have already have the label from the beginning. So we will take these two items. We will do the initialization. We will keep the length of the labels with us. It is required to understand what is the number of samples that are present in the data set. And then this entire thing of one by one will come using get item function. So this is where the initialization happen. This is where the size happen. And this is where one by one, I can use the data for my training purpose. Are you clear with the three functions within the class? Okay. So we will run this class as it is. Now, what do we want? We want train data set and test data set. So we will use this class text data set for my train data set and test data set. Now, how do I do it? I use data loader. What data loader will do here is data loader will take the batch of 8 and will start creating one unit of 8 batches into data loader, and we will get a trained loader as an object and test loader as an object. Then we set our optimizer. I have set optimizer to Adam. You can use it to SGD. You can use it to Adagrad or anything of your choice. So this is preparing the batches that needs to be trained. So by this time, you know that we train the data in deep learning in batches. Yes or no? If we have a data, we will first split it into train and test. Then we need to put them into the batches. Okay. If I have to do the same thing in PyTorch, I have to curate the data into train and test and then create the batches out of it. This batches will get into my model for training. So batches has to be inside it. Okay. So second step is, yes, it's a fair understanding. Then we set the optimizer, and this is where we set our main device. That what is my device? Is my device having GPU or TPU? If it is having GPU, use CUDA. If it is not having GPU, use CPU. And we are loading the model, whatever is in our cache or RAM. Okay, this is the BERT model that we have loaded. Now this BERT model, which is loaded, yes, if you take smaller size, it takes lot of time to converge. If you take larger size, it takes small time to converge. Larger size usually means less effective model, usually. But sometimes if the data is way too big, data size, then large size you can take. Large size also have a limitation of saving into the memory, because whatever you are doing, for example, this model this needs to be in the memory. Till the time you are using the model, it has to be in your RAM. Okay. If your RAM is not big, it will crash. So most of the deep learning, when you do it on your local laptop, they crash. The reason is because model size is in GBs. So that much amount of GB, let's say you have an 8 GB RAM, 2.5 GB will be taken by the model. Then you have a data in GBs. So every time you pass the data, it will crash because OS has to be there, other things has to be there. So that is why minimum 16 GB works out initially. But now since Collab is there or other cloud-based compute is there, so preference is to use them rather than your local machine. Because if you will see the size of these models, they are monstrous in nature. They're pretty big. For learning purpose, we can do this. That's why I'm keeping the data size small, models small. Because if we start taking the big models, it will become very difficult to show you also how it works. So model is now in my memory, and this is how model is getting saved. So it is a BERT embedding is getting used. 512 is the size, 768 is the dimension. So embedding is 512 cross 768. Okay. So the size is 512 and the dimension is 768. Then we have a BERT encoder. This is the intermediate layer, and then you have a BERT output. Okay. This is how internally the BERT model is working. Okay. Now, if I have to train the model, how will I use it? I will train the data. Okay. Yes, we have reached here. Okay. Now, first thing that we will study here is what is optimizer dot 0_grad. So I have trained the model. Once I train the model, what happens while training the model? In training, the forward pass works. Yes. Forward pass means if I have a neural network, if I am moving in this direction, it's called as forward pass. If I come backward and update the weight, it is called as a back propagation. You remember this? We discussed in the first class, gradient descent versus back propagation. And this is called as a backward pass. Are you aware of these terminologies? Forward pass, backward pass? Yes. Now, when you are doing the backward pass, we require optimizer dot 0_grad. What happens here is before the backward pass, the gradients for the model parameter need to be set to 0. This is because the gradients are accumulated by default in PyTorch. If we don't zero the gradient, the new gradient would be added to the existing one. So after every pass that we make, we need to set this to 0. Otherwise, we are going to carry forward the information of epoch 1 into the epoch 2, epoch 2 into the epoch 3. So we won't be able to get the right weights. So after every training, we will set the optimizer to not even the training. After every batch, we will set the optimizer to 0 and we will do the training. In the training, the first thing here is we need to identify our IDs. So I have an input. What is my input? It is a string. I will pass my input string. My input string has input ID. It has attention mask. It has label mask. I need to identify out of which what is my input, what is my attention, and what is my label. Then I will take input, attention, label separately and will start my training. So this process of identifying is happening over here. Okay, just to give you a more perspective of it, if this is my input text, if I'm doing the encoding, my encoding done here will have my input tensor. It will start with CLS, end with the SEP. These are my token IDs, tensor IDs, token tensor IDs, and this is my attention mask. Okay. Now I need to identify what is my input, what is my attention. Attention means what am I giving the priority to this word? Okay, let's take 1 is all important, 0 is more important. So that is how I am giving attention to every single word in the context. So once I have done the encoding, I have 3 different things present. I need to identify which is which one I need to take. Are you clear to this part? These are just the identifier. Okay. So once again, if you have any input, your input when you do the step encoding will convert your input text into 3 different things will generate. One will be the IDs, tensor IDs. Tensor ID is nothing but the tokens. 101 is CLS, 102 is SEP, 2023 will be the equivalent of whatever that word is. Right? Whatever that word is, we will do that. Then there is tensor ID, and then there are attention mechanism. Attention mechanism is internal mechanism where transformer prioritizes which word has what priority. At this stage, everyone is 1 because everyone is important. But internally, when the training happens, these things also gets updated. Okay, it is not 1 and 0, it gets updated inside the training process. Now let's see what happens in the training process. I have ensured my input ID. I have got my attention mechanism. I have got my labels. Okay. Now I am doing the forward pass. What is happening in the forward pass? I am this piece of code will perform the forward pass. The model use the batch data. The model returns the output, which typically includes the loss function also. That means I am performing this function. While performing this function, I am capturing the error. Okay, this error will get captured. Now I will take that error, identify the loss, and I will pass that loss backward. Now this step is my gradient descent, and this step is my back propagation. So let me repeat it again. When we get the training data, we will do the forward pass. While doing the forward pass, we are getting our error. This error will help us to estimate the loss. Okay. Now we will use this loss backward as a back propagation to update everything. What is that? We can update our weights, attention, everything inside it. So I am going to get my attention updated, weights updated by using this method. and this is my back propagation. And to optimize all of them, we will be using an optimizer step. Okay. If you don't want to use optimizer, then you won't be optimize your loss and gradient descent. Does it make sense? And this is how back propagation happens at the end of an iteration. Back propagation happens at the end of an iteration. It never happens at one step. So if I have an input sequence of numbers, because that you can understand easily, I am passing the numbers, I am getting my final output. My actual output was 16. My output which I generated is 14. The difference between them is 2. That is my loss. We are going to pass that 2 backwards to understand how the weights is. Now, at the end of each batch, you mean? Yes. Now, what happens is, if this is my loss function, this is the minimalistic error. I want to reach to this point. What I'm doing here is I'm taking the steps like this and coming over here. Yes or no? This is how you calculate the gradient descent. But if my gradient descent has this kind of a curve, how will I identify the minimum point? This is also a minimum point. This is also a minimum point. This is definitely the best minimum. And these are also minimum points. So this is my local minima. This is my local minima. This is my global minima. And this is my local minima. If I keep on playing over here, I might converge here itself. I might not able to see here. In order to avoid this, what do we do? In order to avoid this situation, what do? We pass information via batches. Now this process is called as SGD, stochastic gradient descent, where you pass the information through batches. If this is my data, okay, I can run entire data and send the message backwards. This is approach 1. My approach 2 is I will keep sending backward after every step. My third approach is I will take a batch of data, get an average out of it, and then I will send. Then I'll take another batch of data, and then I will send. This is mini batch process. Sorry, this is called as a mini batch stochastic gradient, mini batch. This is the idealistic way of, not idealistic, this is how the way if you write SGD, this is how it works. Because if you start doing it, it becomes too expensive to run. Okay. Are you able to understand? All the atoms, AdaGrad, everything, momentum based. This is, those are the extension to it. This is atom or ADA or momentum or whatever. At a risk of sounding daft, I am slightly confused. If back propagation is done at the end of the batch, then how this approach is different to usual machine learning approach where we have learning rate program. How, when did, okay. But why you think there is back propagation? No, I mean, I don't want to sound anything, whatever you have mentioned, but back propagation doesn't exist in machine learning. Right? See, if you have a node and this is your final output. Okay. Now you want to know the impact of each. You want to know the impact of each and every one in the input side. Or you are updating these. What are you updating? You are updating this or you are updating this. You are updating layer 1 or you are updating layer 2 and layer 3. In machine learning, the output updates layer 1, be it MSC or be it SGT. It optimizes what should be my layer 1. Back propagation means you go back and you update every single aspect inside. And back propagation also means what is an individual impact should also get varied. Back propagation doesn't mean just simple updates. Back propagation means if I have to take the car from point A to point B, and I am going through different junctions. Now, if I start at 10 a.m. and if I reach at 12 a.m., what I am trying to say here is, it is taking me 2 hours. Update this time by 2 hours. This is machine learning. Back propagation says, it is not just the starting point. If you take a different route, if you optimize this, because the impact of the delay, if there is a 2 hours delay, 20% problem comes from here, 30% comes from here, 10% comes from here, and 40% comes from, okay, 50% comes from here. So rather than optimizing part A, you should first optimize E. Is there a different way in which rather than taking E, I can take an alternate route? I will save almost 50% of my time, even if I start at 10 a.m. This is back propagation in layman's term. Make sense? Just think of this like you taking a metro. So rather than taking this station, find another station by which you reach B. I get that, but when you use batch for back propagation updates, there is where I'm getting lost. Now you want to take 1 person time to estimate it, or you want to take 20 people. If you take 20 people, it is a batch. If you take 1 person, it is single. Right? If you take 20 people, it is batch. To update the metro time, you want to reach to station B from station A, you can estimate what is the impact of individual C, D, E station by taking 1 person or taking 20%. If you take 1 person, it is also back propagation. If you take 20 people, it is also back propagation. It is said that taking 20 people is better than taking 1 person, because if you take 1 person at a time, you may end up with this problem of getting into local minimum. Make sense? Okay, so where were we? So this is where the loss happens, and this is how we evaluate it. Now, if you want to evaluate, this is the class which helps in evaluating the. Now, since like we said initially, the data is very less, we are not going to get the best model out of here. If you want the model to become better, you have to pass the more data here. Rather than just 3 sentences, pass more data to evaluate. But the purpose here is to understand how the rest of the code is working. So if you want to use this code for prediction, your encoding should be there with you. You should have identify your ID, attention mask, and then you can actually generate for any input that you have asked. You can use this function, predict function, where you are passing text, model, tokenizer, and the device on which you are loading it, and you can actually get your output. So it is getting identified. This whatever we are writing is getting identified as 0. Mostly everything will get identified as 0. There is no doubt about it. But if you increase the size, the answer will become better. But the idea here is not to get a better model. The idea here is, do you understand the structure by which you have to write? Because this is not an easy structure. It is a very different structure than whatever you have learned so far of predicting a data. Make sense? Questions? There are two more layers by which you can go down and fine tune the model. I'm just giving you the tip of an iceberg, which at least give you the feel of how you can code it using BERT. You can actually write the entire transformer and then you can train it. That is also doable. You can decide the size of your heads, how many heads you want, how many layers of transformer you want. You can do all those things. I understand back propagation in DL, but in ML, will it update the inputs? If your ML has back propagation, it will become DL. Are you clear till this part? This is how basic BERT works. And you will get a new models over here. You can use any of that model and replace your this step. And you can use this code. So it's not about BERT, it's about which model you are using it. That will change the whole scenario. So if I'm using classification, I can use, this is your finance BERT. BERT built on finance. Similarly, I think you have a bio BERT also. Yeah, there is a bio BERT. So for your specific domain, whichever you want to use, you can use it. You can log into it. You can upload your own data. You can use Hugging Face to train your model on your data. Whatever you want, you can do it using Hugging Face. But yes, if you think this is BERT, then yes, this gets used. But you have to increase a little bit of more depth to it. Are we good? I think it depending upon who developed, there might be inherent bias based on their needs. So let's take how does our Q&A works if you have to use it not by LLM but by BERT. Okay, shall we start this? What is the problem statement? The problem statement is how do we use BERT for question answering? There are different frameworks which are available for use. BERT this is just one basic rudimentary way of doing it. There are other ways of doing Q&A. So let's try to understand how Q&A works. So there is a question that you have to ask. Who is the PM of India? Okay. Now your answer is, and there is a context. Context would be PM of India. There would be one text which will be talking about this particular question. Yes or no? Yes or no? So if there is a model, I need to pass question and context, which will generate answer or answers, right? Are we good to this part? Yes, context is the corpus. So context is the corpus or the text. Whatever text you want to pass. It can be part from your PDF, book, PPT, Word, whatever, magazine, web page. So the Q&A will be something like this. There would be a user. User will pass the query. Query is basically your question. Then there would be a context or the corpus. Corpus will get structured. The question will try to identify out of this where is my answer, best answer. That answer has to come like this. Now, how do I convert into this to this is a separate task. Okay. Converting my data into the corpus is a separate task. But if we see our goal here is that I am going to ask a question and I am going to pass the context. Context will be a paragraph. How do I convert this into a paragraph is an engineering job. That I am not bothered. What I am bothered here is, if I have the paragraph and if I have the question, what is the mechanism to get my answer? If I can sort this out, I have to just add this element into this and it can become I can scale it. Right? So I'm going with a very rudimentary way of finding an answer. The best models that are available, you can find it on the Hugging Face. There are two models that we are going to use. Those are, sorry, there is a model that we are going to use, that is a SCORD data set. Now, SCORD data set is a model built by on a SCORD data set, SQUAD. So it is a predefined data set where question, answer, and context are given, and we will be using this model. Okay. The first step is clear. Is the first step clear? Now, this is the question and this is the answer. This is the answer text. That is the context which we will be using. Now, this is what it is. I have used the wrapper library to write it properly. BERT large is really big. It has 24 layers and an embedding size of 1024 for a total of 344 million parameters. Altogether, it is 1.3 GB. So expect it to take a couple of minutes to download to your Colab instance. This is the context. What is my question? How many parameter does BERT large have? So BERT large has 340 M parameters. Are we good till this part? Now, if I pass these two information, I should get my answer. But it is not plug and play. Okay. If you have to build a thing from the scratch, you should know how it works. So this is the function that you can pass. I will first tell you the function. Then I will show you the answer. Then I will take you step by step how it works. What is the logic behind it? Okay. The reason is, if you have to scale it, you should know how does scaling will work. Yalla Babu has a question. These question end user can enter as dynamic. Yes. These two things, expectation is the system will provide question and context. Okay. This is what it works to find the best answer. We will talk about the scaling aspect also, Yalla Babu. Okay. So what are the things that happens here? The first thing here is tokenize. Whatever is my question, I will tokenize it. Whatever is my context, answer text is context from where the answer has to come. I will tokenize it, encode it. Okay. Once I encode it, I will get input IDs. I will get attention. I will get other details. Okay. So this is where I will get the length of my IDs. That means what is the token size? Number of tokens that are present in my question. If you will see, I am adding both question and answer into my input IDs. Okay. So I have question, I have answer, I am merging them. I am saying this is the total input I am passing. First X is the question, last X is the context in which you have to find the answer. So how is it working? It is a question. So there is a question and there is a context. Context is called as answer text. Let's say it has 10 words and it has 30 words. So total input that I will pass into the BERT will be 10 plus 30, that is 40. Plus some tokens which are there for separation, that this is my question, this is my context. So this is what is happening so far. Next here is I am setting an indicator. Okay, the indicator is to separate my question from my answer. Okay, I've been asked to repeat. Let me repeat. There is a question. Who is the Prime Minister? 1, 2, 3, 4. And then there is a paragraph from where I have to find this answer. Let's say it goes from 1 to 10. So total it would be 10 plus 4, that is 14. 14 tokens are passing as a part of input. Plus some tokens to identify what is question and what is answer. So there is a token, there is question, there is token, and there is context. And this is getting passed as my input. Basically, this is my input to my BERT model. Next step here is I have put the separator index. Once I put the separator index, I identify what is getting separated from between question and answer. This is my separator index. But what I want here is I want the number. That means I would like to get this number. Let's say this number is 10. So I would say 10 is where my question ends. From 10 to the end of the string is my context. So I will be able to identify the index number. Index number will give me whatever is my starting point to this index number is my question. Whatever starts after this index till the end is my context. This is the idea which I am trying to identify using this. Now what happens here is I divide them into two separate segments. I call this as segment A. I call this as segment B. Segment A is a question. Segment B is a context. Okay. Next step here is I call my segment in with different IDs. I call segment A with 0. So I call every token of here identified as 0. Every token identified here is 1. Why? I want to identify what is my question, what is my context. I'll explain them again programmatically, but I'm just going through it once. This is a step which I'm trying to assert to see whatever is my input ID. Whatever is my input ID. My input ID was 10 plus 4, that is 14. If I am creating segment out of it, that means question is becoming 0, 0, 0, 0. Context is becoming 1. The length of this should exactly be 14. Okay. So what I'm doing here is there is an input. I am creating using a separator to identify my question and my context. I'm calling them different segments A and B. I'm assigning them values of 0 and values of 1 to identify their differences. Next is I pass the information of my inputs. I pass the information of my segment IDs. They will automatically identify what is my question, what is my answer, because my segment IDs are 0s and 1s. And I will get my output probabilities. At this step, I will get my output probabilities. Okay. Now output has nothing but set of probability. Okay. So I will identify my start and end of my answer. So this is the, let's say I have 100 tokens passed. First step here is I will identify at what stage my context starts. At what stage context starts. So what I get here is, let's say first 20 tokens are questions. Last 80 tokens are answers. Sorry, context. Then what I do here is I'll take these 80 tokens and I'll say in these 80 tokens, which token, each token should get a probability. Let's say 5%, token 1, token 2 should get 20%, token 3 should get some percent, 3% like that. So I get the probability between 21 to 100. This is my start, this is my end. And this step will give me all the probabilities. Okay. Then I identify which token has the highest probability. Okay. Let's say T28 has the highest probability. I will take that token. I will find which is the next best token. So I said 27 also has a good probability. So I will say 28 is the best, then 27 is the second best. So I will take the token over here. And this will combine together, will become my answer from my context. Are you able to correlate with the right part, what I have written? Shall I clear it? So with this, if we will see, we are formulating what my answers would be. So if I pass this information, I'll just run this function. And then I just run the answer. The answer is coming as query has 70 token and the answer is 3740 M. For this question and answer, this is the answer that we are getting. If you want, we can change the question and see the answer. Okay. Now, all these steps which I have shown here, I can show you in the explainer. So for example, the first step, if you are passing question and answer, it is telling you there are 70 tokens. Next step here is we are converting them into IDs. Okay. So if you will see that it is ending with separate, it is starting with CLS. There is another separate which has come to identify that this is my question. From here, I am starting the answer. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I start from 0, or if I start from 1, I have 10, then I have 1, 11, and then I start my context. Okay. Now what I'm trying to do here is I'm trying to map my CLS is 101. How is 2129? Similarly, I'll be finding for SEP and all the tokens are getting IDs. Now here I am trying to find where is my question getting ended. My question is getting ended at 10. I have counted and I've shown you how it works. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. But we have to add one more. So if you start from 0, it is 9 and this becomes 10. So total it is at the 10th index, my SCP comes. So now what happens? I will take my segment A as CLS to SCP. Segment B is SCP to the last one. So now I have separated my question and context separately. I am assigning them zeros and 1. And this is what I will generate my output. My output will come for my context. So every token is getting a probability, right? This is my end score, start score, end score. Okay. Now, what is the probability which is the maximum for start score? 41. So I am getting the start of my answer. I am getting the end of my answer with the help of my probabilities. Is it clear to this part? That you need to check. It depends upon the data, Shiv Kumar, what will have the probability. But if your answer is See, we are expecting the answer to be continuous in nature. So your start will come with a token with Narendra and end with the Modi. So it's not about what is going to be your Narendra has a higher probability or Modi has a higher probability. It is about at what token my answer starts. And then I reconstruct my answer. So what I do here is I take my start and end answer. So this is my start answer is 41. If I want to run, I can just run and check my end answer to see at which token my final answer is coming. So my final answer is ending at 42. Tensor 41 to 42 is my answer. I combine and reconstruct it. I get my final answer. My final answer is 340 million. If you want to visualize it, there is a visualization table I have created. So for every token, you see these are the questions and then we have the answers. So if we see, we have the highest probability at 340. It is identifying that my answer should be between 41 and 42. So that is 340 million. That is how behind the scene it works. This is a simple explanation of how Q&A works. Is it clear? Because from here we have to scale it up to a bigger problem. This is start and end string. Here is the maximum context length permissible is 512. Going back to my first question. Yes, it is 512. 3 participants at one go raised the hand. Okay. Interesting. I'll first go with Chitvilas. Yeah. I can't hear you, Chitvilas. Yeah, I'm coming to that one. I'm explaining the scaling part of it. That will cover it. So we have built a Q&A. Q&A we have built for a limited context. But what happens if I have a bigger data? That means, let's say I have a PDF and I have 10 pages. How will I get my answer from it? Yes. Now, there are different ways in which we can do it. The first one here is the BERT way. The one I have shown you. What is it? I have a question. And then I have data. My data have 10 pages. Now what I have to do here is I have to convert these pages into chunks of 512. No, not 512. I have to convert it into chunks. I'll come to the size later. Okay. Dot. That's it. Then what I'll do here is I will append my question to each one of it. And each question and pair context will be passed as a pair to the model, and model will generate one answer. Answer 1 will be generated. Answer 2 will be generated. Answer 3 will be generated, and answer n will be generated. Okay. Out of these answers, I know what is the probability because that is what we are capturing. We are capturing the probability. So each of them has a probability also. So this one has a probability P1, probability P2, and probability N. I can take top P probabilities in order to get my best answers. At any given time, my question and my context should be less than 512, which is getting passed. Now, how do I optimize it? Because it's a very slow process. The chunks can be ranked. and we can choose top 5 chunks and then find the answer. How do I find the top 5 chunks? I can do the semantic similarity between the question and the context. I should not call it as a semantic similarity. I can just call it as a similarity. So how do you do a similarity between question and context? You can use a distance calculation. Second, what can you do? You can do parallel processing and check all 5 answers, answer 1, answer 2, answer 3, answer 4, answer 5, and get the maximum probability out of it using arguments. This is how you can optimize this method if the data is large. This is the key principle behind any Q&A that works using OpenAI, using Gemini, using ChatGPT, using Claude, using Bedrock, whatever you want to call it. Then there are frameworks. One which uses LLM, one which do not use. LLM, if you want to use, you can use LangChain. If you don't want to use LLM, you can use Haystack. What Haystack does here is, Haystack provides reading plus answering capability. You have to only configure. That's one way. LangChain will use OpenAI, or it will use some LLM like Hugging Face. It is just a framework. Okay. There is another way of doing here is that is called as CDQA. That is called as closed domain question answer. But I think this library is deprecated. That means nobody is maintaining it. So there are multiple ways. Again, we will recap it. You can use the BERT plus self-customization. When we talk about the self-customization, it will believe in chunking and finding answer. Or you can use a framework which can do that. It can be Haystack. The third way you can do here is you can use LangChain or an equivalent framework for LLM based. Now, depending upon your budget, depending upon your complexity of the problem, you can choose one of these solutions. Does it make sense? Okay, I will show you. I'll paste this one. So deep set Haystack is your framework which you can use in order to build your Q&A. Documentation. I will just pick up. So you can look into it. It will give you a good understanding on how you can use Haystack for question answer or any other activity that you want, with or without LLM. You don't need to use LLM all the time. Okay. Click on tutorials.
creating your first QA pipeline with retrieval augmentation, that is RAG. You don't need it. Build a chat application. This is all ready to used libraries if you want. Next is, if you don't want a stack, what you can do here is you can go to OpenAI. Okay. If you go to OpenAI, OpenAI gives you some free access. Go to the login. You can click on API. You can log in into it. You can go over here, your profile. You can go to the API keys. You can create your API key here. You can create your project key here. It allows you for every email that gets registered for 3 months of free usage. So you can use 3 months of free usage. Okay. Are you following it? This is your playground. You can explore whatever you want. You want text generation, you can get text generation. You want prompt engineering, you can look into it. So if you want to use text generation, this is the piece of code you can use, and you can try it here also to see whether it is working or not. You can try different models to see it works. It has some specific limitations. Okay, so you can try a licensed version. You can use Hugging Face. You can club Hugging Face and OpenAI. You can use Hugging Face separately, or you can use BERT at its native way. Any one of this can be used for its purpose. Are we good? I'm going to save this file. 14 July. See you. Thank you. Bye-bye.
Just a quick info guys, Intellipaat offers generative AI and prompt engineering course which will help you gain proficiency in creating generative AI chatbots and other Gen AI tools, along with mastering the latest tools and techniques with hands-on projects and real-world case studies. And the best part, this course will be taught to you by IIT faculty and the top 1% industry experts. What's more, you'll be getting your generative AI and prompt engineering certification from Microsoft. With this course, we have already helped thousands of professionals in successful career transitions. You can check out their testimonials on our Achievers channel, whose link is given in the description down below. Without a doubt, this course can set your careers to new heights. So visit the course page link given down in the description below and take your first step towards your journey as a Gen AI engineer.